Great. Welcome to the RQI Circuit. So this is the fourth local edition of the RQI Circuit 2026. This Friday, we're here in Waterloo at the University of Waterloo and the Institute of Quantum Computing, which is also supporting this event. The event is organized by Boris Ragula, Ahmed Shalabi, Matheus Zambianco, and Ireneo Membrere. And thank you guys so much for organizing this. So this RQI Circuit is a series of local conferences that is happening every Friday at a different RQI hub, and it's being broadcast live on YouTube. Next week, we're going to have our event in Manchester, and this week we're here in Waterloo, so let me give it to Boris without further ado, so that he can introduce the first speaker.
Yep. All right. Oh, yeah, I have to get it framed. All right, thanks again, everyone, for attending and everyone online. And I'd like to introduce our first plenary speaker of the day, Rob Mann, who's going to be talking to us about testing detectors in superpositions. Rob, all yours.
Okay, thanks Boris and Rick for, and all the others for organizing this. Matheus, Ireneo, and did I miss somebody? And Ahmed, of course. Gee, staring me in the face. So yes, it's nice to be here and talk about this relatively new and I would contend very simple idea that we came up with not too long ago. This is work with Cisco Gooding and Taylor Say. It's supposed to say Say. That's some stupid spell checker thing, I guess. And it's about possibly testing something in RQI that I sort of feel should have been thought of quite a while ago. So this work is motivated because I think one of the goals of quantum gravity is to understand space-time in superposition. We still do not have a quantum theory of gravity. There are contenders, but there is certainly no fully agreed upon theory, I would say, and of the contenders, there's still a lot of gaps. But whatever a quantum theory of gravity will do or should do, we certainly expect that it will allow some kind of superposition of space-time. Superpositions of different masses, mass curve space. So if you put a mass here and superposition with a location over there, there'll be a slightly different warpage of space and time, and therefore that's effectively a superposition of space-times. So no matter what the theory is, this is what it should do. And so one can ask, how can we try to understand this when we lack a full theory of quantum gravity? And what I've been concerned with over the past few years is asking, if we had such a thing, what would it look like? How would we detect it? How would a detector respond in such a situation? And the model detector that's used in 99% of all such studies is a UDW detector, a simple two-level system having a ground state and an excited state separated by an energy gap omega, as I'm sure is well known to everybody both here in this room and listening. So I talked about space-time superposition, so why do we care about superposing detectors? Well, the basic reason is that superposed detector paths in single space-time correspond to single detector paths in superposed diffeomorphic space-times. And this goes back to the work of quantum reference frames by Flaminia Giacomini and Esteban Castro-Ruiz and Czesław Bruckner and other papers. There are many collaborators, but one can ask from the viewpoint of quantum reference frames, if you had a photon or an electron in a superposition of paths, you could do a transformation so the paths were equivalent, but the space-times, of course, would then be in superposition. Now, the two are diffeomorphic. The two space-times are diffeomorphic that have been placed in superposition, so there doesn't seem to be too much point in doing this. But the interesting things happen if you make the hypothesis that this works even when they are not in even when the two spacetimes are not diffeomorphic. So the formalism that we've been employing is to just take what is done in quantum reference frames when you transform to superposed paths, or from superposed paths to superposed diffeomorphic spacetimes, and then just make the hypothesis that this works even when they are not diffeomorphic. So that's the motivation, but I'm not actually going to be doing this on the right. I'm going to be looking at this on the left because it occurred to us that this is at least a necessary test. Now you might say, well, why bother? I hope maybe I'll convince you of that, so let me postpone that question. So here is the basic detector formalism. The top line is the Einstein action with a scalar field and a possible conformal coupling parameterized by xi, which can be 0 or the conformal value, which depends on the number of dimensions, or whatever else you want it to be. Then there is the action for the point light detector, which can be smeared out and probably should be smeared out, but I'm not going to do that here. And then there is the coupling of the detector to the field, which can be, of course, many different things. This is the simplest coupling, namely a linear one, which is what people generally use. And the operator in there is given by this combination of raising and lowering operators coupled to the field. So let me put these two things in. It's called the monopole operator, and sigma plus takes the system from the ground to the excited state. Sigma minus takes it from the excited state to the ground state. And they're accompanied by these frequency functions here, e to the plus or minus I omega t. You can put in a switching function that is a way of turning on or off the detector. If the detector were charged, it would be a Faraday cage, but in general, you imagine there is some way of shielding the detector. Here I put in a Gaussian. And so in what is well known now, I think, to many, maybe not all people in this room, is that if you start with some initial state and then evolve it unitarily in the interaction picture, which is the time-ordered product of e to the minus I, the integral of dt over d tau dt times this Hamiltonian, since the detector could be at a different frame than the lab, so you have a d tau dt factor, then this would be the final state, final density matrix of the system. And what we're most of the time interested in is what the reduced density matrix is of the detectors. So we trace over the quantum field, and then that gives us a density matrix that depends only on detector parameters, but indirectly on field parameters, or semi-directly, maybe I should say. So the two most common scenarios for looking at this are the single detector scenario or the two detector scenario, where you end up, when you calculate this out in powers of the coupling lambda, get matrices that look either like this on the left for a single detector or this on the right for two detectors. And they depend on three quantities: the response, the correlations, and the non-local correlations, P, C, and X. Sometimes people use different letters like L and M and so on, but they basically look like that. And they have this X shape. In fact, if you went to all orders, the structure of this two detector matrix would not change. You would simply have another entry in the lower right here. And that is a general feature of these systems. It would be modified if you made certain modifications to the field, then you could get other entries in there. But I'm going to stick with these things. So what I'm most interested here in this presentation is the response, P. All all of them, I said they depend on detector parameters and semi-directly on field parameters. Well, the semi-direct part is right here, the Whiteman function, which here is the expectation value of the fields in some state. Here I've taken it to be the vacuum, but it could be a thermal state, it could be a coherent state, it could be all kinds of things. But here I've taken it to be the vacuum. And so what that means is that the final reduced density matrix of the detectors depends not only on properties of the detectors, like their motion in space-time, but also the curvature of space-time, the initial state of the field, which I already said, vacuum or thermal or coherent, etc., and on what the quantum field is. Here I've taken it to be a scalar, but one can consider couplings to fermion fields, vector fields, gravitons, etc. The idea of using a scalar is that, well, it's twofold. From a theoretical viewpoint, the general perspective is that it captures the most essential properties of interest when you investigate these things. It lacks what will happen as a consequence of spin, but it seems to capture most of the other features. But the other reason for doing it is that it actually does seem to be relevant for experimental testing, which I will get to a bit later. So, that's the basic detector formalism, but to understand superposition, we need to go to quantum-controlled detectors. And this is an idea that I don't think anybody did before Eduardo and Yvette and I looked at this 15 years ago. Boy, oh boy, time flies. And our basic idea is we exploited the superposition of detectors to see if we could somehow amplify the Unruh effect. And I'll maybe mention a bit more about that later. But when you have a superposed detector, we use quantum controls, which are quantum degrees of freedom C1, C2. And so the detector in superposition, if it's on path number 1, is this working here? If it's on path number 1, it'll be in this state, and if it's on path number 2, it'll be in that state. And since the beam splitter puts it in superposition, we have this kind of superposition coming in here. And so that Hamiltonian I showed you a couple of slides ago gets modified now so that the coupling of the detector to the field has a different switcher along each path in principle, and it's coupled to the density matrix of the controls along each path. So we call these control qubits. And then what you would do would be to measure this thing in the control state, and you do that by putting another beam splitter here at the upper right or not. You could not put in one and have detector counts at the end of these paths, in which case you would get no interference, but you could put in a second beam splitter, which would be like measuring in some superposition of C1 and C2, and then you would see some kind of interference in principle. So what can happen in general when you measure in the control state, and here I've done it for n different possible controls, is you find that the response function becomes this sum over these quantities here, the product of the switching functions times these phase factors, e to the minus I omega, integrated over the Whiteman functions along all of the possible paths. So path 1 with 1, 1 with 2, 1 with 3, 2 with 1, 2 with 2, 2 with 3, etc., etc. As many as you've got. And the point is that W12, or Wij, where I is not equal to j, is not trivial. And that's what gives interference that would otherwise be absent. So I already mentioned this paper that we had 15 years ago, where we found that the idea was to accelerate the UDW detector in the upper box and let it remain inertial in the lower box, and arranged the paths so the path lengths corresponded, that we got proper crossover when they came out. And what we found is there was a non-trivial Berry phase around this loop that made effectively made the detection of the Unruh effect sensitive by more than 6 orders of magnitude. So the hope was that maybe if one could carry out this kind of experiment, one could then very sensitively measure the phase change in the Berry phase and get evidence of the Unruh effect. Well, a number of years later, Magdalena Zeik suggested we look at this kind of thing again, and so we did, and that set me on this present path. What we found in early work with Josh Fu and Sho Ono is that a superposed detector can distinguish between whether or not it's in a thermal bath or whether or not it's in a de Sitter spacetime, for example, or whether it's in a state of acceleration. This, let me go back to the thermal case. So superposed thermal is not the same response as superposed de Sitter. However, on a classical trajectory, without superposition, they are indistinguishable. That's what Gibbons and Hawking showed a long time ago. But a single detector can interfere with itself, and then you would know whether it was this or whether it was the de Sitter case. This also works with 2 detectors, as shown by Versteeg and Menikuchi, but you can even do it with 1 if you put it in superposition. And then it also was shown in this paper 5 years ago now that this superposition can amplify entanglement extraction or entanglement harvesting from the quantum vacuum, so that density matrix of 2 detectors I showed gets modified when you have 2 detectors each in superposition. It becomes a lot more complicated, but the interference, if you set things up right, can amplify such effects. So there's a lot of interest in trying to test things with RQI, most prominently the Unruh effect, which is sort of the holy grail of this kind of thing, that you really want to see if accelerated detectors perceive themselves to be in a thermal bath. That's very difficult. Entanglement harvesting would also be nice to test, and I've chatted with people in Nottingham about that, and we have a paper on that possibility. There are experiments in electro-optical sampling that look at non-local correlations at the vacuum, and we'd like to do this, test space-time superposition, all that stuff. But there's a very simple thing that we should test, and that is simple detector superposition. So let's just consider a static detector in a state of superposition. No acceleration, no trying to harvest entanglement, just this feature. So why? Well, a single detector, when I equals j, has this Wightman function, where s is tau minus tau prime. I should have written that on the screen. Whereas a superposed detector, separated by where the paths are separated by some distance delta, is given by this Wightman function. And so what had occurred to us is that you will get different responses. Why not test it? It's the simplest test we can think of the very basic RQI formalism. It is the least painful test that is not trivial, in my opinion. So that's what we set out to show. So the overall response will be given by this sum, if it's just 2 paths, over Fij, where Fij is this integral over the Wightman function for a constant switching function, the simplest switching function I can think of. Leave the silly thing on. So what happens for a single detector, as is well known, is you just get a half times the Heaviside set function of minus omega, whereas here when the paths are separated by delta, you get the same thing multiplied by this Bessel function that depends on this product of the separation times the frequency. Yeah.
This is only 2 plus 1, right? All the results are saying that
This is, in this case, this would be 2 plus 1. I'm sorry, yeah. Yeah, this is 2 plus 1. I should have put that on the screen. And there's a reason why I'm saying 2 plus 1 that I'll get to momentarily. You could do this for other detectors. We did it for 2 plus 1 for an upcoming reason. I should have put that on there. So this is what we have in our paper. It's such a simple calculation. It's almost embarrassing to put it in, but not that embarrassing. And so here in 2 plus 1, this is the difference in the response. The Heaviside step function says what is very clear. For a single detector, if omega is negative, that means you've started in the excited state, because negative omega means E is smaller than G, so G is like the excited state, and you'll have a response for negative omega, which means it wants to decay, but for positive omega, you start in the ground state, and nothing's going to happen. However, if the paths interfere, while nothing happens for positive omega, you'll get interference for negative omega, and this should be detectable. So this is why we have the 2 plus 1 result. It's because Cisco has an affiliation with this group. I have a weaker affiliation, I suppose. And
you have about 5 more minutes till your question.
yeah, okay. He said, yeah. And what they proposed in this paper 6 years ago is taking a laser, splitting it into 2 sidebands, filtering out the midband, and the idea is that these sidebands form the 2 levels of the UDW. In fact, they sort of form a continuum of 2 levels. And then what you do is you put it in a rotating deflector that has the beam go round and round and round, and that will give the an effect of acceleration that will allow probing of the circular Unruh effect. And that is the goal of this. And the reason why it's 2 plus 1 is because the surface fluctuations of a Bose-Einstein condensate behave just like a scalar field that would be linearly coupled to this beam, linearly coupled to the detector. And so that's the reason for doing the calculation in 2 plus 1. But you can do whatever dimension you want, of course. And so the hope is that this photodetector will see it. So what we did in our paper is we said, well, let's just use this same setup to test detector superposition. Why not? So the idea would be to have a laser that would come in, and you would then put it in a beam splitter that gives you this reference beam that you need to see what's going on. And then you have a second beam splitter where this is the detector superposition separated by delta. And so then these go through the BEC, and then they recombine into 2 beams, E minus and E plus, given by this, where these are the electric fields. And then E plus is detected relative to this reference, and the response that I wrote down earlier, omega delta, here I've put in delta, it's actually omega delta divided by the speed, what would be the speed of light in vacuum, but it's the speed of sound in the BEC, which gives a huge advantage because the speed of sound is many orders of magnitude smaller than the speed of light, so it amplifies the effect because you're dividing by that number. And so doing a fair amount of arithmetic of the same type that you do to see the Unruh effect that I mentioned on the previous slide, you end up getting this kind of function that experimentalists actually measure that I've written down here, and I'll put it up on the next slide. It's called the difference photocurrent power spectral density, or PSD. And so this delta is the heterodyne shift frequency that's much less than omega. I should have called it an omega, I guess. N is the noise, which is given by this function that depends on mu that I'll talk about in a moment. The sound speed I mentioned is C of S. It depends on the S-wave scattering length of the BEC, the atomic mass of the BEC, and the number density in the BEC. Mu is the effective coupling of the field to the detector. It's like the lambda that I put on the several slides earlier, and it depends on all of these quantities: the atomic polarizability, the atomic resonance frequency, the coherent amplitude modulation band, and these other quantities, m and rho naught, that are there on the left. So you can take this noise. It turns out this is the same noise function for the UDW detector. You can optimize this over mu, and in fact you can put in squeezing that improves the optimization, and what we find is that the ratio of f to n, the signal to noise ratio, can be bigger than 10, because you get this 1/6 root 10 minus 2 thing in the denominator due to the optimization. So I'm told I'm almost out of time, so that's really what I wanted to say. I think this is perhaps the most basic test of RQI that one could carry out that is not trivial. It does tell us something about what detectors do. And we might say, well, Rob, we superpose all the time. Well, that's true, but we haven't superposed UDW detectors. We do not yet have any direct tests of the formalism. This would be one such thing. It has a very promising signal-to-noise ratio. If this works, then there's all kinds of things that we could do. This will provide jobs for a generation. I'm trying to help you in my remaining years. So I put them here. You could think of more, but I've got to stop here. Thanks.
All right, Rob, thank you for the talk. Does anyone have any questions? All right, Rick?
Thank you so much for the talk, Rob. I think that it's really the right time for us to be thinking of how to implement this in experiments, and I think that the BECs and things like this are really a very good platform exactly because of the ratio of the speed of light and speed of sound, right? So let me first advertise a work that I have in this direction in collaboration with Markus Oberthaler in Heidelberg, really trying to use impurities in the BEC as the probes, so they're really localized atoms that we can basically control and measure afterwards rather than photons. This basically allows us to go to 3+1 with less hassle in the sense, because if you have the photon interacting 3+1, then it would really see the whole BEC in the direction it's seeing. But it's okay, so advertised.
Great, another paper by Monday. Good.
But the paper is out in the archive. I can definitely send you later. But and the numbers are also promising. But what happens there when we did this is that effectively what behaves like a quantum field is the density of the BEC, as you said, but it doesn't behave like a scalar quantum field. It behaves like the momentum of a scalar quantum field, for all intents and purposes. Mm-hmm. And the calculations you showed for the rates in 2+1 were using the scalar field phi rather than the momentum.
Rather than pi.
Yeah. So is there any big difference between these two cases? Have you looked at the pi
we
case?
didn't try it, so I don't know. I expect... I mean, generally what pi does is gives you derivatives of Whiteman's, so I think the structural form of the response will change. But I don't think that'd be worth doing, yeah. As I say, let's try it.
I would expect it to get a factor of omega squared because of the different units
they'll
and
be,
things like that.
Right, I mean, yeah, something like that will happen. That's right.
No, okay, good, thank you.
All right, we have time for another quick question.
Yeah. So you said you are using a constant switching function, and as I can say as the experiment, the switching the coupling parameter is fixed. So can I see the final state again? Maybe I missed it.
So you want to see the final state? You said?
Yeah.
Well, I don't know. Boy, that's other stuff that I have later. I mean, the final state, let me go back here, the final state density matrix would be that, except PD would be given by this thing here.
Yeah. So, so we have a double integral here, and if you use a constant switching function, Then when the time is very large, then it will diverge. So if you
you're right. Effectively, we cut it off, right? So I mean, in the actual experiment, it's not on. The interaction only happens while it goes through the BEC.
Yeah, but
so you're right. Technically, we've cut it off. I glossed over that.
In your presentation, the theoretical calculation is finite. Maybe somewhere after this slide. When you are calculating P, yeah, this slide maybe.
Yeah, well, it's effectively there is a cutoff. Sorry, I glossed over that.
Can I add something to this? Just because so if you take this infinite time limit, like of course the probabilities would increase in that principle.
Yeah.
So perturbation theory is not valid. But the whole idea of using the de-excitation rate is that you're saying that in this long time limit, well, your detector is always going to end the ground state because it will
the rate will not diverge.
No, but the whole point is that this tells you how fast the detector wants to decay. So this is not really within perturbation theory in the standard way, but if you do some Lindblad equations and master equation stuff, you can see that basically this F is giving you how fast the detector wants to decay. But the final state technically is just ground state in this approximation because the detector will have decayed in infinite time.
Yeah.
Because the excitation rate is finite.
Okay, I see. Yeah. Thank you.
All right, thanks for the questions, and let's all thank Rob again. Let me know whenever that's ready.
She's not screen sharing. Did you get the microphone?
Oh. Can you take it off?
We can't hear her.
No, we can't hear her. Hey, sorry, we can't hear you just yet. I'm taking care of the audio.
That's correct. The Zoom.
Yep, and we can hear you. Perfect. Thank you
Okay.
so much. Floor is yours.
Okay, so hello everyone. My name is Jiayue Yang, and I'm a second-year PhD student from IQC University of Waterloo and the Perimeter Institute. And my supervisor is Professor Robert Mann. Today, I'll talk about our recent work on relativistic quantum information means holography, collaborating with Dr. Liu Man, Professor Zhang, and Professor Mann. So this is today's outline. First, I will provide you with some background information, a very brief introduction to relativistic quantum information, or RQI in short, and then I will talk about the methodology, including the unruled weight detector model and the detector field interaction. Next, I will talk about our recent progress, including the magic resource harvesting in anti-de Sitter spacetime and also in safeties. Finally, a summary. So now let's begin with the background information. So as we know, the modern physics is built on three major subjects, including the quantum mechanics, which describes the microscopic and the probabilistic physics, and also Einstein's general relativity, which describes macroscopic large-scale physics, or summarized in one sentence by Wiener, the matter tells spacetime how to curve, and the spacetime tells matter how to move. And also, we have the information theory. It's about the quantification of information. It's about quantum communication, and so on. And our interest just lies at the intersection of quantum information and gravity. And in recent decades, a very new and vibrant subfield called relativistic quantum information, or RQI in short, has just emerged at the intersection. So you may ask, why do we care about the relativistic quantum information? So as we know, the quantum information theory has deepened our understanding of entanglement, quantum correlation, quantum communication, quantum computing, and so on. However, most applications assume a flat spacetime, whereas in reality, we live in a curved spacetime shaped by gravity. Sometimes when the gravitational effects or the relativistic effects cannot be simply ignored. And so we have the relativistic quantum information. It is a subject that answering how the gravitational or relativistic effects affect the quantum information quantities or quantum information particles. For example, it studies how quantum information tasks can be done when spacetime is curved or when the atoms are non-inertial, for example, when they are accelerating. And now let's talk about the methodology. So first, let's think about a simple question. Can you get something from nothing? By saying nothing, I mean the vacuum or the empty space. So can you really get something from the vacuum? So the answer is yes. And in 1990s, the Valentini and followed by Resnick, Reisner, and Seelman, they showed that the vacuum is not really empty space, but you can extract some quantum correlations or entanglement from the vacuum of a quantum field by using the localized quantum mechanical system. We call it detectors. And so the protocol is like this. So you start with two initially unentangled detector. Let's call it detector A and detector B. And you let the detectors locally interact with the quantum fields. And after some detector field interaction, you'll find that the two detectors can be entangled with each other. So we say we have extracted some quantum correlation, some entanglement from the vacuum state of the quantum field after this process. And there are lots of examples, and there are lots of examples for the entanglement harvesting, and this has been done for various scenarios, including the entanglement harvesting in three-dimensional de Sitter spacetime, and also four-dimensional de Sitter spacetime, and also recently in CFTs. And now let's talk about how to model these detectors and also the detector field interactions. In the following, we will consider a Q-trait, which is a three-level quantum mechanical system. So we have three levels, K0, K1, and K2, and they have these three Hamiltonian, which has the energy eigenvalues, where the omega-1 is the first energy gap and omega-2 is the second energy gap here. And we can use the so-called monopole operator to describe the state transitions of these Q-trait detectors. So this describes you can go from K0 to K1, and also you can go from K1 to K2, and you can also jump down. So this is the model that we describe the localized quantum detectors. And also we use this interaction Hamiltonian to describe the detector field interaction, where lambda here is a coupling strength, and chi here is a switching function. Mu here is just the monopole operator describing the internal structure of the detectors, and phi here is a quantum field evaluated along the detector word line x of tau. And let's consider the simplest case. So we have a detector in the ground state, and also we have the quantum field is in its vacuum state. And we can construct this evolution operator, which is determined by the interaction Hamiltonian, which we introduced before. And also we can get the Philo state. So we can trace out the degrees of freedom of the quantum field to get the reduced density matrix of the detector's Philo state. It looks like this. And using perturbation theory, you can find that the detector's Philo state reduced density matrix is given by this, where Q here is the excitation probability to the first excited state, and Y minus Q is the probability of it remaining in the ground state. And beta here encodes the coherence between K0 and K2. And you can find the excitation probability Q and the coherence beta, which is given by these giant integrals determined by the switching function, the energy gap, and also the Whiteman function, which is a two-point function in the spacetime you are interested in. So now let's talk about our recent progress, magic harvesting in any de Sitter spacetime and in CFTs. So, first question, what is magic? So it is not like the magic trick that you pull a rabbit out of a hat. It's really something that related to quantum computations. So now let's think a very simple example. So if you have a bare state, you may think of it as a highly non-classical state because it's maximally entangled for these two qubits. But actually it can be described in a formalism that called the stabilizer formalism, which means that you can use some stabilizer generators here, for example, x1, x2, and z1, z2 here to stabilize this state. So they will leave this state become invariant. So here x and z is just the Pauli operators. So actually we can use these stabilizer generators to describe the state instead of describe the amplitudes of this two qubit system. And another interesting is that if you have a very large n, I mean you have a lot of qubits, then if they can be stabilized by some stabilizer generator, then you can just use these stabilizer generators to describe or simulate this state in the order like n squared. But if you want to just use this state to describe the quantum state, you will need like exponentially large in n, like 2 to the n. So this from this case, we can say that this stabilizer formalism can help us to simulate the state very efficiently. So the key takeaway here is that although entanglement is highly non-classical, is very important, but actually it is still classically, it can be still classically simulated very efficiently, or you can construct simulate this Bell state in a Clifford circuits. And all of this can be described by the so-called stabilizer formalism. And what if you want to go outside of the stabilizer formalism and to do some universal quantum computations? So what's the missing resource you need? So actually you will need this kind of resource called the non-stabilizer list to let you go beyond this stabilizer formalism. And this is also called the magic resource. So this is just a summary of what we learned from the example. So there are some kind of circuits that can be described by the stabilizer formalism that can be efficiently simulated on a classical computer. And the magic resource is the resource that let you go beyond this stabilizer formalism and will let you do the universal quantum computation. So this is the resource that we are interested in. It is some resource that is very essential for the quantum computation complement to the resource entanglement. And there are a lot of measures to quantify the magic resource. And in the following, we will adopt mana, which is a very important measure to quantify the magic resource. And it is just given by the Q and beta, the transition probability and the occurrence of the detector, of the detector's reduced density matrix that we seen before. And 2 years ago in 2024, this group, Nilstra, Prazzini, and Kiski, they showed that the magical resource can also be harvested.
Just letting you know you have 5 minutes till your question period.
Okay. Yeah, thank you. And so they show that if you are started with initial non-magic state, and after this interaction, you can your detector can become a magical state. So this is a protocol they have did in the 4-dimensional Minkowski spacetime. And recently we have shown that this can also be done in ADS and CFTs. And so let's consider this d+1 dimensional anti-de Sitter spacetime with these coordinates. And if we consider a static detector, the trajectory can be parameterized by its proper time. And this is the Whiteman function for the anti-de Sitter spacetime, where d is the spatial dimension, gamma is the gamma function, and epsilon is a regulator. And although previous studies have largely based on the numerical integration to get the density matrix of the detectors. But we find that actually we can get the analytic results for the transition and occurrence for the density matrix of the detectors. So we have obtained the analytical results for Q and also beta, and you will see that they exhibit very similar structures, and they exhibit very similar structures, and also you can find that if you take the large L limit, you can recover the Minkowski result in D+1 dimensional, and also if you take D to 3, you can get the results in this paper. And here we show the magic versus the energy gap. So you will see that there exists optimal energy gap for this magic harvesting. And also if you decrease your ADS radius or make your curvature stronger, this stronger curvature will suppress the magic that you can harvest from the vacuum state of the quantum field. So this is the curvature dependence. And also, we also find the dimensionality dependence. So if you increase your dimensionality, this will also suppress the magic you can get from the vacuum state. And also, since you are interested in holography, so we consider this holographic setup. So your bulk line element can be related to the boundary element through the while rescaling. And in the ADS safety dictionary, you have the field operator correspondence. So if you have a bulk scalar operator with the effective mass, it can be related to the safety primary operator with the scaling dimension delta, and you can get the two solutions of this equation. And this is called this one has the larger scaling dimension. It's called the standard quantization, and this one, the delta minus, has a smaller scaling dimension. And also, you will find that we can also obtain the analytical results of the transition and the occurrence for the D+1 dimensional safeties. So it's also exhibit a very similar structure to the ADS case. And also you can plot the magic versus the energy gap. So we can still see very similar structures, and also for the larger scaling dimension, you will get a smaller magic. So the larger scaling dimension of the safety parameter will suppress the magic that you can harvest. So in summary, we obtain the analytical results of the detectors reduce the density matrix for both ADS and safeties. And also we show that magic harvesting can be done in these setups. And for stronger curvature, higher dimensionals, and also larger scaling dimension of the safety, the optimum value will move leftward, and also the magic will be suppressed. And there are a lot of things to do in the future. For example, consider other spacetimes like BTZ and so on, and also other detector models. For example, circular motion of detectors, and also we can consider what if can we extract some other kind of quantum resources, for example, stabilizer ring entropy or contextuality in curved spacetime and in CFTs, so and more. So thank you for your listening. That's all.
All right, thank you for the talk. We have some time for questions, if anyone's got questions. Sure.
Hi, this is Rick. I was wondering always about these studies about magic and contextuality harvesting from the vacuum. Because in entanglement, there's a very clear notion that like if we have space like separated, for instance, detectors, they don't communicate, and then if they end up entangled, we understand this entanglement must have been extracted from the vacuum, right? You know, in a sense, like the vacuum would have lost a little bit of this resource. So is there any notion of a conservation of like, up to which extent are you extracting this magic from the vacuum? Like, is there a good argument for this, just like there is an entanglement, or is it still something that is under study?
Yeah, thank you for your question. So, from my opinion, this magic resource maybe induced from like our interaction from the detector and the field, because we impose these kind of interactions. So that's why we can get the magic resource from the vacuum state of the quantum field. So maybe there are some kind of conservation in this context, but we haven't studied it yet. But I think that's a very good future direction to explore.
Thank you.
Thanks.
Any other questions? All right, if we don't have any further questions, let's thank Jiayue again.
Thanks.
Eirini, if you're there and want to. Yes, we can. All right, so for our next talk, we'll have Eirini Telali giving a talk on entanglement via classical mediators and the Wheeler-Feynman absorber theory. Eirini, it's all yours.
Thank you very much. First, I want to thank the organizers for accommodating the online talks, because otherwise I would not be able to talk here, so thank you. To introduce myself, my name is Eirini Telali. I am supervised by Eduardo Martín-Martínez and Laurent Friedel in University of Waterloo and Perimeter Institute. And today the main question I'm going to address is it possible to observe quantum effects without quantum mediators? And I will try to make the connection to some older theory formalized by Wheeler and Feynman called the absorber theory. I have eliminated as much of the mathematical details, so if there is any question throughout the talk, please interrupt me. So what I'm going to talk about is based on work from Eduardo, Rick, and myself. And I will start by explaining a bit what field-mediated entanglement is for those that are not familiar with it. Our motivation came specifically from gravity-induced entanglement experiments that were proposed recently as tests for quantum gravity. So let me explain the idea. The idea is that one has two masses, put them in superposition of trajectories, and let them interact via the gravitational field, and then recombine them. So the idea is, if in the beginning the state of the two masses is uncorrelated and not entangled, but in the end it is entangled, then there must be a quantum effect happening because of gravity. Thus, gravity is quantum. And the theoretical argument proposed by Marletto and Vedral goes like this. If one has two systems, A, B, for here that would be the two masses, MA and MB, interacting via a mediator that I call C, for the experiments that would be the gravitational field, and assume local interactions, and that in the end of the process, A and B are entangled, then one can theoretically prove that C has to be quantum. And the argument is quantum informational and does not involve anything else. But there is a question that one can ask: what if there is no mediator in the description to begin with, thus violating the locality of the interaction? Can one prescribe a coupling between A and B that is direct and relativistically local? Or to think in reverse, is it possible to omit the mediator in some description? And when can one do that? So for the next part of my talk, I'm going to talk about interactions without mediators. There is two parts. The one is the model that Eduardo and Rick formalized some years ago, called the quantum control model. And the second part is going to include the Wheeler-Feynman absorber theory. So let me start with the quantum controlled model. So that, again, as I said before, that was worked out by Rick and Eduardo, and later I worked on it with them on its causality issues. And so let me explain the formalism. How can one prescribe a direct and relativistic coupling between two quantum systems? One way to do this is to go on shell of the equations of motion of some mediating field. So assume I were to describe this in a classical way, and I have a classical field phi, and then what one does is solve for the equations of motion, thus propagate the sources A and B by the retarded propagation of the field. By plugging that in back to the axiom, one gets an interaction term in the Lagrangian of the system that prescribes a direct coupling between A and B mediated by the retarded propagation between A and B, and the retarded propagation is determined by the equation of motion of the field. Thus, by one extra step one has to take is to omit self-interaction. So A is not allowed to interact with itself, and so is B. Thus, the action, in the previous slide, the action only depends on systems A and B and not on the field. And by also assuming slow time variations, it can be formalized in its Hamiltonian form, again, only depending on A and B. Then to go to the quantum version of the quantum controlled model, one quantizes only the sources, and thus the field perceived by A and B is a quantum field, but the Hilbert space only is determined by the sources A and B. Thus, one can write the Hamiltonian as a quantum operator depending on the sources A and B. And the interaction Hamiltonian, again, describes a direct interaction between the sources. And then one should ask the question, now that we have a model for this interaction, can we actually describe the entanglement that would happen in the scenario I described above? Spoiler, the answer is yes, but within certain regimes. So one way to compare is to compare with a fully quantum field theoretic model that would be with a mediating field that here I write as C, but below I denote as phi. So for the quantum field theoretical model, that is C is quantum. For the QC, C does not exist. We have this direct coupling between the two. And we have the two prescriptions for the interaction. In the first case, we have a local interaction between phi, the mediating field, and the sources. And in the second one, we have a direct coupling. Then one prescribes the evolution operator that is determined by each one of the interaction Hamiltonians and evolves the states, and then asks the question, how well do they match and when do they match? So in the first case, the final state of the systems A, B that we observe is the time evolution of the initial state of the total system, that would be A, B, and C, traced by tracing the field, of course. But for the quantum controlled model, one does not need to trace out anything, just evolve the state. And then we ask again the question that we asked in the beginning, is there any regime where the one approximates the other? And as such, the entanglement of the quantum control state approximates the entanglement of the state by the...
Which one is it?
Sorry, is anyone asking a question?
Yeah, sorry, Eirini. If you can back up, the computer over here crashed. So we lost you when you coupled the Green's function to the quantum fields.
Oh, wow. So...
Yes, so right about here. Yes, we lost you right about here. And don't worry, that's not going to eat into your time. So you'll be all right. I'll let you know when you have 5 minutes. Sorry about that.
No, I hope people can still bear with me. So did you hear the quantization part or no?
Yes, we did. This is like right here is where we crashed.
Oh, cool. Okay, then that would be not that hard to say again. So as I said before, and you don't know it, the question that we want to ask is, can this model, the quantum control model that prescribe an interaction that can explain entanglement? And the answer is yes, but within certain regimes. I'm not going to go deep into what regimes that works in this talk because I want to focus on the Wheeler-Feynman theory, but I will briefly tell you later. So the idea, in order to see if the quantum controlled model can predict the same entanglement that one would have with the quantum field theoretical model, we write down the interaction Hamiltonian in its case. For the quantum field theoretical model, we have A and B interacting with a field that I call C here, but phi here, and they couple directly. And in the quantum controlled model, they couple locally, the field with A and the field with B. But in the quantum control, they couple directly. Then one prescribes the evolution operator in the interaction picture, evolves the states as here inside and Reis and here, and computes the final state of A and B. That would be by tracing out the field in the quantum field case and by doing nothing in the quantum control case. And then after we have the final states, we can ask ourselves, does the quantum control approximate the quantum field theoretical? And as such, does the entanglement of the quantum controlled the state approximate the entanglement that one would get with the quantum field theoretical model? And the answer is yes, but for sufficiently large times of interaction. So I have another 10 minutes, is that correct?
Yeah, you still have 10 minutes. Yeah, you're good.
Okay. So I will go through these slides very briefly. I want to show how the quantum control approximates the QFT with respect to two-point functions of the quantum theory. So in the quantum theory, we have the Whiteman two-point function and the time-ordered two-point function that is the Feynman propagator. And if one decomposes these two into the real and their imaginary part, one has the Hadamard part as the real part of both, and that depends on the state of that we take the expectation value, with respect to which we take the expectation value, and the imaginary part. For the Whiteman function, the imaginary part is the commutator of the quantum field, and for the Feynman propagator, it is the symmetric propagation of the field. That would be the retarded plus advanced. There is a typo here, I'm sorry for that. And then one can show that the quantum control case approximates the quantum field theoretical when one can neglect the commutator and the state-dependent part that we call the quantum parts of the two-point functions. So in the quantum field case, the final state depends on all parts of the two-point functions, or on all the components, while in the quantum control, it only depends on the symmetric propagator. And I want you to keep this in mind because it's going to show up in Wheeler-Feynman as well. Again, I repeat myself, we need large times of interaction to make this approximation that we can neglect E and H. So now I go to the second part of my second part, that is the Wheeler-Feynman absorber theory. So not a lot of math in this part. So let's go back to history a bit. So Feynman, when he wrote down his thesis in 1942, he had the following question. When can I omit a mediating system that mediates the interaction between two systems A and B, that would be C here, and prescribe an action at a distance with quotes, because it's with the oscillators that we're going to talk about, it's not a relativistic distance per se. And he asked this classically and quantumly. In the classical case, he asked it in the context of least action principle. So he asked the question: can I write down a least action an action for A and B that has the same least action principle as my original system? And the answer he found out for oscillators was yes. And what was the answer? It was yes, but only for boundary conditions that are specified, that are of the form x at some time 0 and t. So I would have to specify position only or momenta only between 2 times, but I cannot have Cauchy data. I cannot have position and momenta at the same time. Then he asked the same question quantum mechanically, asking, is there a way for the expectation value of some functional that I write as hashtag here, given some conditions, this is a delta function of the conditions on x0 and xt, be proportional to the expectation value in this calculated with the action without the mediator. And the answer was again yes, for the same boundary conditions that I described before. Going on with the same idea of when can I omit the mediator, Wheeler and Feynman wanted to describe a theory of electrons that is described by a direct relativistic coupling, i.e. an action at a distance, that and the motivation was to describe the movement of the electrons without self-interactions. But we're going to see this in a different perspective here, because we want to draw the line between this and the quantum control models. So the idea is that there is no field mediating, there is only propagation of degrees of freedom of the sources between sources. All sources radiate to all sources, and there is no radiation going outside of the union of all sources. And that is modeled by something called the absorber. So you can imagine that I have A and B and B1, B2, they all exchange photons, let's say, or they exchange radiation. And I can model the fact that there is no radiation going to nowhere by having an absorber that guarantees that radiation is going to be absorbed. So they made the following assumptions to formulate the theory. The one is that one electron on its own does not radiate. The second is that there is no self-interactions. The third is that propagation happens with a symmetric propagator. So it goes back and forth in time, which is kind of puzzling, and one could very easily ask the question, is this not violating causality? But as Wheeler and Feynman show, it doesn't, given that all the assumptions are satisfied. So the field that one electron is going to perceive is given by all the radiation it receives from all the sources. And with this description, one can write the action of all sources, and that would be the free action plus all the direct couplings between sources I and J for all I and J. And the last assumption is that all emitted radiation is absorbed. What they found is that they can describe the movements of the electrons, very well, and replicate all the expected behavior, and also that there is no causality violations within this model or within this theory. Now, as I hope some of you notice, if not, it's okay, I will tell you. These equations are very reminiscent of the quantum control model. In fact, one can write from scratch the quantum control model, predicting the same results in this formulation exactly. Of course, this is classical, so then you quantize the sources, you have the quantum version, but you can start from the Wheeler-Feynman description exactly. So very briefly, I want to compare the Wheeler-Feynman to the quantum controlled case. And in both cases, we assume that the one system on its own does nothing. There is no self-interaction. As I said before, we can describe this in the we can describe the quantum control case in this formalism as well. And the last one is a bit trickier, but it translates to the antisymmetric propagator or the commutator vanishing. So the retarded minus advanced is found to be 0 in the Wheeler-Feynman theory if one assumes that radiation is not leaking out of the system. And for the quantum control case, that corresponds to having a commutator between the fields being 0. So not having a contribution from the antisymmetric propagator. And as far as the results are concerned, they both depend on the symmetric propagator. So for the Wheeler-Feynman, the dynamics is described by the symmetric propagator of the classical field. And for the quantum controlled model, the final state depends on the symmetric propagator only. So let me summarize what we have seen today. We asked the question, can we construct a model that predicts entanglement and assumes no mediating field, not quantum mediating field, i.e. no local degrees of freedom for a field? And the answer was yes, under certain conditions. But the fact that one can describe this even with a model and not with a complete theory creates the question of when I observe entanglement or I observe any signature of quantumness, where does this come from? Does it come from the mediating field or does it come from the sources? And that is kind of related. I think it's an important question for experiments or processes in general that observe quantum effects, so that we can allocate where these quantum effects in some sense come from. The third thing that we saw is that conceptually quantum controlled fields are reminiscent and similar to Wheeler-Feynman observer theory. And that leads to the question, is there more formal way to ask the question, when can we omit the mediator? And maybe answer Feynman's question, but in the quantum case, not in the classical case, since Feynman and Wheeler only talked about classical fields, had the aspiration to go to quantum, but never did. So this is our work in progress, and I hope we have news for you very soon. Thank you very much.
All right, thanks, Eirini. We have some time for questions, if anyone has any questions. All right, if not, then let's thank Eirini again. We're gonna go to
the pointer. Okay. Oh, I can't plug it in, fortunately. No adapter, right? Perfect.
Also, your movement is bounded.
Oof.
By these lines on the board here. So basically, don't go past that chair. And here you're kind of, yeah, you I guess can kind of pace in between the desk and this chair over here.
I'll try my best. That's not working, looks like. No. No, not yet. Okay. Something with the screen out of bounds.
It's the aspect ratio. We can fix it, but it's going to take 5 minutes. So
I cannot give the talk with this, so it's gonna miss half of the content, 1/4. Okay, that's good enough. Thank you. Thank you so much. That was 5 minutes in some reference frames. Okay. All right. Start now.
Yep. All right. So I will now introduce our second plenary talk of the day, Eduardo Martín-Martínez, who's going to be talking to us about no black holes from light.
All right. Thank you very much. So I thought I would give a talk about this relatively old work, but like 2 years ago, a year and a half. But also it's been recently revisited by a recent paper by Don Page. So I think it's most relevant to talk about what's new and what changed and what we know about it. First of all, let me say this is a work that I did in collaboration with my former student, Jose Polo Gomez. Some of you may know, Adolfo here. And then with Álvarez Domínguez and Luis Garay, both at the University Complutense of Madrid. And again, yeah, I will also talk about a more recent paper that Don Page put out related to this topic. So hopefully I try to make it entertaining, and let's see if we can make it fit in the 30 minutes well. Let me talk a little bit about what are Kugelblitze, right? The idea here is that it is known that a massless field can a priori form gravitational structures. So light gravitates, and in principle, you can wonder whether light can confine itself due to gravity. Can we have those structures? So that question was first visited by Wheeler, and the idea here was like, well, in principle, yes, and those are what we call geons. I forget, geons is an anagram for gravitationally, this is embarrassing, but it's an anagram for electromagnetic radiation contained by gravity. Oh, it's actually here, gravitational electromagnetic entity. Very nice. So the idea here is that, well, they were studied and they were proved to be unstable under perturbation. So if you get a geon, so a gravitationally bounded electromagnetic entity, if you perturb it, that's not going to be stable. Either they leak away or they collapse into a black hole, okay? When they collapse into a black hole, this is what is known as Kugelblitz. A Kugelblitz is a black hole, not to be confused with other notions of Kugelblitz in atmospheric physics. In gravitational physics, a Kugelblitz is a black hole made out of the collapse of electromagnetic radiation. Make sense? Anyway, this has been studied in many different fields for a long time. They play a role in quantum gravity. They play a role in sci-fi. This is a very entertaining paper if you want to read a little bit of sci-fi that is archive compatible, sci-fi with some equations. And well, it may be interested to see if those things that are allowed by general relativity can survive when we switch on quantum effects. So where does this come from? Let me tell you a little bit of the story, the fun part of the story of this project. So this goes back to, remember when Rob Mann told you about a paper 14 years ago? This goes back not 14 years ago, but about 10 or so. I was maybe 11 or so. I was a postdoc here. I had recently arrived. And there were discussions, there were very interesting discussions, right, with people like Thomas Genevine and other people at the IQC about, well, we are becoming really good at very powerful lasers that can generate pulses that are very intense in very, very short spatial domains. What are cool things that can be done with those? And one of the things that were mentioned in the discussions were, oh, maybe we can generate black hole, haha, that's sci-fi, maybe in 40 years. What can we do in 40 years? And then my first thought when I heard that was that, yeah, I don't think that will work because, you know, the vacuum doesn't like to be polarized. If you try to concentrate light, you would hear many times that light doesn't interact with light. That's not true, as we know, right? Light doesn't interact with light at leading order in perturbation theory in quantum electrodynamics. Certainly, at even order 4, you get photon scattering. And if you go to non-perturbative effects, light interacts with itself. So one example is the Swinger effect. You have very strong electromagnetic fields, and they can polarize. Think of an electric field, the simplest case, and that can polarize the vacuum. In a way, you're going to see pairs of electron-positron being created that are going to be under the effect of the intense electromagnetic field. So the idea was like, well, probably this is not going to work. I don't think so. Earlier than having gravitational effects, you're going to get electromagnetic effects that are dissipative, interaction of light with itself. Light doesn't like to be concentrated. So I talked to many people about this throughout the years, and I showed them the calculation I'm going to show you now, which is the back of the envelope thing that I did. Well, a less refined version of that. But it wasn't until 2024 that Jose and I said, okay, why don't we talk with the Swinger effect experts? So the group in Madrid that we were talking about were actually people working in the Swinger effect. So let's see if this argument is sustained when you are careful about it, and then put it out in a paper and see what more knowledgeable people have to say about it, if people like it or not. So that's more or less what we did. Again, the Swinger effect is a prediction of quantum electrodynamics. It's often considered non-perturbative, but again, the line between the perturbative version, which is the Breit-Wheeler scattering, and the Swinger effect itself, it's blurry. So we're going to call all these phenomena Swinger effect under the all-encompassing name of Swinger effect. But the idea here is that, well, the vacuum is the electromagnetic vacuum, the electron vacuum, electron-positron vacuum is unstable under very intense electric fields. So if you increase the intensity of an electric field, you're going to start seeing pair creation, pairs of electron-positron. Now, it requires a huge field strength. That's what we call the Swinger limit. The Swinger limit is when this process is generally suppressed. Okay, it's not easy. In general, quantumly, you have this effect happening all the time. Perturbatively, you always get within electric fields, with some probability, you're going to see the emergence of an electron-positron pair, but it's strongly suppressed, very strongly suppressed, because it costs you mass. The electron-positron field is massive, so it costs you a ton of energy, and the probability is suppressed exponentially. But that stops being the case at this laser pointer. Okay, here. This stops being the case at around an electric field intensity of around 10 to the 18th volts per meter. So there is no longer exponential suppression, non-perturbative effects take over, and then you get this effect and suppressed. A ton of particles are created there. Okay, let me give you first the fun back of the envelope reason why I thought this may not work, but a refined version of it. Okay, so very basically, the energy density that you need for black hole formation, you can estimate by saying, well, just you have to put the energy to generate the black hole in some volume, and that volume is going to be small enough so that the whole thing fits into its Schwarzschild radius, more or less. So you get that at constant black hole mass, the energy density that you need to create a black hole, it scales like the inverse of the mass square. Okay? All right, but then you want one thing, okay, how does the Swinger effect work? Well, I don't know much about the Swinger effect particulars, but I remember that the rate of particle creation was proportional to the square of the electric field. And then, well, if you create a pair in an electric field of amplitude E, then the energy that each particle acquires is around that. Well, the energy would be, of course, the electric charge times the distance. Think of a capacitor, right? A constant. Think of a constant electric field times the distance times the amplitude of the field. But if you assume that the energy is going to be huge, so the electrons are going to quickly become ultra-relativistic, then it's basically the time it spends in the region with the region of strong electric fields is just the light crossing time, more or less, because the electrons are going to be ultra-relativistic. If you put it together, then you get that the dissipated power is going to go like this, right? Is basically the energy of each particle times the rate of particle creation, and then the energy dissipated, the energy density dissipator is going to go like that. Okay, so you divide by the extra dimension that you have. So the total electromagnetic energy is going to scale like this. Then you make the proper substitutions. If you put all the energy into generating a black hole, you find that the energy scales like the inverse. The energy density, dissipated, scales like the inverse of the mass. So you see different scalings. You would think, okay, so at some point these two will cross. At some point the Swinger effect is not going to let you concentrate enough energy to generate a black hole. So that's the back of the envelope idea. Make sense? Okay. So what we're going to analyze here is, are these Kugelblitz possible? And the idea here is, well, in principle, creating a Kugel-Blitz may involve electric fields of strength over the Swinger limit. And in principle, it's possible that the Swinger effect dissipates the creation of black holes, right? And then what are the regimes for that to work? Let me just advance to you that the dissipation due to Swinger effect we found is enough to prevent I should write here the concentration of energy to form a Kugel-Blitz with radius between 10 to the minus 33 and 10 to the 8 meters, so a huge range. And we'll discuss this range because it's not that outside, so we didn't conclude that outside of this range you can concentrate. Outside of these ranges, our approximations fail. So probably doesn't work way more than that. So it's not that, oh yeah, if you are above that, you can do it. No, not necessarily. It's just our approximations are not good enough to analyze the problem. Make sense so far? Okay, so let me give you the structure of the talk. So I'm going to propose a model for dissipation via Swinger effect, a simple model. I'm going to use it to analyze to what extent Kugel-Blitz can be formed or are stopped from forming by the Swinger effect. I will discuss maybe the simplifications made along the way. There are several simplifications, so it's really important to take some time and analyze every single simplification and see if they're reasonable and to what extent they apply, right? Well, this I may not do. I may do one of them only, which is the one that gives you that range. The others, I have slides here, but I may not have the time. So if there's time, I may discuss them, or if you have questions, I may discuss them. And then finally, which I really want, is discuss a recent clever argument in favor of Kugel-Blitz formation put out by Don Page. And we will discuss how this modifies, if at all, our results or not. Okay. All right, so let's consider a very simple model. The very simple model is, okay, let's use this model for the dynamical buildup of energy inside a spherical region given by the following differential equation. So you get here the time derivative of the energy density inside the spherical region. If you want the power density, dissipated in the spherical region, could be dissipated or not, could be increasing or decreasing. Then, of course, R is the radius of the region, and F is the constant influx of electromagnetic radiation. So the problem we're looking at is concentration of electromagnetic radiation. We have a constant influx coming in the area. And then we have dissipation due to scattering of particle-antiparticle pairs. There would be probably more dissipation than this, but let's just look at the dissipation that comes from the Swinger effect. Make sense? All right, so we need to estimate this dissipation rates from the Swinger effect. Now, the Swinger effect is non-perturbative, is non-Markovian, and if I wrote an ODE, the first thing that you can criticize is that we know the Swinger effect is non-Markovian. An ODE means, if you can write an ODE, that means that you're assuming Markovianity. Otherwise, you have some memory kernel in here. Well, the idea here is that the non-Markovianity, we know, comes from the back reaction of the produced pairs in the field. Like when you have pairs, those pairs emit electromagnetic radiation, they back react on the field and modify the Swinger effect. That's what makes it non-Markovian. So what happened before does influence what happens after. But the particles that leave the sphere, the region of concentration, are going to stop influencing pair creation. So what we can do is make a quasi-Markovian analysis where you have small cells of time, each of them computed non-Markovianly with the methods that people know how to compute, and then this succession being Markovian. So after the pairs created only influence non-Markovianly the process while they remain in the region of concentration. Once they leave, they don't. So you consider this differential equation to be the continuing limit of a lot of blocks of non-Markovian particle creation. All right. So the resetting happens after some average xt time, let's call it Tx, and the continuous process is discretized into a sequence of non-Markovian processes, typical duration Tx, and because Tx is much smaller than the amount of time that it takes to concentrate, the discrete evolution can be approximated by continuous one. That's an assumption we make. I have slides to discuss if you want, but I may not get to it, so better to understand it now. Okay, another thing that we're going to assume here is, okay, what happens in each of the non-Markovian blocks? Okay, now that's complicated. That again is a non-perturbative calculation. Luckily, there's a lot of all work done about in general in quantum mechanics about things that have this from. This is a Posel-Teller pulse. You may recognize the function if you faced it in your life. One of the main characteristics it has, well, it is adiabatic. Well, adiabatic here means that it decays to infinity fast enough. Okay. But it's also extremely well behaved under integrals of all kinds. We know how to integrate this. And that's the reason why in the Swinger effect, people who compute Swinger effect have used this pulse a lot. So we're going to use this pulse again. And once again, we can discuss how dependent on the form of the specific pulse the results that I'm going to talk about are. The message would be not at all, but again, I have to convince you. I may not have time to convince you, but that is at least my claim. It doesn't depend. So let's pick one that is nice. Anything that's not adiabatic is going to be worse, meaning more particles produced, more dissipation. And anything that is adiabatic will not depend much on the shape. Okay, that's the message. Okay. All right, so we estimate the particle production during every interval of duration tau x using the Postel-Teller pulse. And in the regimes of approximations, these two regimes of approximation, which we will discuss, that's the one that I will definitely discuss, the adiabatic regularization and renormalization of the stress energy tensor leads to this expression. This is a result from people who work in the Swinger effect. Okay, very nice. So, assuming a uniform electric field inside the sphere, so the idea here is that the electric field we consider to be spatially uniform as an approximation. That's another one of the assumptions we will have to visit, whether changing that would change things a lot or not. Well, then we have a dissipation rate, which is given by this. Very nice. We have an expression we can plug in into the differential equation that we had before. Now, if you look at this differential equation, maybe if at any point I teach differential ODEs, right, 251, in math 251 here, I will give them that. This is non-linear, so it's scary, woo, but I'm pretty sure there's a closed expression solution for this. It's going to be ugly and stuff, but nowadays, ugly and stuff shouldn't be an issue, right? We can process data very well. So I'm not going to solve it, though, because what is easy is to make the derivative 0 and then find the fixed point. That's what I want. Asymptotic, in fact, you can solve it numerically very easily. It's very, very well behaved numerically. And you can find out that indeed there is a fixed point, asymptotic fixed point, where you find that the dissipation rate equals, when things evolve, to the inflow, right? The inflow starts concentrating, the inflow wins, then you start getting dissipation. At some point, dissipation grows to the same amount as to be no changes in the concentrated energy, electric field amplitude in this case, in the region. So that happens at this value of the electric field. And the condition here to check is whether the electric field, the asymptotic limit of where the electric field would get, as high as we will get before dissipation stops him from being bigger, is larger or not than the electric field amplitude that it takes to collapse that energy into a black hole. As simple as that. Okay, you compare, you make the proper substitutions, which is very simple. So this is just the total energy, right? Oops. This is the total energy, which is the energy density times the volume. And then this is the energy that it takes to create a black hole, the energy concentration to create a black hole. And in the end, you end up with this expression, right? The energy to create a black hole goes like this with the potential over R. So it's given by this thing here. Now, you can evaluate what is the intensity that you need in order to make this guy be the same as what you need to create a black hole. And the intensity, this is the flow, right? The flow has to be larger than 10 to the 83 watts per meter divided by R, by the radius of the region that you want to concentrate. To compare with, for example, this is in 2021 at least, was the highest laser pulse intensity that one can theoretically generate these days. Not like in a lab, I mean theoretically. Okay, conceivably do it with a laser. Okay, what about the power? Well, the power gives this expression here, which is 10 to the 84 watts per meter times the radius of the region you want to concentrate. To compare, of course in meters, in international units here, to compare with 10 to the 41 watts, which is the power output of the brightest quasars. This is the most powerful thing that we know of, that we've ever seen. All right, so the claim here is that the Kugelblitzer concentrations are practically impossible. For reference, right, the Planck length is 10 to the minus 35 meters, and the radius of the observable universe is 10 to the 27 meters. Now, as long as all the approximations hold, within the scales that approximations hold, we say that we essentially rule out the possibility of formation of Kugelblitz because of the abysmal difference between the conditions that it requires and the conditions that we have available, both in astrophysics sources or thinkable in a lab. Okay, that's the idea. You will not be able to concentrate it What we're looking, and this is an important thing, we're looking at the concentration of the energy, okay? And we're saying that light doesn't like to be concentrated because quantum effects take over and dissipate the energy. Okay, now, the approximation that limits the regime is the strong field approximation. Remember the original claim? I told you that for R's between 10 to the minus 33 and 10 to the 8 meters, then we cannot concentrate light enough to reach the black hole limit. And I think it's very important to say, how am I doing time-wise? It's okay.
You still have like 15?
Perfect, perfect. So, okay, sounds good. So here's the thing. You would say, okay, but then outside of this limit, this is huge, but, you know, I mean, still thinkable that you can do that, no? I mean, you can consider a huge concentration of energy that is, you know, very, very little dense. Let's say that's the idea. That's why you don't have a strong swinger, right? If you're too large, you may think, oh, there's very little dense, no strong swinger, and then you collapse this thing past the Schwarzschild radius. Well, this doesn't mean that you can. What it means is that we haven't proven it that you can't. Once again, these limits are because our approximations or our assumptions fail, not because we find that the production is not high enough. Now, this doesn't apply, so two important caveats here. This doesn't apply to early universe physics at all. Okay, so if you have even thermal radiation on the radius of the universe, this doesn't apply. Okay, it's very outside the regimes of approximation we have. And of course, it doesn't apply to the Planck scale. So in the early universe, we say nothing about it. Okay, let's discuss the validity of these results. So the model is very simple. So arguably, you could say, come on, you did 1,000 approximations here. How true is this? So these are the ones that, well, I mean, all of them, to be honest, that I would love to discuss. But I'm going to definitely discuss in detail the 0 one, the strong field approximation, which is the one that gives you the bounds. Okay? But of course, you can say, okay, you assume a Minkowski background. That's not going to be true as you start concentrating energy. Before black holes, you're going to curve space-time. Does that make any effects? Second, we consider a uniform electric field inside the spherical region. In general, you will not have a uniform electric field, right? So what happens if the field is spatially non-uniform? Number 3, you're modeling dissipation as Markovian sequence of short non-Markovian processes. How good is that? And asterisk number 1, you chose a specific, oh, that was, yeah, that's very sad. Okay, well, it's not that bad because it's still a tau, so kind of. So consider a specific electric pulse profile to calculate the dissipation. So I did the Postel-Teller. Remember, Postel-Teller is nice in the sense that it's adiabatic. It's nice in the sense that you can find closed form expressions. But nothing special about it physically other than that, okay? So what about choosing something else that's not the Postel-Teller pulse? Would that modify things? And the third one is like, well, you're saying, this one may not need a lot of discussion, but maybe, I mean, I definitely have it here, which is you are assuming that the exiting time of the particles is the light crossing time of the region. So you're assuming the particles become ultra-relativistic. Is that true? I think that's the one that needs probably the least convincing because of the huge intensity of the electric field needed for that. You put a charge there, it's going to become ultra-relativistic almost instantly. But those are the things that we need to discuss, okay? So let's look at the strong field approximation. So the regime of approximation under which the dissipation rate was deduced, right, is this. These two things have to be true. Okay, so the first one is just a requirement that the electric field strength needs to be much larger than the swinger limit. Okay, this is when the non-perturbative effects that remove the exponential suppression are no longer there. Okay, well, the opposite, start to be there, start to be relevant. And the other one, well, the other one can be written as this. The idea here is it's putting you, okay, the other one sets, if you want, a limit on how strong the electric field has to be related to these quantum effects being able to be approximated in the way we do, okay? So both inequalities, you need to check that both inequalities are satisfied. Okay, I think this is dead already. Both inequalities need to be satisfied simultaneously, and in order knowing, right, that the field potential that you need in order to get to equal the black hole energy concentration with the dissipated energy is 10 to the 27 volts. Both inequalities are satisfied by this amplitude needed to generate the black hole in these regimes. And this is, again, what limits our result scales. Okay, these two approximations. Outside of that, we don't know what to say, but If you ask me with a gun pointed to my head, maybe a water gun even, if you ask me, maybe I'll just give it to you with no pressure necessary. So no interrogation techniques are necessary for this. I would tell you that if you extrapolate that some orders of magnitude, you're going to be still having the same issue. Only that you cannot use the calculations with it. Okay. All right, I'm going to skip past and may come back if there are questions, the different assumptions. Let me just tell you that in general, we looked at them and concluded that no, our assumptions are not going to modify, the assumptions breaking down are not going to modify the results. The Markovian approximation is not going to modify the results. And the electric field, I can tell you this, the pulse profile, maybe the pulsal teller is adiabatic, tails have a negligible impact on the estimated rate production. So any smooth peak pulse would get the same order of magnitude production. So let me tell you the difference between having the pulsal teller tails or any other tails, assuming adiabatic, okay? Adiabatic means you're going to have tails. Adiabatic in this case means there's only one scale and things die to infinity fast, right? So any other adiabatic pulse, you can prove that the tails have a negligible effect. Basically, it's a form factor of order 1-ish. As order 1 as the 2 pi square can be, so order 1-ish form factor. It's never going to be as radical. Adiabatic, they always have that times a factor. So anyway. So any smooth peak pulse would yield the same order of magnitude. That's the claim. It's not going to modify that. And then if the pulse is not adiabatic, people have studied what is the particle production with that non-adiabaticities make, and it actually increases the particle production. So we expect it to make it worse if it's not adiabatic. So the claim is that pulsal teller is nice, allows you to calculate, but it gives you a good estimation of what you're doing. Okay. The exit in time, I don't think that needs a lot of convincing. Let me give you the take-home messages, and then we go to the cool thing that Don Page put out. We had a long exchange, email exchange, and I want to publicly apologize because I haven't replied to the last emails that Don sent. But very, very nice work. Okay, so the take-home messages. The Kugelblitze with radius between 10 to the minus 29 meters and 10 to the 8 meters are practically, I should say, impossible due to the dissipation via Swinger effect. And then notice the claim, maybe too strong, because what I looked at, what I should claim is concentrating energy, electromagnetic energy like this should not be possible. Okay? We should probably not spend funds on trying to create microscopic black holes from light. Message number 2. You may laugh, but this was seriously considered. There's been in proposals, and they got funded. I've seen the proposals. Okay, but I think what is cool about this work, there are 2 things that I think are cool about this work. Number 1, this is something you could have done as an undergrad project, in the sense that, yeah, you need to know some things, but the references are really good for that. You need to work with some experts on Swinger effect, but it came out of dimensional analysis and estimation. So it's one of those cool things in physics that are not too difficult, and you can extract meaningful conclusions. And it's nice because it's showing something very important in RQI, because you can tell me, where's the I? Well, where's the I? In RQI, it's a combination of all of that. This work is underpinning the importance that you need to consider quantum effects in the context of strong gravity phenomena. Now, if you want to understand, for example, the formation of compact structures in general, this is with light, but imagine that you want to understand something, let me put the I in here. You want to understand the information loss problem. For the information loss problem, the mechanism, the black hole information loss problem, known in the past as, back in the day as the information paradox, if you want. You need to understand the mechanism of the formation of compact structures. And in the formation of compact structures, quantum effects are non-trivial, and how those quantum effects can send information out at the moment of collapse or not may play a role. So understanding these mechanisms is very important. So what I'll do, well, how much time do I have?
Like 5 minutes till your question period.
Cool. So what I'll do is, I'm going to let this sink if you want to ask me one question, so we can subtract that from the question period, and then I'll tell you about what Don Page did, which is pretty cool. Yes?
So, sure, if I get one laser that has this wattage of 10 to the 27 per meter squared, right?
Several lasers too.
Several lasers?
Yeah, you can have many lasers. It's about the concentration. I don't care how it comes in.
Sure, but if I get the strongest laser and then I add another one of the strongest laser, both of them pointing at the same thing, then I can double this intensity, right?
Yeah.
If I consider 10 lasers of the strongest kind, then I can multiply this by 10.
So what you're telling me is that we would need like 10 to the 50 something lasers, or with the highest possible power that we have available right now.
And perfectly collimated and time windowed.
Okay, but it's like, but in principle, if I were to build a structure that is solar-sized, that is huge, really massive, with 10 to the 50 lasers, all pointing at the center, then in principle, I would be able to.
Yes.
Then I agree with you. We shouldn't fund it.
So if you have a couple Dyson spheres and you use them to power those lasers, and you can time the lasers with almost quantum precision in time and space, then you probably can do it. Yeah. Also, you can do many other cool things if you have that technology.
Yeah, let's use this budget for something.
Right. Anyway, let's look at this other paper that Don Page put out. There's like black holes from light. He emailed us a lot before that, and Dom's been amazing. Don is usually amazing, so props to him if he sees this. So Don Page argues that our result does not fully exclude all possible ways in which light could form a black hole, at least theoretically. So it's true, our work studies the concentration and storage of electromagnetic energy in a finite region. In this regime, the Swinger pair production dissipates the energy. Page does not challenge that mechanism. He says, yeah, well, in fact, the end of my talk is going to be the conclusions in the Don Page paper. That's going to be my conclusion slide. I'm going to be just stealing them. He analyzes an arrangement of a null pulse collapse so that a trap surface is formed during a transient beam crossing event, being really clever. So what if you are a theoretical physicist allowed to very cleverly engineer everything to minimize? So you see, what we did is very different. It's like, let's pick a generic scenario and show that it's outrageous in this generic scenario, and then discuss that this generic scenario covers almost anything except for a zero measure set, kind of. Don Page is like, no. What about we go to one of those zero measure sets that are very cleverly engineered to bypass the limitation that you are putting? Okay, let's see it. All right, so step one, consider plane waves. So you have two pulses, but they're plane waves, perfect plane waves. What is the cool thing about plane waves? Well, for each pulse individually, you have no amplitude in the sense of, well, no energy amplitude production. There's no Swinger effect production for plane waves. You have plane wave, there's no Swinger effect. Notice, any perturbation outside of Swinger effect, if you have a huge amplitude electromagnetic wave that is a plane wave, you perturb it a little bit, it's going to huge dissipate in terms of particles. But as long as it's a plane wave, you're fine. Remember, plane waves have to live forever and live forever. No, it's the same. I'm using natural units. Live forever and exist everywhere. Okay, that's a plane wave. All right, cool. So as I say here, this realized on the plane wave idealization, right? But the idea here is that, well, we're going to store the energy into individually harmless null pulses. They're plane waves. They don't see any Swinger effect production. Cool. Now, keep the pulses separated. Now, this is actually key, because if the two plane waves actually overlap, you get Swinger effect. You need isolated plane waves for not having the Swinger effect. If they overlap, they would have Swinger effect. But the idea here is that, well, let's keep them separated. Again, what does it mean for a plane wave to be very separated? We can enter into that, right? But the idea is we separate it by a large distance in a way that they don't overlap with each other. Okay? And once again, any deviation can make the invariance north zero. And the moment you get the invariance north zero, you start producting. And the moment you start, the invariants are less non-zero, and then you product more, and it's a cascade. It's an unstable configuration to get this. Okay? All right, number 3. Now allow the pulses to collide. The idea here is that, well, when the pulses overlap, the fields superpose. But the engineering here is that, why don't we make them collide in the future? They're very far, and they collide in the future in a region that when they start colliding, they're basically already inside the Schwarzschild radius of what they would product. So the idea, get a massive Schwarzschild radius, separate the pulses, and sure, the moment they collide, particle production is going to be dissipating you. But maybe they can't escape anymore because you're already in the Schwarzschild radius area. Very clever, Don Page. Very nice. All right, cool. The overlap time must be short. Longer overlap because per production is related to this. All right, so form a black hole before the particles, with the mess they overlap. They create the black hole, mess starts to be produced, but then you say, oh, no, but you're already inside the Schwarzschild radius. Okay? Anyway, so any subsequent per-production occurs inside the trap surface that is being created. Okay? and then the plasma and radiation are trapped, cannot escape, cannot drain energy. That's the idea. So the recipe is plane waves, very far away, keep them very far away with a ton of energy each, let's not disturb them, so far away that when they get to overlap, they're already inside the spatial radius they would create. That's the idea. Okay. Now, very important is the plane wave idealization is not a generic, unlike the Poschel-Teller pulse that I told you that I claimed was generic, meaning that anything that's remotely physical may look like it. This is not the case. This is very engineered, not to have swinger effect. Make sense? So let me end the talk with the conclusions of the paper that Don Page wrote. Okay? Although I agree with the strong suggestions of us that the formation of black holes solely from electromagnetic radiation is impossible, either by concentrating light in a hypothetical laboratory setting or in naturally occurring astrophysical phenomena, this is a quote from us, if instead one allows purely theoretical situations within the known laws of physics, it is in principle possible to concentrate light enough light to precipitate the formation of an event horizon. The trick is what I explained to you, probably never actually occurring in a universe either, naturally or by human intervention, would be to concentrate the radiation in two plane pulses, each of which separately do not produce pairs, that do not overlap enough, whatever that means with plane waves, right, to give significant pair production before they have concentrated enough energy close enough to each other to form a black hole that would engulf any pair production. That occurs when the two pulses do eventually get close enough together to produce many pairs inside the black hole. Okay, so let's analyze, and then I'll leave it at that. What is our claim? What is this claim? How everything is modified. Our claim is if you try to concentrate energy, electromagnetic energy, so that it collapses into a black hole, generically it won't work. And generically, where generically has a lot of strength. Okay, generically, if you consider any situation in principle that you can do or you can think astrophysically, it's not going to work. Particle production is going to dissipate the energy. However, our claim never was, and this highlights it more, that it's physically impossible to do it. What we mean is practically impossible to do it. If you are allowed to just play with the laws of physics and create things like these plane waves, that are plane waves and perturbed, they don't overlap, once again, whatever that means, and there's a region where they overlap, and you engineer it so that when they overlap and start producing pairs, which again is not disputing the mechanism, he said it will happen the moment you concentrate the energy. But the idea is that since the plane waves allow you to kind of hide the concentration, it's like quantum electrodynamics is watching me concentrate energy and is about to get mad at it. But you say, okay, let's hide the energy in plane waves so the QED doesn't complain much about it, all of it, and when QED realizes it's already too late because we're already inside a horizon. So that's the trick that Don Page proposes and certainly works. So Google Blitzer, theoretically, nothing against them, practically impossible. And that's the message I want to end with. Thank you very much.
All right, we probably have time for one quick question for Eduardo before the coffee break. All right.
Do you think there are any other theoretical ways black holes can be made out of light? Other than this?
I don't know any, but I wouldn't discard it. Okay, yes, no, I do know some. So you can do this. You can have, it's a version of this if you want, right? You can have a concentration of energy that is not very dense, like as in radius of the universe, concentrated energy, and then make it enough energy. So you see, remember the back of the envelope scaling. There's going to be a scale in which you can do it without dissipation. You need just very little dense electromagnetic field so that the swinger effect never enters the non-exponential suppression area. If you go far enough, if you make your black hole large enough, you will find a way to do it. But what we have here is that with the radius of the universe, maybe what you need for this, like as in like the concentration level for that to happen has to be very large. But the idea, yeah, you can do it very, very low density and let it collapse. That is in principle possible. How much? I can't tell you because my calculations don't get that much. But I can tell you that it's going to be comparable to the radius of the current observable universe. In fact, I may even be able, but I haven't done it, to tell you that with the current radius is not enough. You may need a larger radius. But yeah, that's one. Thermal radiation, for example, that is very little dense, as in like the whole universe little dense. That may be possible. The idea, yeah?
Like the CMB.
not enough energy. So it has to be larger in temperature than the CMB. That I can tell you out of experimental check that wouldn't work. And because the universe is still expanding. Maybe it's actually dark energy that's making it not possible. But anyway, the point being that in principle, you could consider that theoretically large enough, very little dense so that it collapses. The trick is similar. The idea is that only concentrates to Swinger effect before when QED realizes too late. They're already below the horizon.
All right, let's thank Eduardo again, and then we'll have our coffee break.
Thank you.
live in camera.
You are
Okay,
live
it's
in camera.
Mayo and say Brazil. All right, everyone, welcome. So we're going to start the second half of the afternoon session, and go Brazil. Brazil's actually is here. So now we have Robin. Our next speaker is Robin Oberfrank. He's a PhD student, a resident at Perimeter Institute, and he's going to talk today about probing space-time fluctuations. So, all right, Robin, the stage is all yours. Can you hear me clearly?
I can hear you. Yes. Can you also hear me well?
Can you hear well? Yes? The sound all okay?
Yeah. Oh, can I start?
Yeah, go right ahead. Yeah. Okay, perfect. Yes. Thank you very much. Thank you very much for the opportunity to give a talk. I apologize, I cannot be there in person. What I would like to talk about today is a set of questions we started exploring with my advisor, Laurent Fredel, and there's also an upcoming work with Nia Shafshordi, Gero von Gersdorf, and Laurent. And the issue I would like to talk about today is about trying to understand the nature of quantum fluctuations of space-time. And what does it mean for space-time to have quantum fluctuations? But before going there, I would like to share a motivation. There's a quote I found a couple of years ago, and I keep coming back to it every now and then. It says, although there has been a lot of work in the last 15 years, I think it would be fair to say that we do not yet have a fully satisfactory and consistent quantum theory of gravity. So this was a quote from Stephen Hawking in 1975, or 50 years ago. And the reason why I keep coming back to this quote, because I still find it relevant today. And basically biggest problem that causes quantum gravity to go slowly is, I think, is the limited observational guidance. But that doesn't mean that there is a lack of observations. In fact, we know a lot of things about the universe. We know much more that we could have ever imagined before. So that's why I think that this is also largely a theoretical problem. And by that, I mean that a physical theory must give us a language to arrange the observations that we make about the universe. And in this sense, it is the theory that has to tell us what is it that we can observe, what is it that we can look for. So that is why I'm interested in the philosophy of phenomenology, which says that we are supposed to focus on phenomena as they appear to us, as well as how the theories make those phenomena appear, how the theory provides a language to describe those phenomena. So with space-time fluctuations, again, the problem with quantum gravity is that the scale of the theory is supposed to be set by the Planck scale, which is 10 to the minus 35 meters. So if space-time fluctuations are at this order, then obviously these are incredibly tiny, and it's almost impossible to resolve such small fluctuations. These are incredibly tiny. However, in ordinary physics, we know that if there are small fluctuations, it can also happen that those small fluctuations, we cannot resolve them microscopically, but macroscopically, there could still be some large-scale correlations. So one example for this is the Brownian motion. But let's say in a fluid, there are tiny particles that are scattering around. Those are very microscopic fluctuations, and we do not need to resolve them individually, but we still see a macroscopic effect, which is diffusion. So the question that I'm interested in asking is, does this happen? Does this Brownian accumulation effect happen for space-time fluctuations, in a sense that space-time fluctuations can still be very small Planckian, but over the course of observation with some time, with some scale in the theory, these small scale fluctuations could accumulate and be potentially observable in the infrared. So there's a way to make this question more precise. Let's try to set up a framework where we can ask similar questions. So consider two time-lag observers. Here on the right, I'm showing a space-time diagram, if you can see my cursor. These two time-lag observers, these are represented by vertical lines. And let's say one time-lag observer emits a light pulse, sends it to the other, and then it comes back. So this is basically a photon a null ray at 45-degree angle. So if geometry fluctuates, if there are space-time fluctuations, then the return time of this light pulse is also going to fluctuate. So the time of return tau goes to tau plus some delta tau, which is precisely due to the presence of fluctuations. Now this effect is already very well understood. This also happens in classical gravity. This is how we measure gravitational waves. But in the quantum case, you can push this much further. So imagine we repeat this experiment. We start sending multiple photons, photon 1, photon 2, photon 3. They each come back and we record their arrival time, the fluctuations, delta tau 1, delta tau 2, and delta tau 3. What we can compute in a quantum case is something called the noise spiral spectral density, which can be written in a form like this in our formalism. So what is important to emphasize is that this is basically some form of an interferometer. It is basically an interferometer experiment, except that laser interferometers, such as gravitational wave detectors, they measure isolated local events, gravitational wave that pass through the detector every now and then. In this case, for space-time fluctuations, what we have in mind is a stochastic stationary noise that is present in the interferometer. So again, what you compute in this formalism is the noise power spectral density, which basically decomposes into these three parts. The first part defines the frequency of the interferometer. It's identified with the zeroth component of the momentum. There's something called the interferometer response function. And then the third part is the most important. It is basically a metric noise kernel given some state rho. And this is a gauge invariant formalism. And furthermore, what I would like to emphasize is that in this formalism, we haven't assumed any dynamics for the metric variable. So this is just any generic perturbation. So it is in this sense that we can treat this as a model-independent framework. You can tell me what is the dynamics of those metric perturbations. You can have all sorts of ideas in mind. It can be some low energy effective limit of some different theory. You give me the dynamics, and then you give me the state rho, and then this formalism is going to give you the noise spiral spectral density, and then you can study the nature of those fluctuations, and you can compute all sorts of things. So in the paper below, we looked at a few baseline computations just to see to understand how this formalism works and how these computations work. So first we looked at the vacuum graviton fluctuations. So this was first computed by Daniel Carney in 2024, so just very recently. So gravitons are quantized gravitational radiation. You can think of it as just taking linearized Einstein's equations and transfer trace as gauge. The metric perturbations just solve the homogeneous wave equation. Then you can compute the graviton propagator, take it on the vacuum state, plug it into the formalism, and then you get the power spectral density. So in this case, it takes this form. So it scales with Planck length squared, and there's times L, which is the length of the interferometer, times a dimensionless function. So in this case, if you plug in the numbers, you're going to see that this spectrum is basically like 10 to the minus 39 meters per square root of hertz. That is the amplitude spectral density. So this is a number that you can compare with the noise that is currently being measured in LIGO, which is 10 to the minus 19 meters per square root of hertz. So this is obviously out of the question. This is incredibly small. This is a baseline computation. Nevertheless, you can fully evaluate everything in this model. For example, this function f of h, I'm showing this on the right-hand side. So here we are plotting the power spectral density divided by Planck length squared times L. This is a dimensionless number. We're plotting this against omega times L, which is the frequency of the interferometer multiplied by the length of the interferometer. So this function starts off at zero frequency. And that is the same statement that in this model, there is no Brownian accumulation. So the picture that I talked about earlier, that there could be microscopic spacetime fluctuations that accumulate over, in this case, the length of the interferometer. For the vacuum case, this does not happen. And that is why there is zero noise at zero frequency. After that, it starts increasing and there's a maximum. This is a maximum at the order when omega times the length is at the order of 1. So it basically says that interferometers with different lengths are going to have the maximum at different frequency scales. And then after that, the noise just starts decaying. So again, in this case, there is no Brownian motion intuition. These are very small fluctuations. This basically confirms the intuition that Planckian fluctuations stay at a Planck scale. Next, you can look at different states for the gravitons. We looked at, for example, thermal states. When you imagine that in the universe, there is a thermal bath of gravitons at some temperature, capital T. You can do the computation similarly in the same way, and then you arrive at the final formula. And one very interesting thing that happens is that since the Bose-Einstein occupation factor blows up for low frequencies, it goes as 1 over beta times omega, this is going to restore the Brownian accumulation factor. So for the thermal state calculation, we can see this Brownian accumulation effect where there are small scale fluctuations, they are still Planckian, but as the size of the length over which the photon travels in space-time, as that grows bigger, this noise spectrum also grows bigger. So if you work out the numbers, you can see that essentially these scales, they still are very small for a tabletop interferometer or even for a LIGO interferometer. But what you have something in mind is a different story. For example, you can say, let's say that in the universe, there's a thermal bath of gravitons, just slightly lower than the CMP temperature, around 3 Kelvin. These are relics from the Big Bang. And then let's say the photon traveled across the entire universe. Then as the photon travels, it's going to accumulate all these geometric fluctuations from the thermal gravitons, and these can potentially be observable already, let's say, from the CMB photon. So this is something to be worked out precisely. Alternatively, you can also look at squeeze state computations when the gravitons are in a squeeze state. Similarly to the thermal case, we again get an enhancement, but here it is an exponential enhancement in terms of the squeezing strength of the squeezing operator. So squeezing again also appears in cosmology, for example, in inflation. So whenever you put a field theory on an FRW background or an expanding background, then the effect of the expansion is going to be a squeezing effect on the vacuum. So if there was a vacuum, graviton vacuum in the early universe, then as the universe expands, that vacuum is going to get squeezed. And this can also enhance the noise significantly. So the takeaway from this is that these cosmological states or states motivated by cosmology can amplify the noise and can potentially be observable. And the last and maybe the most interesting effect that we looked at is a matter vacuum. So in this case, we start from the fact that there are matter fields in the universe which are quantum and they have a stress tensor. And according to Einstein's equations, this stress tensor back reacts onto the geometry. So first you compute let's say the expectation value of the stress tensor, then you get the very famous cosmological constant problem that this just goes to infinity. This number does not exist in effective field theory. And the customer approach is to introduce a normal ordering where you simply just subtract that infinity. So even if you take this approach, you can still compute the correlation functions of the renormalized stress tensor. So there will still be energy fluctuations, even though you subtracted the infinite contribution. And those can very well source metric fluctuations. So this is the case that we studied. This is a baseline computation. It turns out that you can actually go through it precisely without any problems. The formalism works. And then this is the final formula that you get for the power spectral density. So this is a higher order effect. So it scales with Planck length to the fourth instead of Planck length squared. And there's another dimensionless factor. So again, even in this case, the spectrum goes to zero at zero frequency. So again, no Brownian accumulation factor. And then the spectrum just starts growing indefinitely for larger frequencies. So in this case, if you work out the numbers, again, we don't see a measurable effect, but this model basically exposes a very important renormalization question. One say, for example, is that in this computation, we use the Whiteman prescription for the correlator. That's why we are getting very small numbers. If on the other hand, let's say we use the Feynman prescription, we are computing time-ordered correlators, then the answer would have been infinite because we are effectively computing a one-loop computation, and then we get the standard one-loop divergence effect. Except that in this case, we are not looking at a scattering experiment, so it is not obvious that we are supposed to use the exact same renormalization procedure as in the S-matrix computations. Maybe we have to use something else. And this is why what I would like to stress is that these computations, this model basically connects these fluctuations, the scale of these fluctuations to the cosmological problem in this, cosmological constant problem in this sense. So let me conclude where they are. So we are designing models of space-time fluctuations. We are trying to understand what is the computation that you have to do in order to ask the question, how big are space-time quantum fluctuations, or whether there are there? What is the experiment that you could do to test these? So in our paper, we tested some control sectors. For example, we tested the vacuum gravitons, and we also looked at different states, such as a thermal and a squeeze state, the more cosmologically motivated. And we also looked at the stress energy fluctuations. So what we find is that basically this observable that we are looking at seems to be well defined. There are no computational issues. Everything goes through, and we can try to assess what is the nature of these quantum fluctuations. For the graviton noise, we can see signatures of this Brownian accumulation effect when we have the intuition that there are small-scale fluctuations of space-time. They are Planckian, but as you increase the scales in the measurement, these fluctuations can accumulate. So these are potentially relevant for cosmology. And we also looked at the matter back reaction, which was small in the Weitman prescription, but it exposes a sharper question, which is how should stress tensor noise be renormalized for a vacuum noise observable? And thank you very much for your attention.
Thank you so much, Robin. So now we have time for questions. So do we have any questions? Yes.
So, yeah, I think it's an interesting idea, but the thing I wonder about, I mean, gravity is so weak, I would have thought the stress energy fluctuations would just overwhelm everything else. And I mean, is that what you're finding? And if so, then one might consider looking at how space-time, I don't know, has some kind of Brownian motion due to different species, and maybe they could be identified in some way. It's just not, I would think gravitons might get clobbered by everything else. But maybe I'm not, maybe there's something else.
So you're talking about the stress tensor fluctuations or the gravitons?
Well, I'm talking about both in the sense that I would think that I mean, matter will, and all matter fields will undergo similar fluctuations. And because they source the metric, they will induce space-time fluctuations that I would think would be bigger than whatever gravitons could. That's the thrust question.
Yes, exactly. We were also expecting larger fluctuations. I think so. We are still currently designing what is the right setup, like what is exactly what we should compute. So this is something very concrete that we did here. It is not yet clear that this is the final observable. There are lots of questions. And there are a lot of ways that you can expand this model. But honestly, yes, I would expect also that this kind of clumping would appear in some sense. We are still looking for what is the right way to access these. One example could be like what happens if you do a curved background. So this is a perturbation around Minkowski. If you have a non-trivial background, then you're going to have to deal with other stress tensor renormalizations. So those could potentially be different effects.
Yeah. But I just think it must be a lot bigger than what gravity would do on its own. So. Okay.
All right. Do we have more questions? If no questions, I have a very quick one. When you say the Weitman prescription for the renormalization, is it the same as the standard point splitting Hadamard renormalization, or is it something else?
I think so. I'm not fully familiar with that one, but I think that would be very similar. Yes, it's basically it says that the stress tensor correlator is a function of the Weitman function of the matter field.
Oh, I see. Then you use the Hadamard condition and subtract the geometry. Would that be it?
Exactly. So you're looking at the stress tensor correlator. That is a function. Say the stress tensor is a stress tensor of a scalar field. Then you can write this as derivatives acting on the Weitman function of that scalar field.
Oh, okay. All right. Thank you then. Yeah. Thank the speaker. Great. So yeah, if the computer here thing. Okay, so here. All right. So our next speaker and the last speaker before the lunch break is Kelly Wurtz. She's a PhD student in Eduardo's group. And today she's going to talk about entanglement harvesting, conformal field theory. Yes, the stage is all yours.
Thank you. Something I need to ask before we begin. Does anybody want me to give a basic explanation of what entanglement harvesting is? Is anyone lacking that? Okay, so entanglement harvesting, the general kind of protocol, which I cut some slides on, so do it on a little cartoon on this part. Okay, I don't need much space. Pretend this is a quantum field. We are going to take 2 qubits and basically dip them into the field for a limited interaction time. And they're going to stay space-like separated throughout their interaction with the field, or something like it. In flat space, you could say they're on the same time slice, or I'll show some diagrams later of what exactly we mean by this. But the idea is to study the entanglement structure of the field based on the outcomes of doing this kind of probing of the field with atoms. So the field entanglement structure is very difficult to probe on its own, but if we dip 2 atoms in, take them out, and then we look at how those are entangled, and indeed if they're space-like separated, if they become entangled, that entanglement can be traced back to correlations in the underlying field. So this is basically an operational, quote-unquote, way of studying entanglement and quantum field theory. And the main point of this talk is that we're going to do entanglement harvesting in a special kind of quantum field theory called a conformal field theory. And it is defined by invariance under conformal transformations. This is, maybe you've seen a picture like this before when learning about types of conformal transformations in math. It is a map that preserves angles but not necessarily sizes. And it is made of Poincare transformations together with scale transformations, together with these special conformal transformations, which we don't have to worry about too much, usually as indicated by this diagram down here. In physically reasonable theories, scale invariance guarantees invariance under these special conformal transformations. So in a way, they can be grouped together. And a conformal field theory is a quantum field theory whose correlation functions are basically invariant under conformal maps. And so this is a special field theory in that it's a highly symmetric field theory. But it is not necessarily exotic, as we'll see, particularly because it actually simplifies the theory a lot. So one thing to know about CFTs is that operators within these theories are characterized by how they scale under dilatations, basically, which are scale transformations of an operator. It can pick up this factor out in front with the exponent minus delta, and the minus delta basically defines its weight under a given dilatation scaling. And they actually kind of organize themselves into structures that are called conformal multiplets, where you have an operator that we call a conformal primary, that is the lowest weight operator in this kind of column. And then the rest of the operators can be generated by derivatives upon it, and it forms this conformal multiplet. You don't need to worry about these ones. We're going to focus our attention to these primary operators, so just want to give an intuition as to what they are. And what's nice about these conformal primary operators is that their 2-point function is complete. When you put the symmetry requirements on the 2-point function, it's just fixed. And the only free parameter that you have is this delta in the 2-point function. And down here, these are just some examples of CFTs. Massless free scalar fields are examples of conformal field theories. A 3D icing model at criticality, and one that the holographers like called n=4 super Yang mills. This relation here I'm going to explain a bit more on the next page. So we're interested in CFTs. One of the reasons we're very interested in CFTs is because they play a central role in what is called holography. There are these, well, the most popular form of holography is a duality between quantum theoretically, or in practice more semi-classical gravity on an ADS spacetime. That being mapped in a dual way to a conformal field theory that lives in one fewer dimensions. And so understanding this conformal field theory, we can use that to understand things about the bulk space-time. Potentially even quantum gravity is the attraction. So this is the two-point function that is fixed by symmetry for these conformal primary operators. And if you've ever studied a free scalar field theory, you'll notice that this looks a lot like the two-point function of the field amplitude operators in free scalar field theory, except for that this exponent is, well, 1 in like the 3 + 1 dimensional case for that, but here it is anything. And well, I'll make the connection first now with the massless free scalar field theory, that what this is telling us is that if we perform entanglement harvesting coupling to a scalar primary operator of some weight delta, that will be identical to doing an entanglement harvesting protocol in a d-dimensional free massless scalar field where delta and d are related like this. So that doesn't mean we're like moving into a free massless scalar field, but it does mean that the results would be the same. And so this is what we do, couple two detectors to scalar primary operators. This is your run-of-the-mill Hamiltonian integral that occurs in entanglement harvesting, where this is the operator that can excite the detector. This will be how we control the time dependence of the interaction. We're going to choose to kind of turn it on in time in a Gaussian way. And this is the spatial extent of the detector, which we are just going to take to be a delta function because it makes our lives easier, and we call this a point-length detector. And then here we're coupling basically the operator of the detector with the scalar primary operator of the field. And we're going to time evolve perturbatively in this coupling constant. And the setup will kind of look like this, where we have these two Gaussians. The fading opacity is meant to represent a Gaussian of switching time scale t, something like the width t. And we can separate them like this. And we can also separate them like this. You'll notice that because Gaussians have infinite spatial support, these are kind of not technically space-like separated across the whole interaction. But here we can go by like a 5 sigma criterion, say, but that shouldn't be taken without further investigation, because we can actually evaluate how much of the entanglement comes from the field versus from communication between the detectors. And yeah, something to note is that when the time and space separation are equal, then this means the centers of the time smearing functions are space-like separated. These are just some of the basic equations having to do with time evolution. We start the detector and the field state in this uncorrelated state. We form our time evolution unitaries through the interaction Hamiltonian we showed on the last slide, Dyson expand things, and we end up with this being the final state of the two detector system. And a lot of what people do in entanglement this is not special to this paper. A lot of what people do in entanglement harvesting is they get a matrix that looks like this, but all these terms take different forms based on the protocol that you've set up. And you kind of analyze those to see if there's entanglement in the state. These two, LAA and LBB, can be interpreted as the local, or just the excitation probability of the detectors themselves, which is not, it's local, it's not going to depend on the other detector, basically. M is a correlation term. It's going to come into the negativity. LAB is also a correlation term. It comes into the mutual information. Not going to have time to go through that today, but it is explored in the paper. And all of these, when we choose a point-length detector, actually become independent of the space-time dimension. And that makes things a little bit confusing, because I was talking about some of these cases being identical to free massless scalar in certain dimensions. So I made a slide to hopefully make all these points clear. Our conformal two-point function, that is just dependent on delta. That does not depend on the space-time dimension, just depends on the scaling dimension of the operators. And because we use point-length detectors, there's no spatial scale introduced by the detectors, and so our results apply for primary operators of any weight, or of weight delta in any spatial dimension of your CFT. But also, if we consider this relationship between some dimension of a free scalar field that we're trying to match the results of, we just have to basically make delta match that. So in a way, this is like generalizing to more dimensions, but it's way more than that because CFTs are interacting theories, and yeah, I'd say it's basically cool because CFTs are, in general, interacting, and because they have this highly symmetric structure, they are kind of the first theory that we've been able to do entanglement harvesting, first interacting theory that we've been able to do entanglement harvesting on. Okay, so the negativity criterion is actually pretty simple. It's basically just that M, which is in general complex, has to be larger than the local noise term of the detector. And it only takes this form because our two L's are equal because our detectors are equivalent. Otherwise, it would have dependence on both of them. So our entanglement criterion is just going to basically be M is bigger than LAA, or signal overcomes the noise. This is LAA in its beautiful exact form that is not important, but it's the one thing that can be solved exactly, so we write it out. What's nice is that we can work in certain asymptotic regimes for LAA. We can work in the large T omega regime because we just set the gap to 10 because we can. And we're going to consider the L, the delta, or the spatial and time distance and the gap in units of T. Everything will be in units of T here. So what this is saying is this is complicated, but actually we're in this regime where it's actually just an exponential. And if you plot that exponential over the results of evaluating this numerically, you see that it lines up, especially at the small deltas that kind of, well, we can match with the cases we know about free scalar field theory. Okay, now we get to some fun plots. Now we're going to look at M. And so before we were just looking at LAA change with delta because it doesn't depend, capital delta because it doesn't change with L or lowercase delta, the time separation. But for M, which does depend on all three of these things, we'll look at how it varies with all of them. Notably, the correlations fall off as you move them farther apart. This is something we'd expect. They kind of blow up a little bit when they're close together, but that can just be traced to causal contact. Another thing we see is that this is peaked when they are light-like separated. And so that makes us wonder if that is entanglement. When we do the, or if that is entanglement from the field. When we do the subtraction between the signal and the noise, we get these profiles where negativity has kind of a similar profile to what we saw M do, but it has this cutoff where then the local noise overpowers the kind of M term. And you can see that it's dependent on the scaling dimension of the operator and that there exists this maximum. And then we also see that entanglement harvested is dominant on the light cone. I'm a little bit short on time to tell you guys all about, why is this not working? I'll use that. That's fine. I'm going to just say some brief notes on this because there's a lot of work on this. I'm not going to have time to explain these concepts of separating the entanglement in full detail. But the idea is that by separating our two-point function into its symmetric and anti-symmetric parts, this is separating the two-point function into basically contributions that come from communication versus contributions that come from harvesting. This was explored before this paper and these two papers. That kind of is the first one. And that's some arguments for that I will not have time to get into. But a very cool result of this paper is that usually in interacting fields, the arguments of the papers that came before doing the separation don't apply. And so a priori, we wouldn't be able to make a separation between the entanglement that comes from communication and the entanglement that comes from harvesting. But because well, I can't even say because this is a special field theory. It actually comes down to looking at its holographic dual. This is how we realize that these arguments would still apply. And when looking at holographic Cs in particular in this limit where we understand it well, we see that these two-point functions actually take on free field behavior, and they are dual in this limit to free fields in the bulk. And so exactly the same arguments that applied for this separation in free fields apply in conformal field theories in this holographic limit for operators of any scaling dimension. And let's see some fun plots. This is very illuminating because this tells us that as we see the negativity fall off as we move the detectors farther apart, which is basically going this way. The negativity that comes from, well, let's start with the communication, which is down here. The negativity that is coming from communication is dying very, very fast as we move the detectors apart. Whereas the negativity that's coming from, genuinely coming from the field, persists for a bit longer and makes up kind of this regime that we saw in the other plot before it dies out. We can tell that that is all coming from field entanglement. And the really fun plots happen when you make these things, when you shift them in time and bring them closer to the light cone of the other. The two-point function picks up a phase when these things are within the light cones of each other in either direction. And this leads to this very interesting oscillatory structure, which before had just been kind of studied in, this would be the case of 1, 2, and 3 spatial dimensions in a free massless scalar field. And it's just been kind of viewed as some interesting stuff happens around the light cone, but now we kind of get like a vision of how this interpolates between those cases and some fun plots out of it as well. So I'll leave this up here so we can get to questions, if any. But yeah, thank you for listening.
All right, thank you so much, Kelly. We have time for questions. Yeah, we have time for questions. Let me go. Oh, yeah. Okay, we have time for questions. Yeah.
So I'm assuming that you always consider the detectors to start in the ground state in all of these studies.
Mm-hmm.
So when you consider detectors to start in the excited state or ground excited and things like that, sometimes it starts seeing some oscillations too in the negativity. It doesn't get to zero like you found there, but it's like, I don't know, I wonder like if you have any intuition for what would happen if you were to apply the same techniques for the case of ground excited or something like that.
Zero, no intuition. That's very interesting though. Eduardo has intuition.
No intuition, but something you can take in a second, because it's changing the sign of some omega.
Sorry?
It's changing, flipping the sign of some of the omegas. You can do it very fast with the math. It doesn't require a further study. It requires you to flip the sign of some omega.
Ah, I see.
Negative omega means you're starting in the excited state.
Yeah. Yeah, then there would be some interplay with this phase, presumably.
And
maybe some relationships between delta and the frequency will then affect the behavior more. That would be interesting.
And just given that I already have the mic, so Matheus and I, we did a study in the past where we studied basically the difference between coupling to the field or to the momentum of the field. And then what we found is that in the limit of large energy gaps, actually there's a duality between the two. So basically the results, including for entanglement harvesting, can be related by a factor of omega, effectively, up to some extent. Now, I assume that if you were to translate this to this example you have here, then it's you would have that the field and the momentum will just correspond to different scalings of the operator that you're coupling to. But I'm not 100% sure, but I would imagine that that's the case, simply because the pi-pi correlations, they decay faster, like with additional powers in this conformal theory.
Is the question about the existence of something like a momentum operator in a
No, my question is whether you can say anything about like whether there's some sort of like relationship between what you see for small delta and higher delta, like some sort of like connection between the two, some sort of duality that you found in the results, like something that maybe there's a parameter here that relates the results for small delta with larger delta in some effective large gap regime as well, or something like that.
Yeah, for example, I mean, this line, which I kind of failed to explain what that meant, is drawn from taking the first order approximations for LAA and M in far from light cone regime and high gap regime. And if you just take the leading order ones and the subtraction, you get this line, which aligns really well with the numerical results. And yeah, we have a lot of approximations in our paper.
Good, okay, nice, thank you.
All right, any more questions? If there are no questions, I have a very short one. When you do the separation of N plus and N minus, did you also find examples where you have interference? You can have like communication, but they conspire, then you have like no negativity at all?
I haven't thought about where there are dips, if it is due to interference.
Because I think your switchings, I mean, by what I saw, I might have missed something, but your switchings have symmetries when you have like, but I'm not sure if something would change because you're considering a conformal field theory here, and there's also that delta parameter, so I'm not sure.
Yeah, I know. I know you have a paper on that, so that would be interesting too.
Because if that was Minkowski with your switchings, there would be no interference. But I'm not sure what would happen in your case here. I wouldn't like, yeah.
Interesting. No, I haven't thought about that yet.
Okay. All right. So, oh, you have a question?
Very, very short.
Yeah.
Your answer maybe is I don't want to. But any words on trying to interpret that because the parameter delta can be real and in real time. In principle, we know how to solve it for any complex value, obviously. Complex delta. Any imagination about thinking of it in terms of free scalar theory in exotic dimensions or something like that?
Yeah, go for it. You can totally do that. Whatever you want to interpret it as.
Well, I see that the analysis you have allows for even complex data. No problem.
Complex dimensions. You thought non-integer dimensions was crazy, but.
Delta's d minus 2, you've got all kinds of fractional irrational dimensions there, right?
2 plus 1, in every odd space dimension will have fractional square root or it's a fractional semi-integer. Why not more complex?
True. And just flexing that we like solved something for general complex values in the paper. Well, that was Eduardo's contribution.
All right, then. So, if no more questions, let's thank Kelly again.
All right, hello. Hello, everyone. Thank you for joining us after lunch. My name is Ireneo. And for our third plenary speaker, we're going to be hearing today from Rodolfo Soldati. So,
perfect.
Get off to you.
Thank you for the introduction. Hello, everyone. This talk will be a little bit different, I think, from the other RQI talks. I mean, the topic is not so much relativistic, it's more quantum information, and it also involves a lot of programming. I mean, we'll go into that as we go, a lot of mathematics, but you know, I hope to motivate properly why I'm interested in conveying all of this information to you. So I'll be talking about this notion of machine-verified quantum information. I'll be talking about the generalized quantum Stein's lemma and the lean programming language. This is based on a result with Alex Myberg, Leonardo Lessa. They are both at PI, and Alex is also at IQC. I'm also at IQC, an associate at PI. We have this archive from last year and a repository on GitHub that started all of this. Okay, so yeah, so I'll talk about what is this programming language lean. It is something that is called an interactive theorem prover. I will elaborate on what that means, what formal verification or machine verified anything means. The idea here is that we'll input some quantum information theory in this language. Then I'll briefly skim through the versions of the Stein's lemma, which was a big motivation for this work, but it doesn't end there. And at the end, just give more information about what I'm calling here the PhysLib, which should be a physics library, more broadly speaking, written in this programming language. And also, at this point, this is where it becomes interesting to, relate to things that we do in our research, and here in particular, of course, relativistic quantum information. And then have some concluding thoughts. Okay, so let's go for it. I mentioned that lean is an interactive theorem prover. It is also called a proof assistant, but I prefer the first name rather than proof assistant, just so we distinguish a little bit from AI, which is another big thing that we have today. Lean will interact very interestingly with AI, but they are in principle different things. So just to make sure that when we understand what we are talking about. So lean provides this platform for logical verification based on something called dependent type theory. So this is one way to talk about the foundations of mathematics. So maybe you can think of set theory as one way to talk about the foundations of mathematics. You have the ZFC axioms, Zermelo-Franco and the axiom of choice. You build everything, even natural numbers, integers, whatever, all based on sets. And the dependent type theory is a different way of doing these things. You have this notion of a type, which is foundational in that sense, kind of like substitute a set. Although, first approximation, you can understand a type as a set. That would be fine. Lean is not the first of its kind. There are other programming languages that work as interactive theorem provers. There's ROC, previously was called COC. There's Isabelle and many others, possibly also with different foundations. So some other versions of type theory, for instance. And how lean works, to make sense in a programming language to prove theorems, and how in a sense, this type theory interplays with all of that, is kind of like some notion of a dimensional analysis, but some dimensional analysis, a more powerful version of that. So, you will have expressions written in terms of different symbols maybe that you want to compare, and the language will be capable of telling you whether some sort of statement that you made with these symbols is, if it type checks. In a sense, if they have like the same dimensions, right? So you cannot make an equality between seconds and meters, for instance. You need to normalize the dimensions. So it's a very, surface level, kind of intuitive way of understanding how this all goes about proving theorems. And furthermore, so like this logical verification also itself has a story with these other languages. It has been used to already like prove or verify the proofs of other important results for color theorem, the Diophantine equations. One very big result that kind of, put Lean on the map was this liquid tensor experiment, which was proposed by Peter Schulze, who's a field medalist. I don't know about any of these maths. These are just examples, okay? These are like very complicated stuff. On the Lean side, which is very active these days, we have a big project to formalize Fermat's last theorem. So Fermat's last theorem was already proven famously, in the end of the 1990s, I think. It's trusted to be a correct proof, and it's standard today. But these languages like Lean, this logical verification, provides us with a kind of like a next step in terms of rigor. So the proof of Fermat's last theorem is originally put out in terms, it's in human language, natural language, which can be full of ambiguity. Of course, a professional mathematician will do a very good job at avoiding these things, but we can only do so much. So one way to avoid problems is to teach the computer how to understand and check a proof for us. Okay, there's other applications of a language like this. It can be a very practical thing to do as well. Languages like Lean can be used for software verification. One example here, I'm talking about Rust, which is a different language. It's a more regular language in a sense, like it's used to build like systems for, I don't know, government, universities, whatever. And in a sense, Lean can be used, and it is being used. There are projects around this, that you translate Rust into Lean, so you can also check the validity of the whatever output this language gives you. So it's very practical in this sense, and I have some thoughts. I hope to maybe share more of this soon. You can also ask me about it, because this can also have repercussions for physics, but yeah, we'll see. Okay, so like why trust it? Right? Why trust Lean? Why is it, like a next step in rigor? Why is it logical verification? Why should I trust maybe Lean more than I trust my colleague? In a sense, the way that this trust is built on is that it minimizes what needs to be checked. So like you're inputting your theory into code, everything is very precise, followed symbolically. And, maybe to have a full trust on that system, you need to trust that your code doesn't have bugs. And it's in this sense that Lean has a small, kernel, a small nucleus of truth that it's built on. And because of its size, it can be audited. So, different people with different goals can all, read that small code and trust it. Another way to put this is having, a big community building results for this language. So you have a large network of results that essentially are like checking each other, right? They will be independently constructed and eventually connected amongst themselves. And, if everything is working fine, hopefully, these connections should also be consistent. So it forms a coherent whole. So maybe like you're familiar with Python, for instance, that's a programming language. You may have NumPy or SciPy. These are libraries in Python. And for Lean, we have Mathlib, which is this really big library for formalization of all of mathematics. This is like a quote on the website. There are already millions of lines, over 500 contributors. We have, it's a big community, and people are increasingly putting more results there. For instance, those projects of putting Fermat's last theorem, it's like a 3-year effort, and it will eventually be on Mathlib to be used as well. Okay, so a little bit more on how this works is that you have like this certain like simple pipeline here. So you are a human, and you will, you have some result in your mind. You will go to the computer and write some program in Lean. Okay, the way Lean works is through these, the dependence type theory business, and it interprets that program that you wrote as a proof, okay? And it's interactive. You will have something that you can look at. It's called like a tactic state with the result of the program. In a sense, the program will only run or compile if the proof that you wrote is correct. That's the spirit of the thing. And you can read that, and this is the output of your proof. Okay? A few other keywords on this process is like calculus of constructions or proofs as programs. This is already going a little bit into the dependent type theory of Lean. You have this notion of a type, like I mentioned before, and in particular, you have a type called prop. I also said that a type is, you can kind of see it as some sort of set. And the point is that elements in this prop set will be propositions. So they are, for instance, equalities between two variables, A equals B. So you need to state what these things are, you need to state what an equality is, and this forms you a proposition, which is the type of thing that you want to eventually prove. And this whole system here makes the problem of proving a theorem into a very constructive thing, because when you are writing a program that is to be interpreted as a proof, what you essentially are is making a proof into kind of like a concrete object. So you are essentially, kind of building a variable that you interpret it as a proof. I mean, this can be all very abstract. Maybe if I have time in the end, I can try to pull like the no cloning theorem, for instance, to exemplify. But for now, just talking about like why these things are interesting to us, and and what we did choose, like our particular result, like to try to get people involved in this. So yeah, we did this formalization of the generalized quantum Stein's lemma. The Stein's lemma, I will elaborate on what it is exactly, but what I'm talking about here is this formalization, like we build the logical verification of an existing proof of this generalized quantum Stein's lemma, which was first put out by Fernando Brandão, Martin Plânio in 2010. So it has like an interesting story, and we were following this story, and we thought that this would be a really nice thing to put into Lean. You'll see why. So yeah, like a lot of results came up in the meantime since 2010 based on this result. A lot of things on like resource theory and thermodynamics. But in 2023, a proof gap was reported. And it's a non-trivial proof gap. It's not like any factor of 2 that went missing somewhere. So yeah, since 2023, people were working towards correcting this proof gap. And in 2024, there were 2 major attempts by Hayashi and Yamazaki and Ludovico Lamy that are today accepted as corrections to that original proof. So they the proof that they put out differs from the original one substantially. The result is roughly the same still, and despite some efforts that failed, these 2 independent results corrected the proof. And because of this sort of problem that the community faced, we decided it would be nice to put it in Lean and verify these new proofs now to a new sort of standard that something like an interactive theorem prover language would be capable of, right? So we are accepting these proofs as humans, but it would be really nice if, in 10 years from now, we don't, go back to the first step there and we find another gap in the proof, and then we need to start again. So we did go to do this formalization, and we put out this paper last year. Okay, so about the content of the Stein's lemma itself a little bit. So this is a little bit more of quantum info. It's a theorem in hypothesis testing in the following sense. So you imagine you are an experimentalist in a laboratory or something, and you have some device that gives to you some actual state, right? I don't know, like an electron oven that is giving you electrons. And then you postulate 2 alternative hypotheses, a null hypothesis, where this actual quantum state that you're given is described by a density matrix eta, and you have a signal hypothesis where it's described by an alternative density matrix sigma. You may have like a theory that would motivate you to pick one or the other, and the second one, maybe called the signal, is the one that you're kind of like interested in to like do further information processing maybe. And so you will exclude the null hypotheses, the eta density matrices. But first you need to validate that the state that you got is the one that you actually wanted. Second step, you do a bunch of measurements. If you want to like really go into the details of this, you put like some POVM, some binary POVM, and but yeah, so the lemma concerns some error analysis on these results. So you accept some error probability epsilon of concluding that you had sigma, but you were given the state eta. So the state was actually eta, and you thought it was sigma. That's an error. And you have an alternative error, which is kind of the other way around. You were given sigma, but you concluded that the result was eta. The known error states are, of course, you were given eta and you concluded eta, you were given sigma and you concluded sigma. And the question that it tries to answer is how does this alternative error of concluding the null hypothesis given the signal scales as the tests are done, the measurements are done, and again, you accept some error threshold for epsilon, for the error of concluding sigma from eta. And so the Stein's lemma, this whole setup, we'll talk about some sort of like relative entropy related to this error. And it talks about how this error scales asymptotically. So on the limit of you having done a large number of measurements. And the result is that this error will kind of exponentially decay with this factor D here, which is the relative entropy, or maybe the omega key entropy in the quantum case, or Kullback-Leibler divergence. Sorry. And so, okay, I guess I'm running out of time here. The point is that this gives an operational way of understanding the relative entropy. You have like a kind of like a setup to understand that. And so the lessons learned here is that the proof was essentially correct. We find some minor imprecisions, like, when you're putting something into lean, you are being precise into levels that are probably annoying to deal with on a daily basis. But as we put more results there, hopefully we don't need to worry about these particular details as much anymore. And a small little funny comment here is that we put out our formalization, so our verification of the proof on the 9th of October, and 20 days later, the Hayashi and Yamazaki paper came out on Nature. So we kind of beat the publication process by 20 days. I mean, something interesting to consider, given that, the regular job of a referee would be to check the proof, and we kind of did checked the proof independently in some different way. Okay, and so going a little bit ahead already, we had this result, but we are very excited on making some repositories with these results grow. And I'm here, to kind of hopefully get people excited about this. And so we started with this lean quantum info for quantum information in particular. But we are growing to a repository PhysLib for physics in general, like MathLib was for mathematics. I'm a maintainer here, and it's open source. Anyone who learns lean can contribute to code there. And we're managing this, so it has a lot to grow still. And from this perspective is where we can question what kind of physics should go into lean. So physics is not the same as mathematics, and so you need an alternative motivation to put things there. I've been on kind of like this mission that I set for myself on finding out from different fields what should we put there. So maybe quantum foundations, we want quantum theory reconstructions, generalized probabilistic theories. From strong gravity, we have well-posedness problems and results in that direction, singularity theorems. And we can ask about any other sort of field. And relativistic quantum information is one that should definitely be there as well. In particular, I'm excited about quantum information because it's very amenable to be put into lean. It's very rigorous. It works very well in that sense. More so than maybe other more speculative or intuitive areas of physics. And we can ask further questions. Are there implications for experimental physics, like something like on the direction of benchmarking, as Lean is used for software verification, possibly hardware verification as well. And the fundamental question of whether should physics be formalized in the first place, I think is a question worth addressing. Maybe I could talk a little bit on like the process, what we learned in the process of doing this. So, I mean, there is a lot to implement, like especially on the physics side. There's essentially a set of measure 0 probably of what can be done in physics. And we learned that the more we implement, the better we check for the validity of these results. It is good to have, like, to aim for sufficiently complex projects, like, a final goal which is sufficiently complex will demand from you building a lot of background, and this makes everything, kind of coherent in the process. So, you achieve some level of good integration. This is also like why it would be nice to not have, to have like one big library like PhysLib or MathLib for all the, the community, because you have this cross checks working. And, just like regular theorem proving, it's a balancing act between, like if you're writing a proof, you want it to be expressive and to teach you something about the subject. But, you are compiling something on a computer, so you want it also to be somewhat compact. A few more specific questions is how physics would interact with these different mathematical foundations. How can this be made, computational? Can we do search for axioms, in a sense, in a programmatic way? And yeah, so that's mostly it. I guess I'm running out of time here, yes. So, I mean, there are a few things that we still can do. As I said, I'm more very particularly interested in more quantum information, and then we can start interacting that with, relativistic physics, which should definitely be amenable to formalization as well, to some extent. Another result would be, more specifically, there are things in the Hayashi and Yamazaki paper that we did not formalize, and that concern second laws of thermodynamics as they are understood in quantum resource theory. And, kind of, just put the question out there for the relativistic quantum information community, what would you like to see implemented, and to engage with us on PhysLib.
Talk. Are there any questions?
Yeah, so it's quite intriguing, except that it'll put everybody out of a job, but you can't have everything. No, but more seriously, when you did the quantum Stein lemma, did you put in the original incorrect proof, and and if so, did it find where it went wrong?
So no. This is a question that at this point many people have asked, and I think we should definitely do that at some point to learn something new, but it is not trivial. It's like a big work to put a proof there. So even the incorrect one. So we did skip that step just, so we could get something correct at the end of the day. But yeah,
It should be done, I would think, yes, right? Because then it's a necessary test of the lead.
Yes.
So then so now you have this thing, you beat the other guys by 10 days or something. But basically, you're in full agreement with the others to the extent you overlap, I would assume?
Yeah, so we were...
on the Stein lemma.
With Hayashi and Yamazaki, we've communicated with them. Everything is...
Okay, all right, that wasn't clear to me.
Yes,
okay.
No, we're in agreement. Ludovico, the alternative proof, is sufficiently different for us to not be able to talk about so much. In fact, we chose not to do that proof because it relies on statements on infinite dimensional Hilbert spaces, and these are not very well dealt with in MathLib yet. So there's more work to be done if we want to formalize that alternative proof.
Okay, thanks.
Right. So I guess two questions. One quick one, less kind of follow up. So I would expect that one of the main advantages of having this, right, if you were to implement the first version, right, is that it would tell you exactly what you're missing, no?
Yeah. So
and the dependencies of that.
Yeah, it would definitely. The expectation is that it would tell you where it's failing. But you also need, because I think if I remember correctly, the problem with that proof was using the result of some other theorem. So you need, to kind of start digging through these theorems, and you also need to put them there. And I would say that the process of doing this ourselves, in principle, would also it could have, like, if we were trying to do the proof in Lean before the gap was reported, we would definitely find a mistake in that process. And it doesn't need to be something that we notice from the language itself, but from the process of putting the thing into the language. But there are these two levels that definitely exist. The language can definitely, at some point, flag you some incorrect step.
Right. It feels that, you see, there are two. There's more than two. But let me make it up and say there are two main strategies of proofs. Right. One is extremely intuition based and then formalizing, meaning like some mathematician or some physicist has a great idea that probably gives the proof, but then formalizing it is tough, right? The other style is like, well, let's just grind through the formalization and see if we can prove it from that, right? Mm-hmm. Do you think this one is more similar to the second, and then when you add AI, you may try to do the first? Or because right now it feels more like the second, right? As in, like, you still need the human inspiration. Maybe the inspiration can come from elsewhere that's not human, right? But because I guess this is more, we know it's true, let's try to build it in a language that is formal and easy to verify for a computer. But it doesn't have yet the first part, no?
Yes.
Building from intuition to formalization.
Yes. So, yeah, I mean, there are these different levels. So you also, have this notion of what is like a proof that looks natural in Lean. So yeah, you also, want to kind of learn how to talk the language in a sense, not only, just the surface level syntax. And you also have, so one interesting thing is that Lean has, it's a regular programming language as well at the end of the day. So you can do a lot of automation. And, without including AI into the process, a lot of the automation is, us trying to put proof techniques that kind of sort of works always in some sort of like little meta program that we can call and make Lean do the rest of the job for us. Like search, you have a large library of theorems, and Lean can search that large library itself to try to complete the steps for you. So this is one way to do it. That doesn't even invoke AI. Okay. But then, yeah, with AI, you have this level of, some midway point between the human intuition and the AI intuition, whatever that means when writing the language.
And I guess my second question is, if you can say something about the deformalization problem, right? As in, like, you can have a Lean proof that may look very difficult for a human, perhaps. Yeah. I'm thinking not now, right? Because now it's human building them, so in the end. But if you have AI, for example, and AI comes up with a proof, right? Yes. And we know that, and Lean can check that the proof is consistent, but maybe there's some trivialities, maybe not. So to try to read that as humans, we would need to convert it into human natural text of some kind, right? Yes. Do you know if people are working on that, on how difficult it is? Or?
Yeah, there has been some notes on this. When, like, we did use a little bit of AI to help with steps in the generalized quantum Stein's lemma. And like a year ago when we were first starting, the AI would like try to complete steps in a very weird way. I've seen AI written code as well that uses syntax of Lean that I had never seen before. And yeah, so but I think we're still kind of like learning. I think there still needs to be, you know, especially for physics, right? How things will look for physics. We need to put more there to, you know, have this back reaction, this dialogue, and see how things change.
I'm thinking if you can now somehow translate Lean proof into more human natural mathematics proof, is that something that people know how to do? Like mechanically?
Yeah, I would say that mechanically, not necessarily. If the proof is like sufficiently complex, it's something that is not immediate. So, for instance, I mentioned the no cloning theorem. The no cloning theorem almost like goes line by line, even though it's like a, you know, with types instead of sets. But then you just learn types, and you can read it like line by line. Now, very long proofs, for instance, Fermat's last theorem, I don't know what's the status on that. It's probably, like the natural language proof is probably already very complicated. It's going to have its own complications when ported to Lean, and how obvious that will be for other humans to learn from it is unclear to me at the moment. I don't know if humans will want to read the original Fermat last theorem proof or the Lean proof.
I guess it's important for intuition, right?
Yeah, yes. Exactly. Yeah.
Okay, all right, let's thank Rodolfo again.
Thank you. I clicked on something.
Okay, and now we're going to welcome Maria Rosa, Preciado-Rivas. So whenever you're ready.
How do I pick this? Okay. All right. Does this work? Okay. Good morning, everyone. Good afternoon, everyone. Today, I will talk about a work that I am doing in collaboration with Cameron Buney at the University of Nottingham, and it is titled "A Hot Take on What the Unfolding Observers See in a BTC Black Hole." Before I start, I would like to acknowledge that I stutter, which means that it might take me longer to say certain words and certain syllables, so I thank you for your patience. Black holes are scenarios where relativity, quantum theory, and thermodynamics merge. That's why they can serve as a testbed for our current theories, and they can also guide us toward a more unified theory. So with this in mind, the guiding question that we have is, how do different observers perceive quantum fields in a black hole spacetime? So you probably already have an answer for this, and it probably looks like this formula, where we have the black hole or the Hawking temperature, which is the surface gravity divided by 2 pi. Here, the surface gravity is a geometric property of the black hole horizon. This equation arises from two logically separated results. The first one is the Hawking radiation, or Hawking effect, and the second one is the generalized Unruh effect. In the first one, we have a scenario where there is a black hole formed by collapse, and this temperature corresponds to the modes that appear to be coming out of the black hole, but not to the modes that appear to be going into the black hole. In the second one, we have a eternal black hole, and this temperature corresponds to all the modes outside of the black hole. Specifically for static observers that are at some finite distance from the horizon, we have that they will perceive this local temperature, which is the Hawking temperature, divided by some redshift factor. Very far from the horizon, this factor is 1, so we recovered the previous equation, and at the event horizon, this factor is 0. We can rewrite this local temperature, and we find that it is going to be proportional to the proper acceleration. Because we require some infinite acceleration to be at the event horizon, then we are going to get that we are perceiving this infinite temperature. Now, let's assume that our observer has access to some quantum system, that is, to some quantum detector that looks like this. It has two quantum levels that are separated by some gap E. And we also assume that we can couple this detector to a quantum field in some background space-time. Then the interaction is described by this Hamiltonian, and I am going to skip the details because I am sure that we are familiar with those. We have that the probability of the detector to undergo transitions between these states is going to be proportional to the response function, which looks like this. It will depend on the gap of the detector, the switching function, and the two-point correlation or Wayman function of the field. In this case, this ket psi is the field's initial state, which for a Schwarzschild black hole can be, for example, the Hartle-Hawking vacuum or the Unruh vacuum. The first one is used to model the generalized Unruh effect, whereas the second one is used to model the Hawking effect. I know it's funny that they have different names for the vacuums and the effects. Okay, so the way that we check that the response of the detector is thermal is by verifying that it satisfies this detailed balance form. That means that the probability that the detector undergoes excitations is going to be exponentially suppressed by the probability that the detector undergoes the excitations. We know, okay, in this case, this temperature that is given here is going to be independent of the gap. We know that this form holds when the detector is stationary with respect to some state that we already know has some thermal features. And whenever the detector is interacting with the field for an infinite amount of time. So, for example, static detectors at a finite distance will have a thermal response as verified by the details balance with this local temperature in the case of the Hartle-Hawking vacuum. Now, static observers cannot probe the event horizon as we need this infinite acceleration at the event horizon. However, observers that are freely falling, then they will just naturally cross the event horizon. However, their response does not satisfy detailed balance, and this is partly because they sample the region that is close to the event horizon only for a finite proper time. So this raises the question, what temperature, if any, should be assigned to infalling detectors? Well, there are many operational approaches. I know at least 4 of them, but today we will see 2 concerning to detector responses. The first one is simply take the details balance form and solve for T. Then that is going to give you some effective temperature. In general, this is going to depend on the gap of the detector. The second one is the one that we call the Jiayue effective temperature that was prescribed in this paper that appeared last year. In this case, we are going to consider two scenarios. In scenario A, we have this freely falling detector in the Schwarzschild black hole that is interacting with some vacuum state, and we compute what is the response of the detector as a function of the detector's proper time. In scenario B, we have a static detector in flat that is Minkowski spacetime, but it is interacting with some thermal bath. And we compute what is the response of that detector as a function of the bath's temperature. The prescription goes as follows. First, fix some proper time of the detector, then calculate what is the response in scenario A with some gap E and some switching function delta tau. Then find what is the temperature that we call TSC in scenario B that with the same gap and the same switching function gives the same response as scenario A. In that case, then that temperature is going to be the effective temperature for that proper time tau in scenario A. These are the results that Jiayue and Carroll found for the Schwarzschild black hole. Here we are showing what is the effective temperature. Oops, can't see. What is the effective temperature as a function of the infalling radius, which in turn also depends on the detector's proper time. We see that these different curves correspond to different gaps, and we see that for the details balance effective temperature, then we see that there is this clear dependence on the detector's gap. With the Jiayue-Carroll prescription, we are here, they are actually showing all these gaps, but what is happening is that the curves are one on top of the other. So we see that there is this agreement for different gaps. What they highlight is that at the event horizon, as the detector is crossing the event horizon, then we get 2 times the Hawking temperature. They don't show it here, but far from the event horizon, they will get the Hawking temperature, which is the same as for static observers. The reason why they point out this twice the Hawking temperature at the event horizon feature is that it coincides with this other definition of effective temperature that was computed in this work. In this case, they are embedding this Schwarzschild spacetime into a 6-dimensional flat spacetime. In this way, the infalling trajectory in the black hole spacetime corresponds to some accelerated trajectory in the 6-dimensional spacetime. So they are simply assigning to the detector the en route temperature in this flat spacetime. And this one is shown in this green curve, so they get this agreement in the case of the Hurtle-Hawking vacuum. So our question is, can we assign an analogous definition of effective temperature for the BTC black hole? The reason why we ask this is that the BTC black hole is a three-dimensional spacetime for which there is a Hartle-Hawking vacuum, and because it is very easy to compute the response of detectors in this spacetime. Another question that we have is, what is the temperature in BTC as the detector crosses the event horizon? Is it also twice the Hawking temperature? So what we did, which is the hot take, is to compute the response of an infalling detector in BTC, where we use methods from previous work. We actually presented this at the previous edition of the RQI circuit. We extend the Jiayue effective temperature prescription by noting that BTC is locally anti-de Sitter, meaning that it will have this constant negative curvature that is going determined by some characteristic length. So instead of comparing to the response in some thermal bath in flat spacetimes, we are comparing to the response of a thermal bath in ADS3. So, okay, we computed the response in a thermal bath in ADS using previous work from Cameron's. And we extract what is this effective temperature simply by matching these two responses in these two scenarios. So the hot take is actually just a temperature pun. These are our findings. Here I am plotting the Jiayue effective temperature in terms of the Hawking temperature, and here I am showing what is the detector's proper time. First, we noticed that we again obtain this agreement for different gaps, which is surprising because a priori there is no reason for them to agree. We are getting the Hawking temperature far from the event horizon, and when we are crossing the event horizon, which maybe you cannot see very well, but there is a dashed line here showing the event horizon, we get twice the Hawking temperature. This is for black holes with mass equals to 1. When we change the mass, then we no longer get twice the Hawking temperature at the event horizon. We also compare to the details balance effective temperature. We can see that the temperature is going to depend on the choice of gap. But we see that the Jiayue effective temperature is going to be always smaller. Okay, it's going to be always smaller than the detailed balance temperature, as you can see by the values in the y-axis. And we also see that there is a broader spread into the effective temperature obtained using details balance than using the Jiayue method. In this case, this relative spread is about 0.4%, but here is over 1.6%, which is not a lot either. So now we have a definition for effective temperature for infalling detectors in BTC that extends this definition prescribed by Jiayue and Carroll. The main lesson is that this effective temperature isn't always twice the Hawking temperature at the event horizon, and we show that even though these definitions of effective temperature can agree qualitatively, they differ numerically. I would like to acknowledge Professor Jorma Lokot, who hosted me at the University of Nottingham while I was working in this work, in this project. And I would also like to acknowledge Professor Luis Garay for discussions on other methods on how to calculate effective temperatures for infalling observers. that's everything I wanted to say, and thanks.
Okay, I think we have time for one question. Eduardo.
Thank you, Maria Rosa. Very nice. This is a kind of a philosophical question that I always bring on these topics because, again, your work convinces me more of it. Why do we insist in situations that are obviously not thermal, like, for example, this, right, in building effective temperatures? Wouldn't it be a bit of a red herring, as in, like, we have other quantifiers that may be meaningful? Like, you can talk about excitation probability, transition rates, many things like that. But forcing the notion of temperature for situations that are not thermal sometimes can be confusing. So I haven't heard yet a compelling argument that we should look for this effective temperatures. Well, your work, your results kind of show me, yeah, I mean, yes, more or less, but then no. And you see what I mean? Like, maybe we're insisting too much in assigning temperatures to non-thermal phenomena. When you have KMS, no discussion. When you have something like approximate detail balance, then maybe it makes sense too. But any other regime to me feels like, I mean, for a qubit, any state that is diagonal is thermal with some temperature. I can give you a temperature for any state, no matter what it is thermal for a qubit because it's a 2x2 matrix. So I can always find an effective temperature that explains the difference between populations. To me, it has very little physical meaning. I haven't been convinced otherwise. What are your thoughts about that? Very interesting results, by the way. It kind of reinforces my idea a bit that maybe we should abandon trying to shoehorn temperature to non-thermal situations.
I feel that we are getting these, so these look qualitatively the same, meaning that in falling detectors, they will see some finite temperature at the event horizon, at least with these prescription here, which is very different for static detectors, right? So that is one motivation, having different scenarios. And also, and the other reason is comparing with other methods, like the one like this one, right? Like this is like the, like this, yeah, like this is like the under temperature, right? Like, but it corresponds to this freely falling trajectory. This whole.
I'm detecting particles, nothing might have a non-thermal process. And then I assign a temperature to the experiment because I want to compare to other things where there's a temperature. There's no need. You can get the transition rate for the thermal case and compare with the transition rate for the non-thermal case. So what I mean, like forcing a temperature feels. Why?
So you are asking as if whether if I couple some state to a quantum field, will it actually get cooked? Is that your question? Or
some definition of cooked? I don't know.
Yeah. So the.
What I can tell you is that it will not be thermal in general.
Yeah.
So if I blast somebody with very high energy gamma rays and I kill them, they would say I'm being cooked. Yeah, but it wasn't thermal. See what I mean? There's no notion of temperature. I don't know. It's more a philosophical question.
Yeah.
It's not a criticism.
Yeah.
It's more like it feels that we're trying to force the quantity to things that are not thermal sometimes and we confuse.
I mean, yeah, so for example, in the on-root vacuum, we know that it doesn't satisfy KMS state, right? But there are still more like not using detectors, but other frameworks trying to calculate this effective temperature. So my motivation, I think, is just to compare to these other methods that are not detectors, but yeah. Yeah, I agree. So,
the motivation is more about the world. Why do we?
Yeah, I don't know. Why do we do physics? I guess like.
Okay, let's thank Maria Rosa again.
Can you hear us?
Yes, I can hear.
Perfect, and we can hear you. Okay.
All right, next I'd like to welcome Eirini Lima. So whenever you're ready, go ahead.
Can you guys see my screen?
Yes.
Okay. So first of all, sorry? Did you guys say anything? Okay, I will assume no. Okay. Hello, everybody, and thanks for the organizers to allow me to speak online. So as Ireneo said, I'm Carolina Lima, and today I'm going to talk about on sufficient conditions for holographic scattering, a work that was done in collaboration with Sabrina Pastersky and Chris Waddell. So first of all, our work is within the field of ADS-CFT correspondence, and what is that? So in a nutshell, this is a conjecture of a duality between a theory of quantum gravity in d plus one dimensional asymptotically anti-de Sitter space and a d-dimensional conformal field theory, which is a theory with no gravity. Now, if we believe in ADS-CFT, for each phenomenon on one side of the duality, we must have a description also on the other side. And in this presentation, I'm going to show you a bunch of pictures so that you guys understand what these pictures mean. First of all, I'm going to restrict or work on to asymptotically anti-de Sitter space in 2 plus 1 dimensions. And whenever you see some cylinder like this, what I'm doing is that I conformally compactified the space-time. I have a radial direction here, some angular direction there, and a global time here. Sometimes I'm going to show you pictures like this. What it means is that I just took a cut of the cylinder at some fixed global time. So I have the bulk here inside and the boundary on the outside of the circle. And sometimes I'm going to also show some rectangles. In this case, what I have is that I'm just cutting the cylinder and unwrapping and showing just the boundary to you. So in that case, I have this global time here running vertically and then this other angular direction horizontally. So a very important concept within the field of ADS-CFT is the one of Ryota-Kayanagi formula. Basically, this formula, what it does is connecting the geometry in the bulk with entanglement on the boundary. More precisely, what it says is that the entanglement entropy of some spatial region A on the boundary and its complement is going to be proportional to the area of some codimension 2 surface that has to satisfy some conditions. It must be homologous to A, it must have the same boundary as A, and it must minimize the area. So for this spatial region A here in green, with its and here is its complement, this gamma A is this RT surface for A. I hope this is clear. I hope you can understand. Now, another very important concept in my work is going to be the one of entanglement wedge, which is very well connected to the concept of Ryota-Kayanagi RT surface. So the entanglement wedge of some boundary region A that I would denote in the future of this talk as EW of A is going to be the causal development of the region enclosed between the boundary region A and it is Ryota-Kayanagi surface gamma A. So in some situations, there are more than one minimal candidate. If we have more than one candidate, then we're going to choose the entanglement wedge, choose the RT surface, such that this entanglement wedge is as large as possible. Now, as I mentioned before, the entanglement wedge is actually the causal development, but in these figures, what we have is just a cross-section at some fixed global time. So there are some situations in which we have the entanglement wedge in a disconnected phase and other situations in which it's in the connected phase. So here, for instance, if I'm considering the boundary region A to be the union of this region here and this region here, for the disconnected case, what we have as the entanglement wedge, the projection, right, the cross-section would be the union of this blue region here and this blue region there. Now, if we keep enlarging these intervals to get some figure like that, what we see is a phase transition. So the entanglement wedge in this other situation not only contains these regions that are close to the boundary here, but also some region that is very deep inside the bulk. All right, so in order to understand holographic scattering, which is part of the title of my talk, we need to introduce asymptotic quantum test. And asymptotic quantum tests just means I'm considering quantum tests on the boundary. So suppose that Alice has some system A1 in some spacetime point C1 and another system A2 in some spacetime point C2. And we want her to be able to, we want her to achieve some task. So we want her to apply some quantum operation in the joint system A1 and A2, and then send systems B1 to Bob in this point R1 and B2 to Bob in this point R2. Now, the first way that you'd think of how she could apply this quantum operation would be, well, just bring A1 and A2 together, apply this quantum operation locally, and then send B1 and B2 to Bob to reach Bob in this R1 and R2 spacetime points. Now, in this configuration that I chose here, of course, there are some situations that I could choose C1 and C2, R1 and R2, such that what I describe is possible. However, the case that we are looking at here, if I see what is the future of C1 intersection with the past of R1 and R2, I get this causal diamond here. And if I ask what is the future of C2 intersection with both the past of R2 and R1 and R2, what I get is this other causal diamond there. So because there's no overlap between this causal diamond here and this causal diamond there, it means that there's no way that she can apply this operation locally. She cannot just bring the systems together, apply this quantum operation, and then send B1 to and B2 to Bob. So, however, there are some situations in which if Alice only has access to those to the boundary, as I described before, she cannot apply this quantum operation locally. But if she has access to the bulk, then she can do that. So if she has access to the bulk, there are some situations in which she can, the future of C1 and C2 intersection with the past of R1 and R2 in the bulk is not empty, despite the fact that on the boundary it is empty. So more formally, we can define this scattering region on the boundary as the future, the boundary future of C1, intersection with boundary future of C2, boundary past of R1, boundary past of R2. And that is empty. However, in the bulk, the analogous definition in the bulk is not empty, which means she can, using the bulk, perform this quantum task locally, but not if she only has access to the boundary. And this sounds like a paradox, because if we believe ADS-CFT, then whatever operation I can do on one side of the duality has to be able to be obtained also on the other side. So in order to not be a paradox, we need some boundary description of the same phenomenon. And it turns out that the explanation of this phenomenon is that Alice can still do the same quantum operation, but she has to do so in a non-local way. So the explanation is that these regions, the causal diamonds here, which are the future of C1 intersection with the past of R1 and R2 on the boundary, and the other one, which is the future of C2 intersection with the past of R1 and R2 on the boundary, these two regions, these two causal diamonds, are entangled. So more formally, there is this connected wedge theorem by Alex May, Pennington, and Source. And what it says is that if we choose configurations of C1, C2, R1, and R2 in a way that scattering is impossible on the boundary, but still possible in the bulk, then, and if we define these regions V1, which are the future of C1 intersection with the past of R1 and R2 on the boundary, and V2, which is the future of C1, C2 intersection with the past of R1 and R2 on the boundary, then the entanglement wedge of V1 and V2 has to be connected. There is, if I have on bulk only scattering, then the entanglement wedge of V1 and V2 is connected. So this is an illustration of the case in which this scattering region is not empty, and indeed the entanglement wedge of V1 and V2 is connected. And this is an illustration of a case in which this doesn't hold, so there is no point here. There's no scattering. The scattering region in the bulk is empty, so we cannot say much about the entanglement wedge between V1 and V2. In this case, it's disconnected in this particular drawing. So schematically, what the connected wedge theorem says is that if the scattering region is not empty, then the entanglement wedge between V1 and V2 is in the connected phase. Now, what we want to address in this work is is regarding the converse direction. Is that true as well? Like, is it true that if the entanglement wedge of V1 union V2 being connected imply that the scattering region is not empty? Well, if we have period yes, this is true. So for the period yes3 case, we have an if and only if statement for the connected wedge theorem. However, in general, this isn't true anymore. So what we wanted to do is to basically modify this statement a little bit in order to get some statement with a converse. There are basically two ways to modify this. I can change a little bit the right-hand side. In particular, I worked with some other collaborators in modifications to this right-hand side. If you're interested, you can check this work here. But in this talk today, what I'm going to do is talk about modifications to the left-hand side. So instead of considering the scattering region, I'm modifying the scattering region to some other region in the bulk. Previously, this author here in this work, they had proposed they had a conjecture for this modification in order to obtain some if and only if statement. So they defined this SE region, which is the entanglement wedge of U1 union V2, intersection with the entanglement wedge of W1 union W2. So V1 and V2 are defined exactly the way I defined before. Now, W1 and W2 are analogous, the analogous versions in the final points. So what is W1? W1 is the intersection between the past of R1 and the future of both C1 and C2. And W2, similarly, is the intersection between the past of R2 and the future of both C1 and C2. The conjecture that they had is that this new region, this SE region, being non-empty, is equivalent to the entanglement wedge of V1 union V2 being connected. Okay? Now, we basically found counterexamples to that, and the counterexamples that we found are based on this conical defect spacetime. And what is this conical defect spacetime? It's basically if you take the cylinder, the pure ADS case, and just cut a wedge and then glue the sides together, you're going to obtain some conical defect spacetime. The spacetime interval for it's given by this, and in this M parameter runs in the open interval between -1 and 0. And if you look into this spacetime interval, you can see that when we take M to -1, we're going to recover pure ADS3. And when we take M equals to 0, you're going to recover a BTZ black hole. Now, let's look again into the conjecture that they had and the definition of this region that they had. If you look into that, you see that entanglement wedge, the region that they define here is very symmetric between the entanglement wedge of U1 union V2 and the entanglement wedge of W1 union W2. However, the conjecture itself is not symmetric, has less symmetry, right? It's just talking about the entanglement wedge of U1 union V2. So to start off, we could find some counterexamples based on the fact that this right-hand side is not symmetric. So, and we believe that the reason that it's not symmetric is, if you remember, when I mentioned the connected wedge theorem, it wasn't symmetric either. It was talking about just the right-hand side. And that makes sense because when we have pure ADS3, if the entanglement wedge of U1 union V2 is connected, so is the entanglement wedge of W1 union W2. And similar, if it's disconnected, the other one is also disconnected. However, in the conical defect spacetimes, as I just introduced to you, this isn't true anymore. So there are some situations in which one of them is connected and the other one is disconnected. So we can have any possible situation. So therefore, we decided to modify this conjecture of theirs to something a bit more symmetric. So we still keep the same definition of region on the left-hand side. And then on the right-hand side, we add this extra condition that the entanglement wedge of W1 union W2 has to be connected. And just to remind you guys, because I mentioned that the connected wedge theorem is already an if and only if statement in the case of pure ADS3, this new definition of region of theirs has to reduce to just the scattering region in the case of pure ADS. Otherwise, there's no reason to try to to modify this theorem to get something that is always true if it doesn't reduce to something that we knew that it was always true already, right? Now, even with this modified version,
you have 1 minute left, so.
oh my God, okay. But this is almost there. So even with this definition that I have, I still can find counterexamples for the modifying version. So what we see is that there are situations in which both of them are disconnected and S is non-empty or empty. There are some situations in which one of them is disconnected, the other one is connected, and I have either non-empty or empty. SE. So what we actually see is that the only situation in which is always true is that if both are connected, then we have SE to be not empty. So we did an extra modification. So what we did was this SE tilde. So we took the entanglement wedge of V1 union V2 and subtract the individual wedges, entanglement wedge of V1 union the entanglement wedge of V2, and similar to the entanglement wedge of W1 and W2. And what we could see is that with this modification, we found an if and only if statement. So we proved that this holds. If you look into this forward direction, it is actually trivial because consider, without loss of generality, that this entanglement wedge of V1 union V2 is disconnected. If this is disconnected, it means that the entanglement wedge of V1 union V2 is equal to the entanglement wedge of V1 union entanglement wedge of V2. So this is going to be empty. Now, the other direction is more complicated to prove. Now, as for the quantum information interpretation, we know that the original region for the scattering region, we had some associated boundary quantum task. Now, is there any quantum information interpretation for this modified region? Well, for the one that was proposed by the other authors, what we see is that if we consider that Alice has access to V1 union V2 and Bob has access to W1 and W2, and Eve, some adversary, is trying to intercept a message that Alice is trying to send to Bob, if SE is not empty, then it's impossible to intercept. Basically, it's guaranteed that it's like perfectly secure protocol to Alice, for Alice to send a message to Bob. But for our particular modification, this is harder to interpret in terms of content information because we remove the wedges that connect to the boundary itself. So, okay, as a summary, we established an if and only if generalization of the connected wedge theorem. However, the bulk region cannot be interpreted as scattering anymore, or we lose this interpretation in terms of content information. Thank you. Questions, and sorry for going a little bit over.
Okay, I think we have time for one question. So, okay. Yeah, Rob, go ahead.
Yeah, hi, thanks. Very intense talk, especially at the end. But I'm just wondering, so the thing with the conical deficit that you show, that's a BTZ black hole, then takes positive values. So did you look at that case? Or
Say
maybe
again,
it's that I
you're
missed
saying,
it.
no, we didn't look into the BTZ. Are you asking about if we looked into the BTZ black hole?
Yeah, that's
yes.
right. Because that R squared minus M.
But so yes and no, let's say. Rob and Jackie and other collaborators have looked into that. In this case, in these modifications to the right-hand side.
Yeah.
Now, if you're asking me if I looked into the modifications to the left-hand side, which are the cases here, no, we actually introduced some extra. I mean, the authors of this paper, and we kept this assumption that there's no black hole there.
Sure, but why, like, is there a reason not to? Like, why not?
Yes, yeah, it makes the entanglement wedges, the behavior of the entanglement wedges is way more complicated, and yeah, it disturbs the behavior. Basically, the proof for the other region, the other direction, involves rational Dewey equation and some behavior that is going to be disrupted when you introduce this black hole there.
Okay, so is
I can explain better.
Possible but painful? Is that the idea?
No, I think we would
Or
have
not
to,
possible?
not this one, not the one that we propose. Something else, maybe, hopefully, maybe.
Okay.
Awesome. Okay, let's thank Carol again.
Sorry about this.
All right, I'd like to welcome Everett Patterson. So whenever you're ready, you can go ahead.
Terrific. Thank you. Thank you so much to the organizers for organizing this event for its second edition. I'm really excited to share with you today some recent results that I've had the chance to work on with Sija and Rob, whose name is slightly cut off here. And basically what this work is what we're going to look at here is revisit the canonical problem in RQI of entanglement degradation, but from the perspective of quantum reference frames. And a little disclaimer is the title of this talk is very different from the title of the manuscript, which you can find on the archive. So if you're looking for that, there's a QR code, here's the link. But the title emphasizes the entanglement transference, which we'll get to at the end. And this is maybe a little less RQI as a flavor, so I tweaked the focus of this talk to hopefully be of greater interest to this audience here and online. So just to kind of set the stage quickly, I wanted to review what I think of when I think of RQI, especially RQI in the discussions that we have here in Waterloo. So I've identified classical relativistic quantum information examples, such as GIE, or the entanglement harvesting protocol, quantum energy teleportation, or this entanglement degradation result that's about 20 years old that kind of helped kickstart interest in RQI. And what I want to emphasize about this is that they all kind of emphasize the entanglement component of the quantum systems. And this is a parallel to standard quantum information where people talked a lot about entanglement, but there's a lot more to quantum theory, and we've had the chance to explore some of that even in the sessions today. So what I've called new RQI examples include other quantum resources, relativistic quantum resources, magic, contextuality, which we'll hear about in a bit, causal order, holography in RQI, and what I'm very excited about, quantum reference frames. And specifically, this talk, as I mentioned, is going to take quantum reference frames from these newer aspects of RQI and try to apply it to entanglement degradation from these older or classical aspects of RQI. Okay, so I'll give you a little spiel about quantum reference frame, a little spiel about entanglement degradation, and then there's a lot of cool results that I'm hopefully going to get around to and be able to share with you. So why quantum reference frames? What do we want to think about when we're thinking about quantum reference frames? So kind of the motivation here is that when we talk about physics, we're always trying to describe things, physical quantities, and we tend to do that relative to some reference frame. So in the context of general relativity, which is where classical reference frames are really important, we're talking about rods, we're talking about clocks to measure distances and time. And we know that these, the values that you'd obtain might be different depending on your reference frames. But there's kind of some underlying space-time, some space-time quantities that are left invariant regardless of the reference frame that you choose. And so people have been asking, well, what happens when we try to apply these sorts of ideas to quantum theory, looking at the relationality aspect of describing systems relative to other systems. And this is not something that's kind of built into quantum theory in general, right? Typically, when we're doing quantum descriptions, quantum measurements, we've got the quantum system, and then there's kind of like a Heisenberg cut, and then we've got our macroscopic classical observer that's describing the system. And people want to understand, well, what if everything's quantum, which a lot of people like to believe. How can we describe quantum theory relative to itself? And a natural kind of hope that might arise from quantum reference frames is to get some insights into quantum gravity. So kind of quantizing this GR side, or getting some relationality on the quantum side. And specifically, there are many approaches of quantum reference frames that have been being developed over the last decade especially. And today I'm going to focus on the perspectival approach, which is largely developed by people with connections to Vienna and also actually to PI at times by the authors here. And the key features of this perspectival approach to quantum reference frames is that it's describing, say, a multipartite quantum system relative to components of its components of that system, so relative to its subsystems. And there's the additional assumption that the subsystem to which we're describing the relative degrees of freedom cannot perceive itself to be superposed. So in this cute drawing from Giacomini, Flaminia, Esteban, and Cheslav's paper, we have system ABC, which is a joint system, and from the quantum reference frame of system C, A might be in a quantum superposition, but we might want to ask, okay, well, how would A perceive the rest of the systems? How do we transform between them if A cannot perceive itself to be in a superposition? And to do that, we need to talk about quantum reference frame transformations. And so a transformation from the perspective of B to the perspective of A is going to take B's description of state A and map it into some description of state B relative to A. And if you have system C, D, E, F, all of those will transform by some. This is effectively kind of a controlled unitary. And I'll give you a concrete example that I've taken from Carlo Cepolaro and collaborators' paper, because I think it's a really, really good example. And it's a 3 spin 1/2 qubit system. And the system is described from the perspective of C, and we have A in a superposition and B in its ground state. And in this case, if we want to describe the same system, but from the perspective of A, we're going to be applying this quantum reference frame transformation. So what's happening is if we're trying to move from C to A, so we're going to look at the state of A. If it's in its ground state, spin up, we're going to do nothing, right? We're going to act on the identity. But if it's in the down state, we're going to flip the remaining system, B. And so when we do this map, the state that we end up finding is the one here on the right. So from A's perspective, C and B are both superposed, and in particular, those superpositions are entangled. We get this kind of bell-like state. And something that jumps out at you here and was noted in previous work was that coherence in one perspective can be transformed into entanglement in another. And in particular, here on the left, there's zero entanglement and kind of maximal coherence. And on the right, there's no subsystem coherence, but there's maximal entanglement. And this was quantified. So this was kind of the big contribution of Carlo and collaborators' paper, was they were able to quantify this result and say quantitatively that the sum of subsystem coherence and entanglement in one reference frame is invariant across quantum reference frame transformation. Really cool. So we kind of had this background of quantum reference frames. We thought it was really cool. We wanted to apply it to something with a bit more of an RQI flavor, and we chose the problem of entanglement degradation. And part of the motivation was here we can work, there's an example from 2006, one of the original papers, where they're working with fermionic fields, and that allows us to have kind of a natural mapping between our spin 1/2 systems that Carlo and people had looked at with the modes of the field, of our fermionic field. And just quickly, so that we can get to the cool, juicy stuff, the idea of entanglement degradation is that two observers, Alice and Rob, share a pair of entangled field modes, so kind of like a Bell state in some like inertial, in some kind of inertial mode. So you can think of it as Minkowski. There's Minkowski modes. There's a bit of an asterisk there, but I'm going to gloss over that for now. And if Rob undergoes uniform acceleration, then we're going to have to describe his modes not in terms of this inertial reference frame or this inertial perspective, but rather in terms of Rindler modes. And in particular, this, his initial modes are going to be expressed as a product of right wedge and left wedge Rindler modes. So we'll have Rob in the right wedge and some anti-Rob observer in the left wedge. And the computations have been done. It's pretty straightforward. The state that you're going to end up with is described here, where lowercase r is parametrizing the acceleration. So it's going to go from 0 to pi over 4 with as increasing acceleration. And we have our three systems, Alice, Rob, and anti-Rob. And if we want to describe the entanglement between Alice and Rob, but we now kind of have this third system, well, what are we going to have to do? Well, we're going to have to trace over anti-Rob to be left with our Alice-Rob system, which we do. And when one does that, we're going to get a mixed state. And so to compute the entanglement of that mixed state, the authors in the 2006 paper used entanglement of formation. And what you see is that this entanglement decreases monotonically as the acceleration increases. Cool, so entanglement degradation, this is what you should have in mind. Now, we wanted to take the quantum reference frames, apply it to this setup, and see what happens. Honestly, and I'd say we didn't really know what to expect, and I would say we were very fortunate to get a lot of cool things. So first off, we're starting with the same setup, so we have the same initial global state, but you'll recall that the perspectival approach does not have a notion of global state. Everything is relative. So we need to come up with some mechanism to create perspectival states from this global state. And to this end, in our work, we constructed a very reasonable, I think, approach of defining such perspectival states. So I'll give you the example for the perspective of anti-Rob, because we want to look at the entanglement between Alice and Rob. You look at the third register of all these states, which is anti-Rob state. If it's 0, you do nothing, right? Because that's what anti-Rob would be seeing. And if it's a 1, you're going to flip it, right? Because we want anti-Rob to be in not perceiving itself to be in a superposition. So when you do that, you get the state here. And more generally, you can take any 3-qubit system. And what you're going to see is there's kind of some collisions between kind of symmetric states in the global space that end up being joined together in the perspectival state space. Okay, so we have our global state, same as before. Our newly constructive perspectival state, this state is pure, so we'll just use entanglement entropy to compute the entanglement here. And when we do that, we get something very reassuringly that resembles what the literature has found for a long time. The entanglement degrades as the acceleration increases. And a kind of cool thing that we hadn't expected was that this entanglement entropy of the perspectival state is actually exactly equal to the entanglement of formation of the mixed state obtained by tracing over this initial global state. So it seems to suggest maybe a deeper connection between the global state properties with the perspectival state. We were hoping for something that was qualitatively similar, but we were actually able to show that mathematically these are exactly the same. Now, a big part of the motivation for the quantum reference frame stuff was that we don't want to look just at entanglement alone. We want to consider entanglement and subsystem coherence. So we decided to take a peek at that here as well. And what we found was, in the perspective of anti-Rob, the coherence of Rob's subsystem increases. And we kind of maybe had that intuition that maybe the entanglement's going somewhere. Is it possible that it's being transferred into coherence? That's kind of what the quantum reference frame story might indicate. And so here I have the entanglement dashed yellow and the coherence dashed red. And when you add them up together, we're going to get the solid red, and it's exactly 1. So the entanglement that is lost is exactly offset by this creation of coherence as acceleration increases. Now, this is just one pair of subsystems. In particular, it was Rob's coherence, but there's also Alice for the system. So here's it all together, entanglement, same color. Alice's coherence system is the dashed blue, and then you add it together to get the solid line. So solid lines are always sums of entanglement plus coherence. We see that it offsets some of the entanglement, but not completely for Alice's subsystem coherence. And we know that this sum, these solid lines, should be invariant under quantum reference frame transformations. So we computed these values for the other perspectives as well, although these aren't quite as interesting in the context of entanglement degradation. I have them here. And you can see that the solid lines, so this is Alice's perspective. There's a solid line in common with anti-Rob, and the other solid line is in common with Rob. And Rob and anti-Rob also have a solid line in common. So we have that the sums are indeed consistent between any two pairs of quantum reference frames. But here we got kind of lucky in making an observation, which was the 2006 paper actually already had these curves, except in their paper it was also entanglement entropy, but it was not of a it was not of a two of the subsystems. It was all three. It was a bipartition of all three. And so when you look at the plots, you say, yeah, these look kind of similar. But once again, we wanted to know exactly, is this indeed an equality? And this is where the title of the manuscript comes from, Entanglement Transference, where we found that, in fact, it is exactly the case that this entanglement entropy of the global state across this bipartition is equal to the sum of entanglement entropy and subsystem coherence in the perspective. So there's this connection between the global state and the perspective states. And moreover, there's a symmetry here, right? We can swap A and B. It shouldn't change anything on this side. But if we swap A and B here, we're going to get another E plus C, which is exactly the result that Carlo Cipollaro and collaborators had found. The sum is equal across quantum reference frame transformation. So there's maybe an additional motivation here from a global picture that had not been previously studied. Unfortunately, this is not true for all 3-qubit systems. It's restricted to what we've named or dubbed these parity states. So parity, the even states have an even number of ones. The odd states have an odd number of one in their basis terms. They have this nice geometric representation. And this arises because of the perspective assignment procedure. So this kind of, the collision that I described earlier would kind of mess up. It would kind of combine these even and odd states, which would affect this relation here. So with that, I want to leave you with my concluding remarks. The biggest of which is I think that quantum reference frames are really interesting and useful, and I think they have a lot of applications to new areas or existing areas of quantum physics that have not been considered previously. In particular, we showed that there's a new kind of interpretation of entanglement degradation if you look at it from the perspectival framework. We still have that exact same degradation of entanglement, but if you account for the coherence, you see that there's some invariant quantity across the non-inertial frames. And outside, beyond the RQI framework, we have this relation between global entanglement entropy and then perspectival sums of entanglement and subsystem coherence. And these lead to some open questions that are of interest to us, and maybe some might be of interest to you, or maybe there are other places that you can foresee yourself applying quantum reference frames to give you insights. So one thing that we didn't consider all that much in this problem was the role of an event horizon. Will that affect anything in how we should interpret the quantum reference frames? What about other resources? So I showed you that classical RQI results focus a lot on entanglement. Here we've added coherence, but there's so much more. How do those behave under quantum reference frame transformations? What about the other approaches to quantum reference frames? Can they be related to this? Are there similar results there? And that final question is, where else can we apply quantum reference frames, and what other insights can we gain from those places? Thank you very much.
Great, thank you. I think we have time for one quick question. Nothing on YouTube. Okay, if there's no questions, then let's thank Everett again, and we'll have the coffee break now. So. Thank you.
All right, welcome back everyone. We'll now proceed with the final session of today's circuit, and we'll begin by hearing about harvesting contextuality from the quantum vacuum from, well, Dr. Sanchit. Please, the floor is yours.
Thank you, Ahmed. Hi everyone, I'm Sanchit. I just finished my PhD here at Institute of Quantum Computing in University of Waterloo. And what I'm presenting today was some work done over the last year with Carol and Maria, whom you have heard from in the previous session. So, well, we all know in this audience that the field of the vacuum field is not featureless, and there are correlations that can be accessed using localized probes. Everyone knows about entanglement harvesting, where detectors which are spatially separated can become entangled purely through these local couplings. And then, as you may have heard in a couple of previous talks, there's some growing interest in harvesting more esoteric things, newer things from the quantum field like magic, stabilizer, Renyi entropy, etc. So this paper which came out in 2025, which harvested magic from the field, got us thinking whether we can connect that to contextuality. So if in the audience anyone is not familiar, contextuality is a phenomena where we talk about measurement outcomes, the measurement statistics, and we see whether those can be described in terms of a classical description. So contextuality involves contexts, which are basically just a set of commuting observables. And there is a notion of a non-contextual model. So this is the classical notion, where each observable has some value which is independent of the context. So let's just think of this very simple scenario. I give you a grid of 3 by 3. And let's just say I'm telling you that every row and every column here is a context. And you need to fill in the values. So let's just say these are observables. You'll fill in the values that you expect these observables to take. And they all take plus or minus 1 values. And I'm giving you this bunch of constraints that for each context, so each compatible set of observables, their product must be as labeled. You can try and do this. You can spend 2 minutes, and it's very obvious that this is something which is impossible. Because if I were to fill in plus and minus 1s, which respect everything, then if I multiplied every row and every column, I'm effectively multiplying every observable twice. Everything is squared. The answer must be positive. But clearly, the product of these 6 numbers is not positive. So classically, you just can't fill in these boxes which respect all these constraints if you fill them in independent of whether you are filling in a row or a column. What I mean by that is, let's say I allowed you to flip this one particular box between plus and minus 1, depending on whether you look at it as part of a row or as part of a column. In that case, you can then satisfy all of these constraints, and hence this will work. So if you were to fill in the value depending on the context, it would work, and hence that is a manifestation of what we would call contextuality. Quantum physics can be contextual. You can have observables which fit these constraints. So every row and every column commutes here, so they are compatible measurements. And you will notice that these Pauli operators all multiply accordingly. So all the rows multiply to plus identity, and all the columns multiply to minus identity. Meaning with these Pauli observables, given any state, if you looked at the expectation values, that's a way of filling in these boxes which satisfy all these constraints. So quantum mechanics is contextual, and this is a way in which quantum mechanics is inherently different from a classical description, classical probability description. I have given you the most well-known textbook example, which is more of a yes or no question, but you can also have this as a state-dependent property, where some states show contextual measurement statistics and some don't. And we are interested in a quantification of this property, so we'll look at a state-dependent way of computing contextuality. Before I go to that, the motivation behind this is this known connection between Wigner negativity and contextuality for the case of Heisenberg-Weil operators. So in the past decade or so, there have been a couple of important results studying the contextuality with respect to the generalized Pauli group. And it was shown that contextuality and Wigner negativity, which is called magic, as Jiayue mentioned to you all, go hand in hand. So when this paper came out about harvesting magic from the vacuum, it got us thinking about this particular connection and whether we could use that connection and do a quantitative exploration of harvesting contextuality from these detector states. So for it to be quantitative, we need to compute, we need a measure of contextuality, and we use what is called the contextual fraction. So since contextuality explicitly depends on the measurement scenario, let's fix the measurement scenario and then just write down the observed statistics. So a reasonable, well-behaved quantum measurement statistics will be called an empirical model, and it is effectively just a probability table. So it's a table with probability distributions describing the statistical data of the measurement outcomes. And since it's all just probabilities, I can decompose it into linear convex combinations of other probability tables. And I can classify certain types of probability tables as non-contextual. I can check whether they fit the classical description or not, and if they do, they are non-contextual. So I do this sort of a decomposition, and then what I do is I try to maximize the weight of the non-contextual part of the probability table. So what that does is whatever is left over is effectively the probability data which I could not have explained with my classical description, and hence that gives me a measure for how contextual this probability data is. So that is called the contextual fraction. As the name suggests, just the fraction of measurement statistics that you see which cannot fit this classical description that you have. And since it's all a convex constraint problem, all linear constraints, you can compute this quite effectively using a linear program. So you can write down a linear program which does this maximization, and what you get out of it is a robust measure of contextuality. So this is what we use, and with this measure, if you see that contextual fraction is 0, it means there was no part of the data that you saw which could not be explained with these classical descriptions. So you'll say that it's non-contextual. But if you get a non-zero part of this data, you say that there's a non-zero contextual fraction. So we set out to ask whether two localized detectors interacting with the Minkowski vacuum can become contextual. So we choose two Q-trit Unruh-Dewitt detectors. They are initially in a non-contextual product state, and they couple locally to a scalar field. We measure the contextuality of the post-interaction detector state using the contextual fraction as I described for this Heisenberg-Weil scenario, because this connects to magic. And in parallel, we also track the Wigner negativity just to understand this connection better. So I won't be preaching to the choir here. Everyone understands the setup. I have just included this schematic to clarify the notation. So T would be the switching time. D is the distance between the detectors, and R is the spatial smearing. We are considering Q-trit, so we have 3 levels which are equally spaced. Omega is the energy gap, and we choose these values in a way that a space-like separation is maintained between the two detectors. And as I mentioned, we'll be doing this for the Heisenberg-Weil scenario. So this is the generalized Pauli group, which has 2 types of operators. There's a Z operator, sometimes called the clock operator, and the X operator, sometimes called the shift operator. So these are the generators of the Pauli group. And using these generators, you can generate this Heisenberg-Weil group, which can be labeled by these vectors. So for 2 Q-trits, our group will be labeled by vectors belonging to Z3, 4. So basically, 4 entries, each belonging to Z3. And this is helpful because these symplectic vectors give us an insight into the structure of the group. For example, you can look at the commutation relationship by considering whether the vectors are orthogonal or not. So there are 40 contexts, 9 commuting operators, and one of the important results here is that non-contextual value assignment must be linear. So that limits the number of these global deterministic assignments that we must deal with in our constraint optimizing problem. So that gives us 81 deterministic models, which keeps the linear program fairly small. So this is so once you have the machinery for calculating the contextual fraction, now you need the final state. So that involves finding a couple of smart collaborators who can do 30 pages of integrals and hand the final state to you. So this is the detector state up to second order in perturbation, second order in lambda. And it has a few terms. I have just roughly labeled them. So we have L, which is local excitations, then the non-local excitations. Q is the local coherence terms, and then there are some non-local coherence terms. So one of the things which will be relevant will be the reduced states of one of the detectors. So just to clarify, this is the 2 Q-trit detector state. This is now the reduced 1 Q-trit detector state, and only the L and Q terms turn up here. So the known connections between Wigner negativity and contextuality for this measurement scenario tells us that if there is Wigner negativity in the reduced state, then the 2 Q-trit state must have contextuality. And since the state is so simple, we can actually write down just a handful of inequalities, and we can check when they will be violated. So we can check when there will be Wigner negativity. And it turns out that it has to be that L is smaller compared to Q. So in that case, you will see Wigner negativity and hence contextuality. So that should give us an idea for the underlying mechanism, what's going on here. So when this is like two competing terms, this is the local coherence term and the local excitation terms, and the computation between them tells us when the onset of contextuality will be. So now here are the results. So this is the main contextual fraction versus the gap plot, and we have plotted this for a series of distances between the two Q-trits. So a couple of important points here is this purple asymptotic line is when they are so separated that we can just replace the state with just the reduced state of Alice and reduced state of Bob. We also consider this situation where, let's say, one of them, let's say Bob, did not let their detector interact with the field at all. So that remained in the ground state and only Alice's state evolved. And then these other dotted ones are for various distances. So as you can see, as the distance reduces between them, you get more and more contextuality. It collapses onto this infinite distance between them scenario. And when you have both of them interacting their detectors with the field, that is significantly larger than if only one of the detectors interacted with the field. So this is for large detectors where the radius or the spatial smearing is comparable to the switching. And then for small detectors, you see a slightly different trend where you see some higher amounts of contextuality which is harvested or extracted, I should say. And we see that it also persists at omega equal to 0. Then we can compare this to Wigner negativity, and we already expect these trends to be exactly mirroring each other. So, and that's what we see. So that is a dynamical illustration of this equivalence. So whenever you have non-zero contextual fraction, you also have non-zero negativity and vice versa. And finally, because we are using Q-trit detectors, you can have multiple types of internal dynamics. And we saw that the Heisenberg-Weil transitions generally give higher contextual fraction as compared to the SU2 transitions. And it could possibly be because it's easier to generate the coherence in the Heisenberg-Weil transitions because of the degeneracy. So this question was, I think, posed to Jiayue during her talk, so I just thought to include this. That whether contextuality is being genuinely harvested here, and within the framework of what we have just shown you, we can't say. I can't distinguish between whether it's a dynamical property or a kinematic property of the system. So this will require a more nuanced treatment to actually eliminate the scenario in which you are just becoming contextual without harvesting anything from the field. So in summary, two Q-trit detectors, which are initially non-contextual, can acquire contextuality while after coupling locally to a Minkowski vacuum. It is non-monotonic in the gap. It grows towards the point-like limit. It scales as lambda square and decreases with separation. So finally, I can leave you with this conclusion that contextuality is a resource that can be, maybe I should not use the word harvested, but can be obtained when the detectors interact with the quantum vacuum. And it's controlled by the discrete Wigner negativity, extending our understanding of this harvesting beyond entanglement and magic. Thank you.
right, thank you so much, Sanchit. Yes, can we open up for questions, please?
So you said that it's open whether it's harvested or generated. I think there's an argument to be made that is not harvested, right? Because, for example, if you think of Wigner negativity, the vacuum state is Gaussian. There's no Wigner negativity there whatsoever. So certainly it's not that in the notion of harvesting that the resource exists in the state and then you get it in new states. I would say that both in the case of magic and contextuality, it's most likely generated through the interaction than harvested. I would say that there are strong arguments, perhaps. What is your opinion on that? But strong arguments to say that it's not harvested. Maybe the word harvested should not be used for this.
Yeah, the word harvested should not be used here. And I agree that there's a strong argument that it is probably the dynamics, because you can have local unitaries which are non-Clifford act on the detectors, and that will give you contextuality. Yep. That is part of the reason why we have done this sort of different types of separation and whether only one interacts or the other interacts. But yeah, we'll need to probe this more to really understand what's happening.
I would like the word generate.
Yeah, okay.
Just related to that, have you checked what happens if you replace the quantum field by a classical field in interaction, and whether it's possible to also obtain, for instance, contextuality?
We have not.
Because if you just put a given classical configuration, it's like if you say that you can also generate contextuality there, then I guess it's very clear that I don't know, what you're seeing is not from the vacuum, but just from the interaction itself, I would argue.
Yeah, that is not a direction we had thought of. The direction we were thinking to answer this question is to couple it, to have like a discrete system where you can actually talk about the contextuality of your state which you are extracting. So I can't talk about the contextuality of the field, but maybe if it's a photonic system or something, a harmonic oscillator, I can, and then say whether it can be extracted. So that's the direction we were thinking.
Why do you say that you can't talk about the contextuality of the field?
Well, I don't know how one would do it. Yeah.
There are a couple studies in this direction, yes. They've shown like violations of Bell inequalities by explicitly giving some observables of the field that can be measured and things like this. So it's, there are definitely some ways of talking about contextuality and some other,
Okay, yeah, I think that's worth looking into. Yeah.
Thank you.
Thank you.
All right, if there are no other questions, let's please thank Sanchit one more time.
Just unplug?
Yeah. So this is the HDMI, the mic, and the clicker if you can. Sorry, I can unplug this here? Yeah.
Suck.
Microphone. So this is working here? No. And then the one with the USB dongle if you want to use the clickers.
All right, let me see here. I'll just hold the microphone. Okay.
Sorry, for realizing off.
Let's try this.
Yeah, if you can just. Maybe a quick like Windows key and P, just to make sure you're allowed to project on different screen. No, Windows key. Yeah, here we go. And then like duplicate or extend your call.
Yeah, it's duplicate.
Oh, I see something. Something is detected. What you can do if this starts to internet, is like send to the presentation user computer.
Okay. Let's get this up.
Do you have have a USB-C port?
Yeah.
Maybe you can try to connect with it.
No, I don't have a.
You have USB-C? Okay. Okay, I thought actually, do you mind presenting first? And then I'll set up a. Okay.
Good.
Yeah. So I thought, and then if you could just like
Send
shoot
it.
me the slides, I'll set up on my laptop.
Oh, okay, perfect.
No worries.
Do I need to connect something for this?
Well, if it works, maybe.
It works.
Oh,
Yeah, let's carry on. It showed up for a sec, yeah. Maybe the cable. Not doing anything? Do you have USB-C? Like maybe, yeah, let's just try through the thing here, because it was just working.
I have to do something here, like duplicate.
No, I think. Oh, there we go. Okay. And then just set up the mic, like, okay, colors. All right, thank you for bearing with us. All right, we're all good. We're all good.
Okay.
So now we'll hear from Aitor Avila, who is going to tell us about causality of smear particle detector models. Aitor, the floor is yours. Thank you.
Thank you for the presentation, and thank you to the organizers for accepting my talk. Today I'll be talking about causality in particle detector models, based on work that we've been doing with Ireneo James Membrere and Professor Eduardo Martín-Martínez, which we hope that will be ready to be published very soon. Particle detectors are non-relativistic quantum systems that couple locally to quantum fields, and they are useful because they give us an operational way of proving the fields without having to implement projective measurements of the field observables. They appear in many different contexts. In fundamental QFT, they provide an operational formulation for the Unruh and Hawking effects. They are also used in experimental setups in quantum optics and superconducting circuits. And most importantly for this talk, they are widely used in relativistic quantum information, for example, in communication protocols, entanglement harvesting, or in some studies of quantum information processing. So the motivation is clear. If these models are going to be used to discuss relativistic information protocols, we need to understand whether they themselves respect relativistic causality. And the main message of this talk will be that signaling remains controlled by field commutators. In particular, we work with the simplest Unruh-DeWitt model. In our setup, we have two detectors, which we label A and B. And in this model, the interaction Hamiltonian in the interaction picture of the detectors is given by this linear coupling, where lambda is the coupling constant, chi is the switching function, which controls when the detector is switched on and off. Mu is the detector monopole operator. In our case, as equation 2 shows, we are working with a two-level system where omega is the energy gap between the two energy levels, and sigma plus and sigma minus are the respective raising and lowering operators. And then the field part is the smeared field operator, which means that instead of coupling to the field at one point, the detector samples the field through a spatial profile defined by F. And then having defined these interaction Hamiltonians, if we assume that both detectors are commuting in the same, in a common inertial frame, then we can say that the interaction Hamiltonian of the system is the sum of the two contributions. Then after both interactions have happened, we know that the final state of the system is given by equation 5, where ρ0 is the initial state of the system, and U is the interaction picture time evolution operator. We will expand this operator using the Dyson series, and this will give us a perturbative expansion of the final state of the system. We've said that we assume both detectors at rest in a common inertial frame, but moreover, we are going to assume that detector A is switched on before detector B, or interacts before detector B. And that allows us to interpret this setup as a sender-receiver protocol. And now the question is, how can the interaction of detector A affect the final state of detector B? And to isolate this final state, we will trace out the field and detector A degrees of freedom. And finally, order by order, we will define the signaling terms as all the contributions in this final state, which contain both coupling constants. That is at least 1 power of lambda A and 1 power of lambda B, because these are the only terms that can encode signaling or an influence of A on B. By doing this, the first non-vanishing signaling contribution that we find is at second order. This has been studied in many previous works. We are interested here in this field commutator that is appearing in the field part. In our setup, detector is going to be switched on in an interval 0t, and detector B is switched on in an interval of the same duration but later in time, separated by delta. This means that the switching functions are top hat functions. And then the distance between the detector centers is going to be L. We know that if the detectors have compact support, we have a causality criterion for this setup, which is if the full support of the detector's A's interaction is a space-like separated from detector B's interaction, then by microcausality the field commutator vanishes, and hence the second order signaling term that we found vanishes as well. However, for a non-compact smearing, in our case we will work with a Gaussian smearing, this is not true in general. Our commutator is not going to be 0, even when the detector centers are outside the light contact region. And we can now plot the second order term to see this effect. But first we need to fix the initial state of the system. We will assume an initial product state between detector A, detector B, and the field. For the field, we are working with a coherent state, which can be defined with the displacement operator. And in particular, we work with a distribution which is an spherical Gaussian. And then for detector B, since it has this receiver role, we choose a ground state. And then detector A, for numerical reasons, is prepared in a real superposition of its ground and real state. With this, we can now plot the second order estimator, which gives these plots. This is the estimator that we are plotting. Here, all variables are expressed in terms of delta. And what we are plotting is the signaling that reaches detector B as a function of the distance between the detector centers for three-dimensional cases. Here n is the number of spatial dimensions. Here are some of the parameters that we fixed. And sigma is the width of the Gaussian smearing. So we indeed see how the signaling term or the commutator is not 0 outside the light contact region, the light contact band. But this leakage is concentrated around that band, and it decreases, it vanishes as the smearing scale decreases. This is what we expected. And now, before claiming anything at general order, we wanted to see what happens at third and fourth order in this setup. The second order term its field part was only a field commutator, and that's why the causal interpretation was very transparent. At third order, the signaling term is separated into two sectors depending on the powers of the coupling constants. And the important thing is that in all of the contributions to this order, the field part always depends on objects of this type, a product of one-point functions and a smeared AB commutator. These are the explicit third-order estimators that we found. You can see how these commutators appear. Here Cn is the AB commutator. And then at fourth order, the signaling term now splits into 3 sectors. It happens that one of these sectors, for the setup that we are considering, just cancels out. And the other 2 introduce new field objects, such as 2-point functions or the anti-commutator. But the important thing is that, again, we find this commutator appearing in all the different terms that we have. We do not show the explicit fourth order estimators because they are rather long, but we can now plot all these terms to compare their behavior. This is what we do in these plots. So here we are plotting all signaling contributions up to order 4th, all non-vanishing signaling contributions. It's important to say that these curves are being independently normalized against their maximum. So here we are not comparing any physical magnitude. We are only comparing shapes and support. The plot is the same as before, the signaling that reaches detector B as a function of the distance. And what we are seeing is that indeed there are new shapes. Not all contributions have the same shape as the second order one. But the leakage, there is no new leakage region or no new mechanism that introduces signaling that was not there at second order. This can be better seen in this plot, which is a close-up of the previous one in a logarithmic scale. We see how asymptotically the decay outside the light contact band is tied to the commutator. So our statement is that at second order, the commutator fixes the causal envelope of the signaling that can reach detector B. And then higher order terms may modulate this signaling, but always inside that envelope. Now, in order to claim anything in general order, we need to see if this commutator structure persists at every order. And this is the main result of this talk. The statement is the following: for every perturbative order M, every contribution to the signaling terms of the detector's B's final state contains at least one commutator. This gives us exact causality for compact supports of the detectors. And this also gives us that, for instance, in a Gaussian support, the residual leakage in the outside the light contact band will be always dominated by this commutator. So let me give now an idea of this proof. We will use the recursive structure of the interaction picture dynamics. We know that our state satisfies the von Neumann equation. If we now expand perturbatively this state, and we use that the interaction Hamiltonian is linear in the coupling constants, then we can say that the order M contribution is obtained by commuting the Hamiltonian with the order M-1. We can then integrate this, and well, since the Hamiltonian is a sum of both Hamiltonians, order M will be a sum over a nested commutator of different sequences of A Hamiltonians and B Hamiltonians. As we have said, we are only interested in sequences containing at least one A Hamiltonian and one B Hamiltonian. That is why all the terms that we obtain are of this form. And now the proof follows, but showing that using repeatedly the Jacobi identity, we can reorganize this expression into terms containing an explicit AB Hamiltonian and a remaining term of this form here. But this remaining term does not contribute to the final state of detector B because it vanishes under the partial trace of over detector A because of cyclicity of the trace. And then we claim that every surviving term every surviving term contains at least one AB Hamiltonian commutator. And since the coupling constants and the switching functions are scalar functions, and both detectors' Hilbert spaces are independent, every such commutator yields a field commutator, which is the object that we wanted to find at every order. So just to summarize what I've said, second, third, and fourth order estimators show that they share the same causal envelope. We have shown that arbitrary order, every surviving signaling term contains at least one AB field commutator. This gives us exact causality for compact support, and for Gaussian smearing, the residual signaling will be always an effect of the commutator and will be always tied to this commutator. And I just wanted to add that the same interpretation applies to any non-compact smearing, but here we have worked with Gaussian smearings. And with that, I would like to end my talk.
Thank you so much. Do we have any questions? Yeah.
There's room too. Thanks for the talk. So you did mention that the commutator would basically, I mean, every single term would be proportional to the commutator in the end, this mirrored commutator, if you want to control the causality violations. This is true, makes a lot of sense. Now my question is whether you have any sort of bound for the rest of the terms that are multiplying this commutator. So what I mean here is like, as far as I know, we don't have a proper proof that the sum converges, the Dyson series converges in this case, right? And this means that technically, although every single term there is proportional to this commutator and you can claim that it's going to be, you know, modulated by it, in principle, one could see that if the series diverges, then, well, these terms are still increasing like crazy, although they're all increasing like crazy, but proportional to this commutator, but the nth term is increasing. So have you thought about this large n limit of the Dyson series and how this commutator argument can apply there?
Okay, so yeah, we have thought of trying to say something more about the general order terms. We have not yet done anything there. This is like all the work that we've done so far. But yes, we are aware of that, and I don't know if any of my colleagues wants to add something, but
it's helpful. I've seen a proof that the Dyson series for the unruly detector coupled linearly to a scalar field has always a non-zero radius of convergence. That proof is by people, but I've seen it and it works. So the series is convergent, at least for some small value of lambda, it will be convergent.
Yeah, thanks. I just want to be sure I understood the dimensionality dependence. Can you go back to one of the graphs early on where you had that with the blue? No, yep. Early. Yeah. Okay. That. Yeah. So it looks like I'm having a bit of trouble seeing the colors, but it looks like when you go to the highest order, everything peaks in the blue band. Roughly speaking, is that right? Where n equals 3 seems to split into 2 peaks, but still within the band. Is that correct? I'm not sure I'm seeing it properly.
Yeah. So if you mean that there are terms that
the green, right? The green dot dashed.
Yeah, the green and the orange. Those terms are also the ones that are different here.
Yeah, but I'm trying to see. So for n equals 1, it looks like the whole thing. The contribution peaks within the band, right? Mm-hmm. And for n equals 2, it looks like it mostly does, except for the little bump to the left, or am I not seeing that correctly? That's what I'm having trouble discerning. Okay. What's n equals 2? Is the green only to the left, or is there a big peak in the middle?
I'm not sure if I am understanding you, but so yeah, here this peak is at the left. And
no, but the green one, E4, is...
I think there's a green peak inside.
That's what I think so. But
okay, here.
There's a bunch of dotted lines.
Okay, I think this green...
No, isn't it to
Do you
the
mean
right
this
of
green?
that?
Here?
Yeah, that one. Isn't that the green one?
Yeah, this is the green and the orange together here.
And then in the other one, it peaks. So, okay, so now I think I see it. So would the total... Oh, I guess I should hold this up. Would the total be... for any given dimension, would it be the sum of all those contributions? Or is E4 the sum of everything up to E4?
No, E4 is just the... So each of these, for example, the green line are the 4th order terms that are proportional to lambda B, lambda A,
Okay, so if I wanted the whole thing, I'd add up all of those together. Is that right?
Yeah.
Yes. Okay,
so here
thanks.
we are omitting some constants.
Thank you. That's what I couldn't quite get.
All right, okay. Let's thank Aitor one last time. And then all right, for our next speaker, we're going to hear from Julius, who's going to be telling us about purification or the cost therein using the quantum energy teleportation protocol. Julius, the floor is yours.
Yeah, thank you. Okay, so sorry for the technical difficulties, right? Someone always has to have them, and today it was my laptop. Okay, so yeah, my presentation is called The Cost of Purification via Quantum Energy Teleportation. And this is done in collaboration with Boris Ragula and supervised by Dr. Eduardo Martín-Martínez. Okay, so today's conference, of course, is about quantum information. And one of the main things we study in quantum information are quantum protocols. I'm sure we've seen many of those today, but here I have some examples. So quantum key distribution, quantum teleportation, superdense coding. And the reason we're interested in all of these different protocols is because they have a lot of applications. So here, for example, in encryption, communication, computing, and so on. And one of the things that most of these protocols have in common is that they rely on pure states. Okay, so all of these rely on pure quantum states. Pure states are hard to make, but we do have protocols to create them. For example, algorithmic cooling protocols. So here, for example, the partner pairing algorithm or SR gamma. These work. One limitation that they do have, though, is that they become less efficient in strongly coupled and interacting systems. And so how do we overcome this problem? Well, thankfully, in 2005, Masahiro Hotta came up with another protocol called quantum energy teleportation. And this one seems very promising because as was shown in this paper here, it can outperform conventional cooling methods despite the presence of strong correlations. And the question we're trying to ask is, what's the cost of doing this? So what is the cost of using QET for cooling? Okay, so how am I going to answer this question? Well, here we have a little table of contents. So first, I want to introduce what is QET. So I'll talk about two protocols which are equivalent. Then I'll show that you can, in fact, purify states using it. Then we'll get to the question, so what do I mean by cost of purification? And then I'll explain the methods we did. So our initial approach and then a second attempt. Okay, so let's begin with quantum energy teleportation. So consider a system of two entangled qubits, okay, called qubit A and qubit B. And to particularize them, give each of them a local Hamiltonian that looks like this. And suppose also that there's this interaction term here, where we can see that we have some sigma x correlation between the two. We also have some parameters. So we have, for example, the energy gap size, and we have the coupling strength. And we also have this F scaling factor, which we just use to set the ground energy to 0, for example. So that's our model. Now suppose that the system starts in its ground state. So this ground state is also maximally entangled, or has max rank entanglement. Give Alice access to qubit A, Bob access to qubit B. Then the QET, minimal QET protocol consists of 3 steps. So first, Alice will make a measurement on her qubit and will get back a result alpha. Then she will classically communicate this result over to Bob, and Bob will apply a unitary depending on the result Alice sends him. And the result of this is that he's able to extract some energy from his qubit. Now, important for this protocol is also that Alice needs to make her measurement and send her result to Bob faster than it would take the energy injected by her measurement to propagate to qubit B. So if you do this, then you can be sure that the energy Bob gets out of his qubit was in fact teleported. Also, from Bob's perspective, it looks like he's able to extract energy from a ground state, whereas really we know Alice's POVM will in general inject energy, raising the system out of the ground state. So there's no violation here. Okay, so one remark. Numerically modeling and physically implementing POVMs can be cumbersome. So can we modify this protocol somehow maybe? And the answer is yes. So for that we can look at the Stein-Spring dilation theorem, which very roughly says that if you have some system S and you apply some POVM to it, equivalently you could dilate your system to S tensor S prime and then apply a unitary on this dilated system. Okay? So that's the essence of Stein-Spring dilation theorem. And so what this means is we can take as our S prime system a third qubit, an ancilla, call it the ancilla, and then we can replace Alice's POVM with a unitary. Okay? And so this gives what we call fully unitary QET. And of course, this is very similar to the minimal case. The minimal case uses local operations in classical communication, as we just saw. And so now this fully unitary QET would use local operations and quantum communication. And this quantum communication is, of course, done via this ancilla. And so the three steps are very similar to earlier. First, you bring in your ancilla, your just third external qubit, touch it to qubit A, and apply a joint unitary. Then you send your ancilla over to qubit B, and apply a joint unitary over there. And again, the result is you're able to extract energy. Of course, the unitary you apply over here on qubit B and ancilla will depend on the state of the ancilla. So it's in that sense that it takes the information over, similar to Alice's phone call. Also, this first unitary in general will inject energy, so again, there's no violation there. Okay. The minimal and unitary QET protocols are in fact equivalent. So for any POVM Alice could make, you can find a unitary that Alice could make on her qubit and an ancilla, which would give you the same protocol. Okay, so they're equivalent. And here I just wanted to show two examples where you have two different papers. One uses the minimal case, the other one uses the fully unitary protocol. And this means that you're able to switch freely between the two. And so for our project, mainly we're working with the fully unitary protocol. Okay, so that's QET. Now, it can also be used to purify states. To demonstrate this, I just want to go through a quick example. So take again the same setup we had earlier, right, with our qubits A and B, the same sigma x interaction. Starting in the ground state, we can very easily compute the initial purity right there. Then let's say that Alice makes some sigma x measurement, right? The parameters here aren't really important. What's important is that she's making a sigma x measurement because we have sigma x correlations. And then let's define Bob's arbitrary unitary like so. And the details aren't really important here. But the final state can, of course, be written like this. So if we start out in the ground state, then you apply Alice's measurement, then you apply Bob's unitary, and this will give you your final state. Having this final state, you can compute the final purity, and you can see the first two terms in your final purity are precisely the initial purity, and then you're going to have to believe me that for some set of parameters you can choose, you can find that the final purity is in fact greater than the initial one. And so it's in the sense that via QET, you can purify qubit B. This is pretty interesting and also has important applications, for example, in those algorithmic cooling protocols. Right? So in those cooling protocols where you need some way to purify a qubit, right? You can see you can use QET for this. So there's cool applications for that. Okay, so this brings us to the research question. Given the QET process, what is the relationship between the extracted energy and the purification of the state? How are they related? More specifically, for our project here, what is the cost of optimally purifying? Okay, so if I find the optimal unitary to purify as much as we can, how much will this cost me? Okay, so what's our approach? let's first particularize our ancilla. So let's give the ancilla the same free Hamiltonian that qubit A and qubit B have. Then let us place qubits A, B, and the ancilla in thermal states. Okay, so there's just two thermal states. We place them in at the same inverse temperature beta. It makes sense to put them at the same inverse temperature, for example, because in a measurement, if you connect qubit A to qubit ancilla, you can kind of intuit that they'd be at a similar temperature. So it's in that way that it makes sense to have the same inverse temperature here. Of course, since the ancilla is an outside system, we can write the full initial state by just taking the tensor product between these two thermal states. Okay, so this is how we define our initial state of A, B, and ancilla. After the protocol, our final state will be given by this, right? So again, we have our initial state, then just apply Alice's unitary, apply Bob's unitary, that gives you your final state. And we model our unitaries like so. So, for example, let's look at Alice's unitary. We exponentiate some H probe, where H probe is just a combination of all the permutations of the Pauli matrices. So H probe is just some arbitrary or general matrix, and then we turn that into our unitary operation. Okay, so this is how we model them. Then the optimization is over these J and K coupling matrices. Okay, this will give us a 32-parameter optimization problem to find the optimal unitary, which is a lot of parameters. And how do we do this? Obviously not by hand, so we do this numerically in Julia. Okay, so numerically in Julia, we optimize these J and K matrices to find the optimal operators, UA and UB. Okay, here just as a picture very quickly, we define our initial state, input them into the code spits out the optimal J and K, and from those we can compute everything. So what did this do? Well, if we plot the optimal purity of our qubits A and B, right, you can see it works. We tried many attempts, random seeds. We get a nice smooth plot showing us that really our qubits are optimally purified. Okay, this works really well. And so now we can ask the question, okay, if we use these operators to also compute the extracted energy, what happens? And that's where it breaks. So we can see that using the same operators, which give us the smooth purification plot, we get sporadic jumps, right? We get noise. And so the question now we have to ask is, okay, how do we always get the optimal purification operator, which gives us the best extractable energy, right? The least cost. That's the question. Okay, why is this happening? Why do we have this nonsense plot? Possible causes that we think could be happening is that our unitaries, the way we define them, are cyclic. So you can see here that they're equal, of course, up to this additional term, right, for any n. And of course, if we try to optimize the J and K matrices, which are in this exponent, maybe the optimizer is finding very, very high frequencies here, and then if you had very high frequencies, this is where machine precision errors could start to cause issues. So that's what we think is happening there. At high frequencies, machine precision errors start to mess with our unitaries. That could be one problem. Another problem we think could be happening is that, of course, states are equivalent up to some global phase. So we know, of course, if we want to compute some observable, there's no difference between the state psi and psi up to some global phase. But again, if, for example, we have a very high frequency here, machine precision could start to introduce some randomness or noise or something. And also maybe in the optimizer, some intermediate step, these different phases could maybe throw off the optimizer. So that's what we think is sort of happening. And how do we deal with this? Well, for this, we started looking at block spheres. So very quickly, what's a block sphere? Qubit states can be written in terms of 4 parameters, right? So if we have a qubit, you can have 2 basis states, 0 and 1, and then you have these 4 parameters, A, B, C, D. Of course, 4 parameters, you cannot visualize this, but you can make use of the fact that states are equivalent up to phase. You can use this to sort of eliminate one of your parameters, which gives you 3 left, and that you can visualize. And this you can do, what this gives you is a block sphere. So the way a block sphere works is it's a sphere where every point on and inside the sphere represents a state, an equivalence class of quantum states. Also, the outer shell of the Bloch spheres represents pure states, and the very center of the sphere represents all of your mixed states. Okay, so that's the Bloch sphere. And so, why is this useful? Well, because single qubit states can be very easily be written like so, where R is the Bloch vector. But of course, we don't have a single qubit state. We have three, A, B, and ancilla. And so the way we now write this state is inspired by this paper here, where essentially we take all the possible combinations of Bloch spheres. So what I mean by this is, you can see we have local Bloch spheres, so a Bloch sphere only on A, only on B, only on ancilla. Then we also have the AB Bloch sphere, A ancilla, and also all three together. So this is the idea. Writing our state like this, what does this do for us? Well, observations could be more intuitive in terms of these Bloch vectors. And also, in terms of these Bloch parameters, so the local Bloch vectors and mixing coefficients, for example, this could give us stronger restrictions, which would help the optimizer. And so what do we observe? Well, in fact, the local Bloch vectors for qubits A, B, and ancilla appear to be constant in the final state. Also, in the minimal case from earlier, the extracted energy is proportional to these local and mixing coefficients. So this gives us a lot of restrictions we can use to sort of help the optimizer and stabilize it and hopefully get better results. Also, what we find is that the optimal purification operations are non-unique. So what we can find is two different sets of unitaries, so UB and UA, and UB prime, UA prime, which are not equal. They will give you different final states, but they will give you the same purification. However, they'll give you different extracted energies. And so now what we have turned our optimization problem into is, how do we find, among all of these unitaries which optimally purify, how do we find the ones which give you the most energy out of it? Or in terms of the Bloch language here, the reason we introduced the Bloch sphere, we can frame it as, how do we find the unitaries which give you the optimal purification, as in map onto this Bloch sphere shell inside the Bloch sphere, but give you the most energy out. So, and that is where we currently are, and that's our idea. And that is it. So quickly to summarize what I talked about, I introduced two QET protocols, which use local operations and then classical or quantum communication. I showed that QET can purify states. Yeah, then the question we asked is, what is the cost of optimally purifying? I showed that numerical optimization, our approach of numerically optimizing these operators. We introduced the Bloch sphere formalism to try and help the optimizer to get more restrictions. We showed that the optimal purification operators are not unique, and this gives us our new optimization goal: find the optimal energy extraction under the condition of mapping onto this Bloch sphere shell. That's it.
All right. Thank you, Julius. Do we have any questions for Julius? Yes.
So I am familiar with the QET protocol when you couple to a quantum field, right?
Okay.
So how does this, because it's very interesting, the whole optimization, the whole idea here, right? And I imagine that in the future you would like to also apply this in more relativistic contexts and things like that.
Mm-hmm.
So given that you've been doing things with finite dimensional Hilbert spaces and local couplings and all this in this case, how do you think that this will translate into the relativistic case with relativistic field theories? Do you have an intuition about what would be the difference or what can actually be taken from this result in that case?
Yeah, so maybe I should say that this started out as an undergrad project, and so I don't know much, if anything, about QFT yet. So I actually don't know how QET in general formalizes to QFT, right? So I'm not too sure how this would apply. I think what we're trying to do is pretty general, right? We're just trying to write some code to find the optimal operators. If the jump from this QET to QFT style QET is not too different, which I don't think it is, but again, I don't know much. I think it should apply pretty straightforwardly.
All right, any other questions? If not, let's thank Julius one more time. And then for our final speaker of the circuit, we'll hear from Professor Achim Kempf, who will be giving like the career development talk of the Waterloo circuit.
Yes. Are we online as well?
Yes.
You're being broadcast.
Okay.
And then there's a dongle if you want to use the clicker, but it's up to you.
Oh, that's a small screen. Can you read that in the back?
Yeah.
Okay.
You can make it full screen maybe on your.
Yeah, I will. All right, I have half an hour, is that right? Okay, I'm not exactly sure what's expected of me today. Let's improvise a bit, and I'm happy to turn this also into a bit of a discussion, if you like. Okay, so this talk is about academic careers in physics, as far as I understand them. Let's start with the math of replacement. How long is a prof a prof? 30 years? 35 years? Right? If you become a prof in your early 30s, and you do it until you're 65, 67, something like that, it's like 30, 35 years. How many PhDs will they produce? How many PhD graduates will they produce in their career? Let's assume hypothetically it was one. Every prof gets to supervise one PhD student in their career, and that person graduates successfully. This is steady state. See, that person would be very likely to become a prof too, because as many profs retire, as much replacement there would be. For every prof that retires, there is somebody on the job market waiting for that job. But how many profs do you know who had only one PhD student in their career? How often do they have PhD students? How often do they graduate a PhD student? Some, perhaps once a year, there's a PhD student finishing. Others, maybe every other year. Now, what does that mean for the total number of PhD graduates that they produce? Well, if it was one every year, then, well, between 30 and 35 PhD graduates in their career. If it's one every other year that they graduate, it's half as many. It's like 15 or so. And the truth, the average is probably somewhere in between. It depends also very much on the discipline. So let's go with 20. Let's say it's about 20 PhDs over 3 to 4 decades. So that means we are facing here a replacement ratio of 1 in 20. So professors are putting 20 times more people on the job market than the job market can bear. Now, there would be, just a sec, there would be an alternative, right? We could just hire more people. Then there's replacement. Let's say we hire 2. So a prof retires, we hire 2. Financially, it would be possible, because at the end of the career, a prof typically makes twice as much as a beginner. So they could do it, but of course, they will become more expensive over time. And sustainable, it's not, because the number of professors would grow exponentially. Every generation, it would double, right? If we hired, instead of 1 out of the 20, if we hired 2 out of 20, the number of professors would grow exponentially, doubling every generation. Imagine if we hired 10 out of 20. The number of professors would grow by a factor of 10 every generation. So that's not sustainable. If we hired fewer than 1, then the number would shrink. In some systems, this is happening, that the system is actually shrinking because the population is shrinking. For example, in Japan. In other countries, the system is growing, like in India or China. So there they can actually hire more than replacement. But this is a priori what we face. It's a 1 in 20 replacement ratio, which means that if we assume a meritocracy, which is not necessarily fair to say, if we assume a meritocracy, it means that those who are aiming to become a professor better be in the top 5% of PhDs. Right? So you look around and you see 20 others, 19 others, you've got to be the top out of these 20 or among the top 5% and the top 5 of 100. It's not that bad though, not quite that bad, because it turns out that not everybody who gets a PhD in physics actually wants to become a professor. Many make the decision early on or later that they do want to go to industry and don't even try to get a postdoc job, and they don't aim for an academic career. And I read a few years ago, I don't know what the ratio now is, but a few years ago, the National Academy of Sciences in the US studied that, and the ratio was about 50%. So about 50% don't even try to do an academic career. They look at the situation and they say, nah, I don't want that uncertainty, so they go to industry immediately. This helps those who do want to do an academic career because it removes half of their competitors. So instead of having to be in the top 5% of PhDs, it's sufficient to be in the top 10% of PhDs. But so far, we've not talked about what discipline we are dealing with. And it very much depends on which discipline you choose. If you do what we may call standard physics, in the sense it's not super hyper theoretical, it's not super applied, somewhere in the middle, then yeah, that estimate that we just discussed applies. So you ought to be in the top 10% of PhDs on average, assuming a meritocracy, to have a good chance to get a professorship. But then if you work on something to do with AI or quantum, then of course, the situation is very different. It's very, very different because there's very high industry demand. If you know both quantum and AI and you're ready to go to industry, you might start with a salary of 200,000 US, right away from the PhD. It's a very different situation. You may not want to go to academia under these circumstances. In fact, universities struggle to compete on perks and salary in these fields. For example, here in our Faculty of Mathematics, we have computer science. And computer science finds it really hard to hire really great people, for example, in AI, because those great people could make a salary of above $1 million in industry, easily. It's very hard. There, the plates are completely turned. Table turns completely. So you would find it much easier to pursue an academic path, but you may not want it because it's so attractive in industry, because there you do the same things, you just get perks and much more money. On the other hand, if you do something that is on the more theoretical, unapplied and unapplicable side, such as foundations of quantum mechanics or cosmology, industry doesn't really pull that in. And if that's what you want to do, then you don't want to go to industry, right? There's no cosmology factory. So the industry pull is low, and in that case, you don't even get that benefit that I talked about earlier, which is that half of your competitors don't even want an academic career, and they go to industry right away. Not true in those fields. There, virtually everybody has made up their mind, I want to pursue an academic career. Which means it's not the 10% rule, it is the original 5% rule, because you're just facing that replacement ratio. So what does it mean to be in the top 10% or in the top 5%? What is that, a top postdoc? Well, the old metrics are, roughly speaking, those. You need to have a lot of papers in good journals, preferably top journals, impact factors, and maybe win some prizes along the way. Why are these the old metrics? I mean, why have they been so important? It's because hiring committee members who don't understand what you're doing can still evaluate these things. It's just numbers, you know. Oh, how many awards? What are the impact factors? How many papers? But in the future, that's going to be very different. What will matter is not paper volume, because you can pump out papers now by prompting them. So in the future, the metric is going to be vision and significance. How important is it what you do? How clear is it that this is important? How clear is the vision? How clear is the significance? And super important, you need to have exceptional oral communication skills. Why? For the same reason that homework is worth nothing now. Because homework, you can give the most difficult problems, and you get the homework back, and you know that person hasn't done it, right? Probably none of them has done it. Because it's so tempting to just shove it into the machine and get the answer out. No, when people need to evaluate how great is this researcher, they need to have them in the room, they have to explain their ideas, they have to convince the committee that it's in them and not in an LLM. They have to convince the committee that they are clear thinkers, they know what's important, and they know how these things work. You can tell when you listen to somebody whether they just memorized something from an LLM or whether that's really theirs. You have to own it, you have to display that you own it. Therefore, exceptional oral communication skills. It used to be that the single author paper was great because you heard the original voice of the author. No longer true. Now it's the presentation. That's where you find out about the person themselves. So this is the shift that comes with AI. Anything that's obtainable via prompting will be worthless. It's quickly becoming worthless, right? Because if you see some paper and you feel, yeah, I could have gotten that by just typing this into ChatGPT 5.5 at the pro mode, then what is it worth, right? So anything incremental is just taken for granted. It will be taken for granted that everything is very well written. That's no longer a plus, it's just assumed. And anything that's clearly just incremental will not count for much. The number of papers will matter less than ever, because you could write 10 a day now. No, what people will look for is depth, novelty, and significance. Hard to see, but you can still see that. You look through the paper and you check, is that really pushing the field forward? Which means don't focus on just pumping out a lot of papers because everybody's doing this and this will take over probably. No, you have to stand out. And you cannot stand out by quantity anymore. There's just no way. You have to stand out by quality. You have to make a difference. And let me also mention, please do learn AI. I've been preaching this for many years now. It used to be, over the past 5 years, that knowing how AI works, understanding neural networks, understanding what a transformer is and how it operates, used to be an advantage, but it's switching from an advantage to a necessity. I've been in many hiring committees, and over the past few years, I don't remember, did we hire anybody without AI skills? I don't think so. And that's because every department of physics wants to upgrade their AI knowledge. They know that the curricula will change. They need people who can teach it, people who foresee how AI is going to impact the field. So work on those credentials. They're going to be necessary. It's no longer an option. It used to be my advice, well, if you want to improve your chances, learn AI. No, it's no longer an option. And so, strategic advice, first of all, be your own best critic. As you know, these large language models are very sycophantic. Maybe not so much Claude, but Gemini and ChatGPT are very prone to it. So they might praise you a lot for some ideas. Don't believe it. Be your own best critic. If you need feedback from the machine, prompt it to be harsh. Tell it, I don't need any sycophancy. You know, give me the straight dope. You have to have that. So be your own best critic. Prioritize significance over volume. You need to be able to explain to people why that is valuable and why it is new. You know, one deeply significant finding outweighs several incremental ones, because the incremental thing can be automated now. On an industrial scale, we haven't even seen yet to what extent the incremental stuff will be just taken out of our hands. And then, in order to prove yourself, don't rely on papers. You have to be able to go out there, explain your vision, explain your results very clearly, and along with the results, you need to convey that it's yours and that you have a vision and that this is not LLM generated, but it's generated by yourself. And it's genuinely new, unpromptable stuff where you just have the spark, the inspiration yourself. Just like homework counts for nothing anymore, it's when the student comes and sits the exam in the room in person without electronics, that's when the test is happening. And in research, it's no longer just the papers. The papers are super important, you can't do without them. But the proof that it's you behind it and not some stupid machine is in the presentations. Presentations have always been important, but they will be even more important just as the proof that it's you and that you have that power that's needed to rise above the machine. Any questions? Yeah?
So you said that the number of papers doesn't matter more, but you are pretty much the first person that I saw seeing that. Do you think that most of academics are still stick to the old system. They just count papers, and especially in North America.
Yeah, that's true. There's inertia in the system, and there's a transitional period where everybody rushes to publish more and more until it's so much noise that the grant agencies, the hiring committees will say, I don't care about that noise. I want to see just the stuff that sticks out. And we are in the middle of that transitional period now.
Oh, I see. Yes. Oh, thank you.
I was just, foreseeing where this is going.
So, Ahmed, thank you so much for all of the hints on this upcoming change, right? I think that they're very valuable. What I would like to ask you about is actually about the beginning of your presentation, because you mentioned, for instance, that each professor trains 20 PhD students, but much more than the replacement rate, right? And I've heard this before, right? And I always thought, sure, but a company has hundreds of interns, right? Or, companies have interns, and then, these people don't become jobless, I would say, afterwards. It's as population increases, job increase, overall, right? So what would be the difference, from academia to a more standard company in the sense, or something like that?
Yeah, I can tell you that. So let's just redo the calculation for industry now. The calculation that we did for university, how long is a academic career, 30, 35 years, how many PhDs do you produce, what's the replacement rate? Now, in industry, there are a lot of jobs for PhDs. And industry doesn't produce PhDs, just none. And that's the balance, right? That's the balance. Namely that those PhDs retire after 30, 35 years in industry, and they haven't produced any other PhDs. And there are a lot of scientists in industry. And that's why industry can absorb so many PhD physicists, right? Because they don't produce them themselves. So we are lucky in this, but it depends on the field. It's not the case for cosmology, because there's no cosmology industry. There's no quantum foundations industry. But there is a quantum computing industry, and in case you haven't taken notice of this, it's happening. Quantum computing is entering the post-quantum error correction era within the next 5 years. If you look at the counts of how many logical qubits there are, nowadays it's between 20 and 40. And if you look at the roadmaps of how long it will take for the various companies to produce processors with 100 logical qubits or more, logical means fully error corrected, those roadmaps are all saying that they will, with IBM or Google or QEra or whatever, they all say within the next 5 years, we will have more than 100 logical qubits. And just for comparison, from 60 logical qubits onwards, no computer can simulate what it does. If you have 70 or 80 qubits, or let's say 100, just to make it completely clear, then all computers of the world together could not simulate what a 100-qubit processor can do. And once you can build a unit with 100 logical qubits, you can build many of those units and then link them up with quantum communication. All of that, at least the building of these 100 logical qubits units happens within the next 5 years. Some companies say 5 years, some others, like QEra, says, no, this year. Do it this year, right? So this is happening. And you can imagine that all those billions that are being poured in that industry go into paying physicists, most of them PhD physicists. So that's absorbing a lot. It can absorb. In fact, there's a shortage of people who can do that sort of thing. And it has been a shortage for several years now. I remember when the pandemic hit, I got mail from Jack Hidari, who was Google X and Google Quantum, and he wrote this book, Practical Guide to Quantum Computing, and he sent me 35 copies of it, and he said, go ahead, educate people, I want to hire them all, right? And that was at the beginning of the pandemic in 2020. So that's a lucky thing that this is happening now, because when I was a PhD student, it was academia or bust. you basically either became a prof or you were not a physicist. There were very few true physics research positions in industry, and those that were there were experimental or applied physics, but not theoretical physics. So you either did cosmology or foundations or quantum gravity, or you were working in a bank or a software company. But it's not like that anymore. Now you can do quantum information, and I find that very cool.
So we have one more question from here.
Thank you for the insight. I have two small questions. The first one, you mentioned the metrics for a top postdoc. And I just wanted to know, in a sense, like, what's your evidence for that? Is that something that people are talking about, let's say, in the back rooms, or is this, like, there are some studies already on a shift regarding that?
Basically, I'm on hiring committees every year, so I see how things change. And yeah, it's very clear. So AI is now really necessary. And let me add a detail that I didn't mention here. And that people learn too late. So let me tell you early on. If you want to apply for postdoc jobs, then what's your best strategy? Has been and still is. Best strategy is to work in the middle of a field and contribute something interesting somewhere in the middle of the field. Middle of the field because a lot of people will pay attention. It's built in because you work on what a lot of people are working on. So you have built-in guarantees for citations, for example. And you have more of a network that, you know, bigger conferences, you meet more people, all of that helps. But does it help when you want to apply for a professorship? It's a little different. And the reason is that when you apply for a faculty position, the committee will ask, oh, okay, so what is this person known for? In other words, where did you stand out? Where did you not do what is happening in the middle of the current, but what is really attributable to you? Another way of looking at it is it just incremental? Is he really good, or is she really good at doing incremental work? You know, popular stuff in the middle of a popular field. Or did they do something unusual, something unexpected, made a name for themselves? It's a different thing. It's harder to try to do your own thing when you are looking for a postdoc position. But it's kind of easier to stand out when you do your own thing when you apply for a faculty position. It's very hard to square those things because you have to present yourself differently, right? You have to do different things. You have to have been more risky when you apply for a faculty position. And along with that comes another change, which is when you apply for a postdoc position, you apply on the strength of your research proposal. And the research proposal is usually a project or a set of projects where you explain, I did this and this, and now I want to do that and that because these projects are going to be great. This is how you should do it as a postdoc, but not for a faculty position. For a faculty position, the committees are looking for somebody who has a vision, who has a program. Instead of having a project or two, you need to demonstrate that you have a program, which means you have a general vision of where you want to go, from which then projects follow. But it's a matter of graduating from the project thinking to the program thinking. This is never explicitly said in the hiring committees, but it's my experience that in hiring committees, this is what they're looking for. No, sometimes they would say, oh, that person is too junior. But on the other hand, they sometimes hire people from their PhD, right? So it's not really how junior or senior a person is. It's how junior or senior they act. And if you can early demonstrate that you have a vision and a program and you stand out and you live up to what you say, then that's what gets you a faculty position. Or can, I mean, there's no guarantee, right?
Yeah, so I had the other question also can be a short comment. What do you think is the value of teaching in the middle of all of this?
The union of research and teaching goes back to about 200 years ago, when the modern university was invented by a fellow by the name of Wilhelm von Humboldt. And he had this idea that a researcher needs to be a teacher as well. It has obvious advantages for the students, of course, to be taught by a researcher who is at the forefront of the field. But what advantage, and I guess that's your question, is it for the researcher to be teaching? Now, I don't know whether Wilhelm von Humboldt had this in mind, but I think there is a huge advantage, which is that learning to teach is learning to think clearly. Because otherwise, how can you teach, right? It's the difference between describing and explaining. Anybody can describe. You know, there's a chair here, and so, right? But an explanation is different. Right? And keep that in mind in your presentations, keep that in mind in your papers too. Imagine you travel to Rome as a tourist and you hire a tour guide, and the tour guide shows you around the Forum Romanum and says, look at that stone there, how yellow that is. And then look at that column here, and then you see there's a ruin there. That's descriptive, but it tells you nothing, right? You need the explanation, you need the story behind it. This is the ruins of the Senate of Rome, and on those steps is where Caesar was assassinated, right? That sort of thing, the explanation behind it. And when you teach, you learn the difference between describing stuff, where all the students fall asleep immediately and hate you as a teacher, and explaining things where they will think, oh, okay, now I understand what's going on, right? And so teaching is very valuable because it teaches yourself to think clearly so that you can express the explanations and not just mere descriptions. And that, I believe, is useful for two things. Fundamentally for research as well, because it clarifies your thinking. You just get into the habit of thinking of why. Not just what, but why is it like that? And secondly, presentations are super important, have always been super important. I've seen careers made and destroyed by presentations of high and low quality. In this room, on this stage, there was a fellow who on paper was the winner in the competition for a faculty position here. And then presented so badly that we didn't hire him. I hired somebody else. He just screwed up the presentation. We felt, no, I mean, we can't let him loose on students. There's no way. And in any case, we didn't understand it. His writing was fine, but it just, didn't work. And on the other hand, you know, sometimes it happens. People give a presentation and they get 1 or 2 job offers from somebody in the audience. It's so important. And if you have taught hundreds of hours in class, which you accumulate quickly over the years, then that trains you for general presentations. So I would advise everybody to teach. And when you're a postdoc, you don't have to teach, and I wouldn't advise you to sign up for teaching because you need all your time for research, but I would advise you to give presentations wherever, whenever you can. Preferably with the informal settings first, and find a friend or two who give you honest feedback and who tell you that you suck when you do, right? And how you fix it before you are on stage at a big conference with 100 listeners, right? Yeah.
All right, any other questions? Yes.
Yeah, I would follow up on the teaching question. So how, like in the hiring process, how does it weigh the research versus teaching and presentation skills, like in the decision to hire a faculty member?
Up until 15 years ago, here we had our candidates also give test lectures. Like half an hour they would teach resonance, for example, something about ODEs or something, just to see how they can teach. But we gave up on that because when they give a presentation about their research, you can also tell how good they are as teachers. Generally, in modern day, I would say that at good universities, they will never ask you to do a test lecture. It's all about the research. And the ability to teach is inferred from your research talk. But the ability to teach is very important. It's just no longer an important part of the hiring, of the interviewing process. It's still indirectly super important because it is contained in how you give your presentation. And don't underestimate, even at the top universities, how important it is for them that you're a good teacher. Because usually at universities, technically 40% of your time is spent researching, 40% teaching, and 20% pushing paper. Bureaucracy, they call it service, right? You serve the gods of bureaucracy. Right, but technically research and teaching at most universities is treated equally. And universities are very aware of how popular their instructors are. But generally, of course, the research is the dominant factor in hiring at top universities.
All right, let's end it here. Please join me in thanking Dr. Kempf for the talk. Thank you so much. So yeah, this should be the end of the circuit. Before I hand it off to Rick to conclude, I just, on behalf of all the organizers, I want to thank everyone who presented, everyone in attendance. I hope this was fun and informative. Also, again, have to acknowledge funding support from both the Department of Applied Math and the Institute of Quantum Computing here in Waterloo. And yeah, thank you so much. And Rick?
Thank you, Ahmed. So let's start, please, by thanking the local organizers who made this possible. Ahmed, Matheus, Ireneo, and Boris, thank you so much for having organized this. Well, this is the end of the RQI circuit in Waterloo, but it's not the end of the RQI circuit. We're not even halfway done. This is 4 out of 9. So next week we're going to be in Manchester. It's not going to be the same time because of time zones, but everyone here is welcome to join online and watch it. And then the week after, we'll have it in Dublin. So we have actually members of the DS community here, the Dublin Institute of Advanced Studies. So it's yes, please join us online. And thank you so much for watching. Thank you so much for being here. Thank you.